Welcome back to the Kritia AI Labs Tech Interview Series, the show where we put experienced engineers through the kind of interview that actually separates the people who have lived inside a system from the people who have read about one. I am Balu, Senior Technical Architect at Kritia AI Labs, and today we are running a full-length Principal Python Engineer mock interview. My guest today is Saket, 14 years writing Python professionally, currently leading a team of 10 engineers and actively looking for his next move at the principal or staff level. He reached out to us because he wanted a genuine stress test before stepping into those conversations, not a friendly review, a real interrogation. So that is exactly what we are going to do. We are going to cover testing as an architectural constraint, salary failure modes in fintech pipelines, Python supply chain security at the institutional level, SQL alchemy transaction semantics, API contract ownership across front-end teams, and the hard problem of hiring signal calibration. 14 years is a long time. The question is always, has that experience compounded or has it just repeated? We are about to find out. Saket, welcome to the show.
Thank you, Balu. Genuinely glad to be here. And yeah, I specifically asked for the version that does not go easy on me, so let us do this.
Perfect energy. Let us start with something that sounds simple but is not. 14 years of Python. You have watched the language evolve. You have watched engineers come up through it. Here is my question. If you had to name the single Python language feature, not a library, not a framework, the language itself that you most consistently see misused by engineers with 5 to 8 years of experience, what would it be, and what does the misuse pattern actually look like in production code?
Good opener. I want to say context managers, but I'm gonna give you the one that actually costs the most in production, and that is generator-based coroutines and the send protocol. Not async await the older generator machinery underneath it. Engineers in that 5 to 8 year band have enough experience to reach for generators confidently. They use them for lazy pipelines for streaming large data sets, all the correct textbook reasons. But almost none of them actually use generators correctly, and more importantly, almost none of them handle the stop iteration propagation correctly when a generator is nested. The misuse pattern looks like this. Someone writes a data transformation pipeline. Each stage is a generator and they wire them together beautifully. It works perfectly in testing. Then they hit a specific input shape in production where one stage yields 0 items and the downstream generator never gets primed, and instead of a clean empty result, they get a stop iteration that bubbles up through a try except block that was written to catch a different exception entirely. In Python 3.7 and later with PP479, that stop iteration gets converted to a runtime error inside a generator body, so the error message is completely misleading. It does not say anything about the actual zero yield upstream stage. I have seen this exact bug in production 3 times across 3 different companies. The stat trace always looks like an internal framework error. Junior engineers spend hours thinking something is wrong with their async setup. The actual problem is a misunderstood generator lifecycle.
That is a genuinely non-obvious answer. Give me the code smell at the core site. What does the broken version look like versus what you would want to see?
The broken version at the core site looks like this. You have a function that accepts a generator and does something like for item in transform source.gen, and that is it. No check that source.gen was actually primed. No handling for the case where transform yields nothing. The caller just assumes the pipeline ran. What I want to see instead is explicit priming where send is involved, and for pure yield pipelines, I want to see the consuming code explicitly handle empty iterators as a valid branch, not as an error as a branch. Something like results equals list pipeline, and then if not results, handle that explicitly before continuing. The deeper fix is architectural. If you have a pipeline where empty output from any stage is a valid state, your pipeline should not be a chain of bare generators. Wrap each stage in a class with explicit state, or move to a proper stream processing abstraction. Generators are beautiful for read-once sequential data where you control both ends. They get dangerous when you hand them across abstraction boundaries to code that does not understand their lifecycle.
When you spot this in a PR, do you block it or let it through with a comment? What is your actual decision heuristic?
It depends on where the generator is living. If it is internal to a module, a private implementation detail, never exposed across a service boundary, I leave a comment, explain the failure mode, and ask the author to add a test that covers the zero yield case. I do not block, but if that generator is crossing an abstraction boundary, being passed as a parameter to another module, being used as a return type in a public interface, or being iterated inside a celery task, I block it. Because now the lifecycle assumptions are implicit and the next person who touches that code does not have the context I have in my head. The blast radius of the bud is no longer contained. My general heuristic for blocking versus commenting is, can the person who fixes this bug in production at 2 a.m., having never seen this code before, figure out what went wrong from the stack trace alone? If the answer is no, I block.
That is a clean heuristic. The 2 a.m. stranger test, I like that framing. Second warm-up question, and this one is metacognitive. Walk me through the last time you genuinely changed your mind about a Python architectural decision, not because someone told you to, not because a tech lead above you mandated it, but because you ran into evidence in production that your mental model was wrong. What was the decision? What was the evidence? And what did you actually change?
This one I can answer specifically, and it is still a little embarrassing to say out loud. About 2 years ago, I was a strong advocate for moving a set of our internal data processing services from synchronous Django management commands to async FastAPI endpoints backed by asyncio. The argument I was making was completely standard. We have IO-relay workloads. Async will reduce thread overhead. We will be able to handle more concurrency with fewer resources. Textbook reasoning. We migrated 3 services, deployed to production, and for about 6 weeks, everything looked fine by the metrics we were watching: request latency, error rates, memory. Then our DBA started asking why connection pool exhaustion alerts were firing at much lower traffic levels than before the migration. I dug into it. What I found was that our async services were using asyncio.gather to fan out sometimes 50 to 200 small database queries concurrently by request, because async makes that easy to express. In the synchronous version, we did those queries sequentially because the code naturally serialized them. The sequential version was actually better for the connection pool because it held one connection for a short sequential window. The async version was holding connections open simultaneously across all branches of the gather, even though each individual query was fast. So, I had replaced sequential connection borrowing with concurrent connection borrowing, and I had done it invisibly because asyncio makes concurrency so cheap to express that you do not notice you are doing it. The mental model I abandoned was, async is better for IO heavy code as a general rule. The corrected model is, async is better for IO heavy code where the IO operations are independent and the resource they compete for has headroom. If the shared resource, in this case the connection pool, is the bottleneck, async can make things worse by saturating it faster.
How long was the gap between deploying that decision and the production evidence landing on your desk?
6 weeks of normal traffic, then the issue surfaced during a promotional campaign that pushed traffic about 2.5 times the baseline. So we did not have enough load in normal conditions to exhaust the pool. The fanout looked fine at low concurrency. It only became visible when per request fanout multiplied by request volume exceeded pool size simultaneously. And the honest answer to your follow-up is, if I had instrumented connection pool wait time from day one instead of just watching query execution time, I would have seen the pool utilization climbing even at normal traffic. The signal was there, I just was not measuring the right thing.
That is exactly the kind of answer I was hoping for. And it sets up what we are going to do for the next 35 minutes, which is go deeper on all of these systemic thinking questions. Let us move into the technical deep dive. Question 3. Testing, and I want to start here because most senior engineers treat tests as a QA function, not an architectural signal. Here is the scenario. You have a fast API service with a dependency-injected SQL Alchemy async session. Your PyTest suite has 400 tests, all passing at 100% line coverage. A mutation testing run with Mute or Cosmic Ray reveals that 60% of your mutations survive. As a principal engineer, what does that number tell you architecturally, not just about test quality? And walk me through your triage process for deciding which surviving mutations actually matter.
60% mutation survival with the 100% line coverage. That gap is telling you something extremely specific. It is telling you your test execute code paths, but they do not assert on outcomes. The coverage number is a measure of what runs, not what is verified. Architecturally, what a high mutation survival rate means to me is that the module being tested does not have clearly defined behavioral contracts. When your tests only check that a function ran without raising an exception, or they check a very narrow slice of the return value, mutations that change branching logic, comparison operators, or boundary conditions survive because there is no assertion that catches the difference in outcome. The deeper architectural signal is about coupling. If your mutations are surviving in your business logic layer, the layer that decides whether to approve a payment or calculate a price or validate an address, that tells me the business logic is probably not expressed as pure functions with clear inputs and outputs. It is probably entangled with infrastructure, the database session, the HTTP request context, the authentication middleware. Entangled code is hard to assert to against precisely because the behavior depends on a complex implicit context, not a simple input-output contract. So, the high mutation survival rate is not just a test quality problem, it is a design feedback signal. The tests are hard to write precisely because the code is hard to reason about precisely. For triage, I do not try to fix all 60%. I cluster the surviving mutations by module and by the type of operation being mutated. Mutations in code that touches external contacts, API response shapes, database writes, event payloads going to a message broker, those I prioritize immediately because a surviving mutation there means a behavioral change that a consumer might depend on can slip through undetected. Mutations in pure internal transformation logic are lower priority. Mutations in error handling code replacing res with pass or changing exception types I treat as high priority regardless of where they are because silent failure is worse than wrong output.
Good. You joined a team, you ran this, you got 70% survival rate. What are the first two conversations you are having with that team?
First conversation is not about the tests. It is about the business logic layer. I would ask the team to show me where the core domain decisions live in the code base. I want to see if those decisions are expressed as pure functions that I can call with a dictionary and get a result, or whether every business decision is wrapped inside a request handler or a database transaction. If it is the latter, I am going to explain that the mutation survival rate is a symptom of a design problem, not a test discipline problem, and we need to talk about extracting logic before we talk about writing more tests. Second conversation is about what the team actually trusts the test suite to catch. I would ask them, if you change the operator in a price comparison from greater than to greater than or equal to, would your tests catch it? And I would look at their faces, not wait for a verbal answer, because that expression tells me how much they actually trust their own test suite. If they have low trust in it, they are probably compensating with manual QA or feature flags and slow rollouts, which is fine, but it means the CI pipeline is not actually the safety net they think it is.
Where does property-based testing with hypothesis change this picture? Does it reduce surviving mutations, or does it change which mutations survive?
It changes which mutations survive, and the change is directionally useful. Hypothesis is very good at finding boundary conditions, off by one errors, MP input handling, type edge cases, because it generates inputs you would not think to write manually. So mutations that change boundary comparison operators tend to get killed by hypothesis when you could not kill them with example-based test. But hypothesis does not help with mutations in code where the property you care about is domain-specific. If I mutate a line that checks whether a payment status is pending versus processing, Hypotheses cannot generate an assertion that distinguishes those states unless you have explicitly encoded that business invariant as a property. So it shifts the survival distribution, fewer boundary condition survivors, more domain logic survivors, which is arguably a better shape of problem to have because domain logic survivors are easier to reason about and write explicit assertions for. The other thing hypothesis does that mutation testing cannot do alone is surface the cases where your code is doing something technically correct but semantically wrong. It passes all your example test, it passes mutation, but on an input of -0 or an empty string versus none, it gives a different result than the invariant you intended. That is where hypothesis earns its keep as a design tool.
Excellent. Moving to distributed systems. This is a salary question, but it is really a correctness question. Scenario fintech payment processing pipeline, salary workers, Redis as the broker, PostgreSQL for state. A network partition between Redis and your workers lasts 47 seconds. The partition heals. Walk me through every category of correctness problem you now have in your task queue, your result backend, and your application database, and tell me which ones salary handles and which ones you have to handle in application code.
Okay, let me work through this layer by layer. In the task queue layer, during the partition, workers cannot send archives back to Redis. What happens depends on your axlate configuration. If axlate is false, which is the default, the task was occurred at the moment it was received before execution. So if the worker received the task, started processing it, and then lost connectivity, the task is already gone from the queue even if execution was interrupted by the worker crashing or being killed during the partition window. You have lost those tasks silently. If ax.lib is true, the axik happens after the task function returns. During a partition, that axik cannot be sent, so when the partition heaves, Redis still thinks the task is unacknowledged. Depending on your visibility timeout, the Redis setting that controls how long before an unacknowledged task is required, you will get DDLRY. In a 47-second partition, if your visibility timeout is 60 seconds, you are right at the edge. Tasks that were executing during the partition are likely to be delivered when the partition heals. That is your duplicate execution risk. In the result backend layer, if you are using Redis as both broker and result backend, which is common, the result backend state is also unavailable during the partition. Any task that completed during the partition window cannot write its result. The caller polling for results will see a timeout or an indefinitely pending state. After healing, the result may arrive late or may be lost entirely depending on your Redis persistence configuration. If you are using RDB snapshots only with a long interval, results written to Redis in memory just before a restart scenario could be lost. In the application database layer, this is where it gets interesting. If your task is doing something like begin transaction, update payment status to processing, do external call, update status to completed, commit, and the partition interrupted the worker mid-execution, you may have a transaction that was never committed, leaving the payment in processing indefinitely. Or if the task ran to completion but the result write to Redis failed, the task completed successfully, but your calling code never got the confirmation, so it retries and now you are executing the payment twice. Salary handles basic redelivery mechanics after partition heals, the visibility timeout requeue, and task routing reconnection. That is it. Your application code must handle idempotency. Every task that touches money must have an idempotency key, a unique identifier for the logical operation that is checked before execution. First thing the task does, look up that key in the database. If it exists and status is completed, return the stored result immediately without re-executing. This is the only real fix for at least once delivery in a fintech context. Salary gives you at least once. Your code must implement exactly once semantics on top of that guarantee by making every operation idempotent.
If you are redesigning this pipeline today with access to any broker, Redis, RabbitMQ, Kafka, SQS, which would you pick for fintech payment processing specifically given that partition scenario, and why?
For fintech payment processing specifically, I would pick SQS with FIFO queues. Let me explain why that is not the obvious answer and why it beats the alternatives for this specific use case. RabbitMQ gives you better delivery guarantees than Redis through publisher confirms and durable queues, but it is operationally complex to run at high availability, and the partition recovery story requires careful cluster configuration that most teams do not get right. Kafka is where a lot of engineers would go, and I understand why. The durability story is excellent, the replay capability is excellent, but Kafka with Celery is a friction point. Celery's Kafka integration via Confluent Kafka has historically been less mature than the Redis and RabbitMQ integrations, and in a fintech context where you need exactly once processing, Kafka transactions are powerful, but they require your producer and consumer to be in the same transaction scope, which does not map cleanly to Celery's task execution model. SQS 5.0 with message deduplication IDs gives you exactly once delivery at the broker level. SQS deduplicates messages with the same deduplication ID within a 5-minute window. So if your Celery worker enqueues the same task twice due to a partition and retry, SQS drops the duplicate. You still need application level idempotency for the execution side, but you have eliminated the duplicate delivery problem at the queue layer. The managed service operational simplicity is also not nothing one fewer system to operate under pressure at 3 AM when a partition is happening. The trade-off is throughput ceiling. SQS 5.0 is limited per message group, and latency, since SQS has higher baseline latency than Redis. For payment processing where correctness trumps raw throughput, that trade-off is worth it.
Good answer. Let us move to security, and I want to be clear, this is not an injection or XSS question. Here is the scenario: your team maintains an internal Python package published to a private PyPI server. A new engineer on your team adds a dependency in setup.p that has the same name as a public PyPI package but at a higher version number, and that public package is not from your organization. 3 days later, your production build pipeline starts pulling from public PyPI instead of your private mirror. Walk me through exactly what happened at the PIP resolution level, and as a principal engineer, what systemic controls you put in place so this class of attack cannot recur.
This is a version resolution race, and the mechanics are specific to how pip flattens multiple index URLs into one candidate pool. When your CI pipeline uses extra index URL to point at your private mirror alongside public PyP, pip does not treat those sources as a hierarchy with your private mirror taking precedence. It queries both sources, collects all available versions of the requested package from both, and then selects the highest version number regardless of which source it came from. So if your private package is named internal payments SDK at version 1.422, and an attacker, or in this case an accidental name collision, causes a package with that exact name to exist on public PyPI at version 2.0. Pip will pull version 2.0 from public Py because it is numerically higher. Your private mirror loses the version race. The 3-day delay makes sense. It takes time for the attacker to publish the package, and pip caches don't immediately invalidate. So the first few builds after the dependency was added may have used a cached version from your private mirror before the cache expired and pip started doing fresh resolution. So let me be concrete about how I would actually confirm this diagnosis and then stop the bleeding, because this was presented to me as a live incident, not a design review. Confirmation first. I would pull the exact resolved version and download URL from the build pip install with the verbose flag prints the source URL for every package it resolves, and pip's JSON report output gives you the same thing machine readably. That tells me unambiguously whether internal payments SDRs came from the public index or the private mirror on the failing build. Then I diff the resolved UR against a known good builds log. The moment the source host flips from the internal mirror to files.python hosted. The diagnosis is no longer a theory, it is in the log. The immediate stopgap today before any architecture changes, pin the affected package to the known good version and source with an exact specifier and clear pip's cache and CI, so the next build cannot re-resolve to the public artifact. That buys me the afternoon. The durable fix is where I want to invoke something specific that changed the landscape here of 708. Historically, PIP 708, historically PIP had no notion of which index was allowed to serve a given project. That is the entire root cause of the version race. PP 708 adds a repository level metadata that lets an index explicitly declare which projects it is authoritative for. So a private index can say internal payments SDK is mine, do not accept it from anywhere else, and a modern resolver honors that. It is a standard Stack answer to exactly this class of confusion, and it is a direction I would move the build toward rather than relying forever on operational discipline. Discipline fails on a Friday. Metadata does not.
Does Poetry or Roof change this attack surface compared to PIP? Is one of them structurally safer here?
Woof is structurally safer, and it is specifically because of how it handles source priority. Woof, when configured with multiple sources in pyproject.tommin, supports an explicit priority ordering between sources. You can declare that your private index is the primary source and that public PyPI is a fallback only, and more importantly, you can declare that specific packages should only ever be resolved from specific sources. That is a first-class concept in UV's configuration, not a workaround. Poetry introduced source priority as well, but it has had historical inconsistencies in how it applies that priority across different versions of the log file format, which means teams using older Poetry versions may not be getting the protection they think they have. With UV source configuration, you can say package named internal payments SDK must resolve from source private mirror full stop. If it is not found there, the build fails. It does not fall back to public PyPI. That eliminates the version race entirely for packages you control. The other thing UV does better is that its log file is genuinely comprehensive. It logs the full dependency graph, including hashes in a way that is resistant to re-resolution on install. You generate the log file in a trusted environment, you commit it, and you installs from the log file rather than re-resolving. The attack surface for substitution shrinks significantly when there is no re-resolution happening in the production build.
That is a strong answer on UV. I want to stay in the ecosystem but move to a different layer, SQL Alchemy internals. And this is a question about something SQL Alchemy does silently. You are building a service with async SQL Alchemy sessions. You have nested transactions, a top-level transaction with save points used for rollback within a task, and you have celery tasks that share session state across process boundaries, or believe they do. Walk me through what SQL Alchemy's unit of work pattern is doing to your transaction semantics in that setup that you might not realize until something goes wrong.
This is a layered problem, and the failure is almost always silent until it produces data corruption. Start with the unit of word pattern itself. SQL Alchemy session is a unit of word. It tracks all objects loaded or created within that session, accumulates pending changes, and flushes them to the database in dependency order when you commit or when it decides to flush automatically before a query. The critical word is automatically. The session can and will issue a flush before a select query if it has pending changes that might affect the query result. This is called auto flush, and it is on by default in both sync and async sessions. In a nested transaction setup with save points, this auto flush behavior can cause a flush to happen inside a save point context when you did not intend it. You create a save point, expecting to be able to roll back to it cleanly, but before you even do any writes, SQL Alchemy has flushed pending changes from earlier in the session into the database under the save point scope. When you roll back to the save point, those changes get rolled back to changes that were flushed and already visible to your own queries within the transaction, so your code has been behaving as if they were safe. They were never committed, only pending. But if you are not watching your flush boundaries carefully, you will silently lose writes that the rest of your code path believed were persisted. With async session specifically, the problem is compounded. The async session is designed to be used within a single async task or request, one coroutine, one session, short-lived. It is emphatically not designed to be shared across coroutine boundaries. But the pattern I see in code bases is create a session at application startup or module level, then use it across multiple celery task invocations. This is a process boundary problem. Celery forks worker processes and a session object created in the parent process is not safely shareable across fork. The SQL Alchemy connection objects inside the session reference file descriptors that are duplicated by the fork but represent the same underlying TCP connection. You end up with two processes writing to the same database connection, which produces either connection state corruption or data interleaving depending on timing. The correct model for Celery with SQL Alchemy is every task creates its own session, scope to the task execution lifetime, and the session is closed within the task before the task returns. No session state crosses task boundaries. If a task needs data from a previous task, it reads it from the database via its own fresh session. It does not pass a loaded ORM object because that object's session reference is from a different process context. Symptom of getting this wrong is subtle. You will see intermittent detached instance error, where SQL Alchemy tells you an object is no longer associated with a session, usually when you try to access a lazy loaded relationship inside a Celery task on an object that was loaded in a different process. That is the tell.
Detached instance error as a diagnostic signal, that is a good call-out. One more deep dive question, and then we go to leadership. This one is about API contract ownership. You lead a team that owns a Django REST framework API consumed by 3 front-end teams, 2 React, 1 mobile. The teams are hitting edge cases with your API serialization, dates coming out as strings in some endpoints and integers in others, nullable versus absent fields being inconsistent, decimal values losing precision after JSON round trip. As a Python principal engineer, how do you own this problem? Not just fix it for today, but establish a process that catches this class of issue before it reaches front-end teams.
The first thing I do is stop treating the serializer layer as an implementation detail and start treating the API contract as a versioned artifact that my team owns. The 3 symptoms you listed, dates as strings in one endpoint and integers in another, nullable versus absent fields, decimal precision loss, those are not 3 bugs. They are 1 bug. The contract lives implicitly inside DRF serializer code, so every engineer who writes a serializer is making contract decisions without realizing they are making them. Immediate fixes first, because the front-end teams are hurting today. Dates get 1 representation everywhere, ISO 86.1 strings with an explicit UTC offset, enforced through a single shared field class that every serializer imports, so nobody handrolls a timestamp again. Decimals never travel as JSON floats. DRF actually gets this right by default. Decimal field serializes to a string, and the precision bugs almost always come from someone overriding that default for convenience or from values bypassing the serializer through a raw query set. So the rule is money and precision sensitive values are strings on the wire, and the front end passes them with a decimal library, not parse float. And on nullable versus absent, I ban absent fields entirely. If a field is part of the contract, it is always present in the response, and if it has no value, it is explicitly null. The moment absent and null both exist, every consumer has to write 2 different existence checks, and no schema diff can tell you whether a missing field is intentional or a regression. Then the process fix, which is the actual answer to your question. The contract becomes a generated OpenAPI schema diapre spectacular from the code committed to the repository as an artifact. CI diffs the schema on every pull request, and any breaking change fails the build unless it is explicitly marked and versioned. The front-end teams generate their typed clients from that schema, so the contract is machine checked on their side too. And we run schemathesis in CI, fuzzing our own implementation against our own published schema that catches the class of bug where the schema says one thing and the serializer does another, which is exactly the class of bug you described. The last piece is organizational. Any contract surprise a front-end team discovers is filed as a backend defect not worked around on the client. Owning the API means the boundary is my problem on both sides of it.
Banning absent fields in favor of explicit nulls. That is a strong structural opinion. I want to hold that thread. Let us move into war stories. Seketh, give me a story where a Python performance problem turned out to be completely invisible to your standard monitoring. No CPU spike, no memory alarm, no error rate increase, and you only found it because you were looking at something else entirely. What was the problem? How did you find it? And what did it change about how you instrument systems?
This happened about 3 years ago on a data export service. The service took a user requested dataset, ran a series of SQL queries, transformed the results in Python, and wrote a CSV or Excel file to S3. Standard batch job type of work. The complaint from users was vague, exports were slow. Not timing out, not erroring, just slow. Latency P50 was fine by our dashboard because the dashboard was showing HTTP response time and the export endpoint returned immediately with a job ID. The actual export ran async. The job completion time was not on any dashboard. I started looking because a user filed a support ticket saying a dataset that used to take 30 seconds now took 8 minutes. That is a 16-index regression with no deployment in between that would explain it. I added timing instrumentation at each stage of the pipeline. The SQL queries were fast, the S3 write was fast. The transformation step iterating over query results and building the output rows was where all the time was going. But it was not constant, it scaled superlinearly with result set size. I profiled it with Profi and found that inside the transformation loop, we were doing a membership check, something like if field unstar name in allowed unstar fields, where allowed unstar fields was a list that was being constructed fresh on every row iteration from a database lookup result that was itself a list of tuples. So every row in a 100,000 row export was doing a linear scan through the allowed fields list. The fix was trivial. Convert the allowed unstar fields list to a set once before the loop and reuse it. 2-line change brought the 8-minute export back to 45 seconds. But the reason I am telling this story is what it changed about our instrumentation. The root cause was that we had zero visibility into job execution time for async work. Request looked instant because we separated submission from execution. What I implemented after this incident was every async job emits a started event with a timestamp and a completed event with a timestamp to a structured log stream, and we have Datadog monitors on the percentile distribution of job duration by job type. If P95 for any job type exceeds a threshold, it fires. That instrumentation has got 3 more performance regressions before any user noticed them.
Superlinear complexity hidden inside a tight loop. And the monitoring was looking at the wrong thing entirely. The job duration instrumentation pattern you described is something more teams should have as a baseline. Second war story. Tell me about a time you had to push back on a technically correct architectural decision that someone above you in the organization wanted to make. Not a wrong decision, a technically correct one that you still pushed back on. What was the decision? What was your argument? And how did it resolve?
About 4 years ago, a new VP of engineering joined, very sharp, and within his first quarter, he proposed decomposing our Django monolith into event-driven microservices with a Kafka backbone. And I want to be precise here because this is the point of the story. His design was technically correct. The bounded contexts were drawn well, the event schemas were thought through, and it genuinely addressed coupling problems that were slowing us down. Standing at the whiteboard, I could not fault the architecture. I tried. I pushed back anyway, and my argument was never about the design. It was about operational capacity. At that point, I had 9 engineers. 2 of them were comfortable being on call for a distributed system. Our observability was single service dashboards, no distributed tracing, no correlation IDs, nothing. And our hiring pipeline was struggling to close senior candidates, which mattered because the plan quietly assumed we could staff up. So the case I made to him was this: the monolith fails in ways this team knows how to debug. Your architecture fails in ways that require competency. We do not currently have partial failures, consumer lag, event ordering, schema evolution across services, and cannot hire fast enough to acquire. You are designing for the team you want. We have to operate it with the team we have. Every architecture decision is secretly also a hiring and training plan, and the plan attached to this design was 18 months long, while the migration itself was scoped at 6. It got tense, honestly. He read it initially as resistance to change. What resolved it was that I did not just say no, I brought a counter proposal. Modular monolith first, enforced module boundaries inside one process, import linting, separate database schemas per module, then extract exactly one service as a pilot, the one with a genuinely different scaling profile, and use that single extraction to build the operational muscle deliberately, tracing, runbooks, on-call rotation training. 2 years later, that system had 4 services, extracted one at a time as the team's competency grew to meet them, and each extraction was boring. The VP told me later that the pushback saved him from his own best idea. The design was right. The organization was not ready to operate it, and those are different questions.
Technically correct versus organizationally appropriate. That is a distinction that does not show up in architecture books. That is experience. Let me pick up one thread from what you just said. You mentioned hiring and team competency. Here is a leadership question I want your honest, specific answer to. How do you detect the difference in a Python interview between a candidate who has memorized patterns and one who can generate them? Because most standard Python interview formats, lead code, DRF design questions, even system design whiteboarding are structurally incapable of making that distinction. What do you actually do differently?
You are right that most formats cannot make that distinction, and I think the reason is that most interview questions have a well-known correct answer that can be found online. If the question has a Google-level answer, you are selecting for people who prepared, not people who can reason. My technique is to take a problem that is close to a known pattern but has a constraint that breaks the standard solution and watch what the candidate does when their prepared answer stops working. Concrete example, I ask candidates to design a rate limiter. Every senior Python engineer has seen this problem. The memorized answer is the sliding window counter with Redis and a Lua script for atomicity. I let them give that answer. Then I add a constraint. Your Redis instance is shared by 5 different services and you cannot use Lua scripts because the security team has disabled eval. What do you do now? The candidate who memorized the pattern is stuck. They know the Lua script is the atomicity mechanism and they do not have a mental model for why it is necessary. They just know the recipe. They will often reach for a Redis pipeline with watch and multi without being able to explain what it actually gives them. Watch is optimistic locking, so it can give you check and set semantics, but only if you wrap it in a retry loop and it degrades badly under contention on a hotkey like a rate limit counter. If they cannot articulate that trade-off, they are reciting a recipe, not reasoning about atomicity. The candidate who understands the problem will say, without atomic read modify write, I have a race condition in the counter increment. I need to think about whether that race condition is tolerable. For a soft rate limiter, approximate counts are acceptable, and I can use INCR with expiry and accept occasional overcounting. For a hard rate limiter where correctness matters, I need a different synchronization mechanism. Maybe a distributed lock with a short TTL, or I push the rate limiter out of Redis and into a service that owns the counter with proper transaction semantics. That reasoning process, identifying the constraint, tracing its implication to the correctness property, evaluating the acceptable approximation, that is what I am looking for. The answer they land on matters less than the path they took to get there. The second thing I do is ask candidates to find the bug in code I wrote, where the bug is in the assumptions, not the syntax. No syntax errors, all tests pass, the logic is internally consistent, but there is an implicit assumption that is wrong in a specific edge case. Engineers who memorized patterns often cannot find it because they are pattern matching to the structure of the code rather than reasoning about its behavior under all inputs.
Deliberately planting a flawed constraint and watching whether they catch it. I have not heard it put that cleanly before. Alright Saket, we are going into the rapid fire round. I am going to give you a question and I want an answer in 60 to 90 seconds, opinionated, specific, no hedging. Ready?
Ready. Let us go.
First one, Python 3.23 ships free credit mode. Part 7.3, the no-GL experiment. A team asked you, should we enable it in our production Django service today? 60 seconds, honest answer.
No, not yet, and not for Django specifically. The reason is not that free-threaded Python is dangerous in principle. It is that Django's ORM and every mature Python web library you are running alongside it was written with the GIL as an implicit thread safety assumption. The GIL serializes access to Python objects, which means library authors did not need to add their own locks around shared state. Remove the GIL and that implicit serialization disappears. Libraries that seemed thread safe because the GIL was doing the work for them will have data races that only show up under genuine concurrent CPU bound load, which is rare in development but happens in production at scale. NumPy has started adding its own thread safety mechanisms. SQL Alchemy is working on it, but the ecosystem is not there yet for a production Django service where you cannot audit every transitive dependency for GIL-dependent assumptions. Enable it in a greenfield service where you control every dependency and you have time to validate each one. Do not enable it in a mature production Django stack without a serious audit.
Second one, TypeScript is increasingly the language of choice for backend as well as frontend. A strong TypeScript engineer on your team argues that Python's type system, even with MyPy and strict mode, is fundamentally weaker than TypeScript's because it is gradual and the runtime does not enforce it. Is he right? And does it matter?
He's right on the narrow claim and mostly wrong on the conclusion. Yes, TypeScript's type system is more expressive, discriminated unions, structural typing designed in from day one, and the compiler is unavoidable in the word chain, whereas MyPy is opt-in and gradual. All true. But here is what the argument misses. TypeScript's types are also erased at runtime. A TypeScript backend receiving JSON off the wire has exactly the same problem a Python backend has. The type system tells you nothing about that data until you validate it, which is why serious TypeScript backends run served at the boundary and serious Python backends run Pydantic. Both ecosystems converged on the same answer: static types inside the process, runtime validation at the edges, and Pydantic is arguably the more mature half of that comparison. So does it matter? What actually matters is discipline, not the tool. A Python codebase on strict MyPy with validated boundaries and no, any leakage is safer than a TypeScript codebase with any sprinkled everywhere, and I've seen plenty of both. The type system is not the guarantee. The discipline is.
Third one. Most experienced Python engineers have a hot take about the standard library. What is the one standard library module that you think is actively harmful to put in production code, and what do you use instead?
Threading. Thread with shared mutable state and no synchronization primitive. It is not the module itself. Thread is fine. It is the pattern that the standard library documentation actively shows. Start a thread, share a list between threads, use it without a lock. That example in the docs has caused more subtle data corruption bugs in production Python code than I care to count, because Python programmers see it, copy it, and assume the GIL means they are safe. The GIL does not protect compound operations. Appending to a list from two threads simultaneously is safe. But read, check, then modify is not. The documentation does not make this distinction clearly enough. What I use instead for actual concurrent work, concurrent.futures thread pool executor for ISON for I-bound parallelism with explicit result collection, or multiprocessing for CPU-bound work, both force you to think about data passing rather than state sharing, which is the correct mental model.
Fourth one, Pydantic v2 introduced significant breaking changes when it rewrote the code in Rust. Your team is still on Pydantic v1 in a service that does heavy serialization work. A junior engineer asks, should we upgrade? What is your one-sentence answer to them? And what is the longer answer you give when they push back?
One sentence answer, yes, but schedule it as a project, not a sprint task, and do it on a quiet week. Longer answer when they push back, the migration is real work, v2 changed validator syntax, field declarations, and the model configuration interface in ways that require touching every model. But the case for doing it is not just performance, though the Rust core is genuinely faster and that matters in heavy serialization workloads. The case is ecosystem drift. The Python ecosystem is moving to V2. FastAPI, LangChain, and most modern libraries now assume V2 semantics. Every month you stay on V1, the number of libraries you cannot use without compatibility shims grows. The migration cost is known and bounded. The compatibility debt compounds. My advice to the junior engineer: write a one-pager that estimates the number of models in the codebase, the complexity of the validators, and the test coverage. Bring that to the team planning session. Do not do it guerrilla style in a feature branch. Do it as a dedicated migration with its own acceptance criteria.
Fifth one, this is a Python-specific algorithms question. You have two implementations of the same algorithm, finding all unique pairs in a list that sum to a target. Implementation A is a nested loop O of n squared, pure Python. Implementation B is a set-based approach, O of n, pure Python. At what input size does implementation B actually start winning in wall clock time on CPython? And what does that say about how you think about BGO in Python specifically?
The crossover point depends on the constant factor difference between the two implementations. The set-based approach has a higher constant factor per element, set construction cost, memory allocation, hash computation per insert, and there is interpreter overhead for each set lookup. The nested loop has a simpler inner loop in terms of Python object operations but quadratic growth. In practice on CPython for small lists below roughly 200 elements, the nested loop often wins or is competitive because the constant factor overhead of the set operations dominates. Around 500 to 1000 elements, the O of n set approach starts pulling ahead clearly. By 10,000 elements, the set approach is not even close. But here is the thing that BGO does not tell you. If your input is reliably small, say always under 100 elements, because it is a user input that is validated upstream, the nested loop in pure Python may be the right production answer because it has less code, no set construction overhead, and is trivially retrievable. BGO is a limit analysis for large n. If your n is bounded and small, you are not operating in the regime where BGO dominates. The even more important version of this, if you can express the problem as a NumPy vectorized operation, you skip the Python interpreter overhead entirely for the inner loop and you will beat both implementations by an order of magnitude for any n above a few hundred. The constant factor for Python interpreter overhead versus a compile C loop is not 2 or 3 times, it is hundreds of times. So sometimes the theoretically worse BGO algorithm in NumPy beats the theoretically optimal algorithm in pure Python by a factor of 50 at your actual production data size.
Excellent. NumPy constant factor wins over BGO optimality in pure Python. That is a nuance that trips up a lot of people who learned algorithms in a language agnostic context. Last rapid fire. This is a leadership and hiring opinion question. You are building a Python engineering team from scratch. You have headcount for 5 engineers. You can only pick from these 3 profiles. Pick 2. Profile A, a Python generalist with 12 years of experience who has deep expertise in exactly one web framework. Profile B, a polyglot engineer with 7 years of experience who is excellent at systems thinking but has only been writing Python for 2 years. Profile C, a Python specialist with 4 years of experience but who has contributed to CPython, understands the runtime deeply, and has a track record of excellent technical writing. Which 2 do you hire and why?
B and C. And I want to explain why I am leaving A on the table because that is probably the surprising choice. I am leaving A behind because deep expertise in one framework over 12 years is a signal of comfort with a local maximum. 12 years of Python is only valuable if that experience compounded across different problem types, different scales, different failure modes. If someone with 12 years of Python has stayed in one framework, I have to bet on whether the learning compounds or just repeats. That bet is uncertain. C, I hire immediately. Someone who has contributed to CPython has demonstrated 3 things I cannot easily hire for: They understand the runtime at a level that makes them dangerous when debugging subtle performance or correctness issues. They have navigated a demanding open source review process that selects for communication and correctness simultaneously, and the technical writing track record means they will document what they know and scale their expertise across the team. BI hire because polyglot systems thinkers are the engineers who are most likely to transfer patterns across problem domains. They are the ones who will suggest that your rate limiter design is actually a token bucket, not a sliding window, because they have seen that pattern in a network routing context in another language. 2 years of Python with excellent system thinking is a 6-month ramp. Deep Python knowledge without systems thinking is much harder to remediate.
That is a bold call, and I think it is the right one. Saket, let us start bringing this home. We have been going hard for 45 minutes, testing architecture, salary correctness under partitions, supply chain security, SQL alchemy, transaction semantics, API contract ownership, and hiring signal calibration. If you had to name the single sharpest edge in Python engineering in 2026, the thing that separates the engineers who are good from the engineers who are principal level, what is it?
Failure surface reasoning. The ability to look at any system, a piece of code, an architecture diagram, a deployment configuration, and enumerate the ways it fails, the conditions under which those failures are silent versus loud, and whether the failures are recoverable within the system or require human intervention. Good engineers make systems that work. Principal engineers make systems where the failure modes are legible. Those are different things. A system that works but fails opaquely is more dangerous in production than a system with more known failure modes that are all visible and recoverable. Every answer I gave today comes back to that. The 2 a.m. stranger test for code review, can they find the failure? The mutation testing discussion, are your tests catching behavioral failures or just checking that code ran? The salary partition question, which failures does salary give you visibility into and which are silent? The API contract question, when front-end teams hit serialization edge cases, is the failure visible at the backend boundary or does it silently corrupt data on the client? The principal level engineers I respect most have a habit that the good but not great engineers do not. They are never satisfied with a system that works. They keep asking, when it stops working, will we know? Will we be able to fix it? Will the blast radius be bounded? Until those answers are yes, they do not sign off on the design. That is the edge. Not more Python knowledge, that reasoning habit.
Failure surface reasoning as the defining trait of principal level engineering. That is a clean thesis, and I think it will land for people listening. Saket, one final question before I let you go, and this is the personal one. You have 14 years, you are actively interviewing. What is the one thing about your own engineering that you are still working on? Not a weakness you have rehearsed for HR, a genuine current work in progress.
Letting go of implementation details earlier in design conversations. I have a habit, and I know it is a habit, of jumping into implementation specifics before the problem space is fully explored. Someone proposes a design and I am 3 layers deep in how we would implement the retree logic before I have asked whether we have validated that the retree is the right solution to the user problem. At the lead and principal level, that habit is counterproductive. My job in a design conversation is to expand the problem space before we collapse it into a solution, and my instinct as a programmer is to collapse it immediately because that is what gets reinforced over years of writing code. Every time I write a function, I make it concrete. That is the skill. But in architecture and leadership, staying abstract longer is the skill, and I am consciously working against my trained instinct every single day. I catch myself doing it and I have gotten better. But I would not say it is solved.
That is a genuinely honest answer, and I think a lot of senior engineers are going to hear that and recognize themselves. Saket, this was excellent. Genuinely strong performance across the board. The salary partition deep dive was the highlight for me, and the hiding signal question answer was unusually clear. I hope the companies you are talking to are listening to this episode and making the call. Thank you for coming on and letting us do this properly.
Thank you, Balu. This was the most useful 45 minutes of interview prep I could have done. I appreciate the team at Kritia AI Labs for building this kind of resource. I genuinely mean that. There is nothing like this for senior Python engineers who want to stress test their thinking before a real process. For anyone listening who is at the senior or staff level and preparing to interview, record yourself answering these questions. You will find gaps you did not know you had.
Welcome back to the Kritia AI Labs Tech Interview Series, the show where engineers grow, learn, and get hired. I am Balu, Senior Technical Architect at Kritia AI Labs, and if you are watching or listening to this for the first time, what we do here is simple. We run real unscripted mock interviews at the level of difficulty you will actually face when you are interviewing for staff or principal engineering roles at product companies. No softballs, no textbook answers accepted. Today's episode is one I have been genuinely looking forward to because our guest sits in a very specific and interesting position. He has 15 years of Python engineering behind him, not 15 years of writing scripts, 15 years of owning systems, making architecture decisions stick, and cleaning up the messes that follow when they do not. Is actively looking for his next move, and he agreed to do this live on the show. We are going to go deep today. We are talking Python runtime internals, the parts that do not show up in documentation. We are talking distributed system correctness, the failure windows that your architecture diagrams do not draw. We are talking about what it actually means to operate as a staff engineer inside an organization, not just write good code. And we are going to dig into a few war stories from production because that is where the real learning lives. 15 years, staff level, job change. Let us see what we find. Stay with me. Alright, let me bring in my guest, Saketh. Welcome to the show. Really glad you said yes to this.
Thanks, Balu. I appreciate the invitation, and I will be honest, I am a little nervous, which is the point, right? That is the whole idea of doing this live.
That is exactly the point. Nows are information. They tell you which questions you have not thought carefully enough about. Alright, let us not waste time. Let us get into it. Sekar, before I get into the technical questions, I want to ask you something that sounds simple but rarely is. You have 15 years in Python. That is a long time to stay committed to a single ecosystem. At some point in the last 5 years, there were real conversations in the industry about whether Python was the right choice for high throughput backend systems. People moving to Go, people moving to Rust for performance critical paths. What was the moment, if there was one, where you had to genuinely defend Python as a choice and not just default to it because it was what you knew?
Yeah, that is a good framing because you are right. There is a version of that question where the answer is just inertia, and I want to be honest about where the line is. The moment that stands out for me was about 4 years ago. We were running a data pipeline service, ingestion, transformation, some light ML feature computation, and we were hitting latency walls. P99 was bad. The instinct on the team, and I had it too initially, was Python is the bottleneck. We should rewrite in Go. And we had a Go engineer on the team who was very enthusiastic about this idea. I spent 2 weeks going deep on the profiling before I was willing to have that conversation seriously. And what I found was that the latency was almost entirely in two places. One was network I saw that was synchronous when it should have been async, and the other was a transformation step that was doing pure Python loops over large lists when it should have been a vectorized NumPy operation. Neither of those is a Python problem. Both of them are a Python expertise problem. We moved the IO to asyncio, we rewrote the hot loop in NumPy, and our P99 dropped by 60% without touching the language. That is when I became much more deliberate about the defense. Python is not slow. Python written by engineers who do not understand its performance model is slow. Those are different diagnoses with different solutions. Now, is there a category of problem where I would genuinely reach for Go or Rust? Yes. If you are writing a high throughput, low latency network proxy where you need deterministic sub-millisecond response times and you cannot afford GC poses, Python is the wrong tool. But that was not what we had. And I think the discipline is in making that determination based on profiling data, not based on what is trending on Hack News.
I love that framing Python expertise problem versus Python language problem. That distinction does a lot of work, and it actually sets up my next warm-up question nicely because I want to stay on the expertise angle but go somewhere specific. Here is a scenario that surprises a lot of experienced engineers. You have a long-running FastAPI service. It has been running for 6 days. You look at RSS in your container metrics and it has grown from 138 megabytes to 340 megabytes. You attach PySpy and the flame graph looks completely normal. No hot loops, no obvious leaks. You run tracymalloc and the top allocations are tiny and stable. The process looks healthy by every Python level metric. What is your mental model for where that memory actually went? And what would you do next?
Okay, so the key detail here is that tracymalloc shows nothing interesting but RSS is growing. That asymmetry is the diagnostic clue and it points you away from application level allocation and toward the allocator itself. Python uses its own memory allocator called pymalloc for objects under 500 bytes, which is most Python objects. Pymalloc works by allocating memory from the OS in arenas, 256 kilobytes historically, 1 megabyte on recent Python versions. Within those arenas, it carves out pools and within pools, it carves out blocks. The critical behavior is this: pymalloc will never return an arena to the OS as long as any single object in that arena is still live. So, if you have an arena where almost every object has been freed but one tiny object, maybe a cached string, maybe an interned symbol, is still alive, that entire arena stays resident. The OS sees the full arena as committed memory. tracymalloc sees almost nothing. Because from Python's perspective, those freed slots are available for use, so it does not report them as allocated. Over 6 days of request processing with allocation patterns that vary, big requests, small requests, different object sizes, you end up with fragmentation across hundreds of arenas, each partially full, none of which can be returned to the OS. RSS grows. Python's view of memory is fine. That is the disconnect you are seeing. Now, how do I confirm this? tracymalloc and PySpy are the wrong tools here, as you noted. I would reach for memory. Memory gives you native level allocation traces, including the allocator zone overhead, which tracymalloc structurally cannot see because tracymalloc hooks into Python's object allocation layer, not into the cmalloc calls that pymalloc itself makes. With memory, I can see the actual arena allocation pattern. I would also try running this service with the python malloc environment variable set to malloc set in the environment, which bypasses pymalloc entirely and uses the system malloc entirely. If RSS growth stops or significantly reduces under that configuration, you have confirmed that pymalloc fragmentation is the source. If it continues, you have a different problem, possibly a native extension that is doing its own allocation, and then there is the GC angle. Python's cyclic garbage collector handles reference cycles that the reference counting mechanism cannot collect. If your request handling is creating cycles, which is easy to do accidentally with closures, with event handlers with certain ORM patterns, and those cycles are surviving into generation 2 of the GC before being collected, you get long-lived arena residency that compounds the fragmentation.
That is exactly the right model. Let me push on one specific thing you said. You mentioned the pymalloc environment variable set to malloc as a diagnostic step. If you do that experiment and you confirm it is pymalloc fragmentation, not a leak, not a bug in application code, how do you explain to your engineering manager why you cannot quote-unquote fix it, and what operational mitigation do you actually ship?
The conversation with the engineering manager is actually where a lot of engineers stumble, because the instinct is to feel like you have failed if you cannot eliminate the symptom. The honest framing is this is not a bug, it is a characteristic of the allocator. The memory is not lost, it is fragmented, and the distinction matters because the mitigation is operational, not a code fix. What I would explain is pymalloc is a performance optimization. It makes Python object allocation very fast by pulling small allocations. The cost of that optimization is that memory is held in arenas that cannot be partially returned to the OS. For a long-running service with varied allocation patterns, fragmentation accumulates. This is a known documented characteristic, not something we introduced. The operational mitigations I would actually ship, roughly in order of complexity. First, periodic worker recycling. In Gunicorn, you have max request, and max request does jitter. Set a reasonable ceiling, say 10,000 requests per worker, and the worker process is restarted, which hands all arenas back to the OS. This is already a best practice for other reasons. It bounds the blast radius of memory leaks in third-party extensions. It prevents slow accumulation of connection state. Framing it to the manager as a memory hygiene strategy rather than a fix for a bug is accurate and defensible. Second, if we are on Kubernetes, memory limit headroom. If the container memory limit is set at 512 megabytes and we know fragmentation can push RSS to 400 megabytes under normal operation, the limit is too tight. We adjust the limit with informed headroom rather than treating every RSS increase as a fire. Third, if we want to reduce fragmentation without worker recycling, we can look at dmalloc or tsendmalloc as drop-in malloc replacements via LDD tools pbdlld. Both have better fragmentation characteristics than pymalloc for certain allocation patterns, and both have production usage in large Python deployments. That is a more invasive change and I would benchmark it carefully, but it is on the table.
Max request with jitter, informed memory headroom, gmalloc as an option. That is a real engineering answer, not a hand wave. Alright, I want to keep moving because we have a lot of ground to cover today. Let me ask you one more warm-up before we go into the deep technical material. This one is about the job change itself. You have 15 years in. You are not leaving because things are bad. Or maybe you are. But I want to understand the actual reasoning. What is the thing you are optimizing for in your next role that your current situation is not giving you? Be specific.
I appreciate you asking that directly because the diplomatic answer and the true answer are different. And I think the true answer is more useful. The honest answer is scope of consequence. I have been in an organization where the engineering problems I am solving are interesting, but the decisions I make affect maybe 30 engineers and one product line. I have reached the point in my career where I want to see how my architectural decisions behave at a scale where the failure modes are genuinely surprising, where the system has emergent behaviors that I did not predict and I have to reason my way through them under real pressure. That sounds abstract, so let me make it concrete. In my current role, when I make a call about how we handle idempotency in our payment pipeline, I can validate that decision within a week because the traffic volume is manageable. At the kind of scale I am looking for next, something processing millions of events per day across multiple regions, that same decision has failure modes I will not see in staging, I will not see in the first week of production, I will only see at 3 in the morning 6 weeks in when some edge case in the timing assumptions surfaces. I want that problem. I want to be forced to think at that level of precision before I ship because I know I am not doing that now. The secondary thing is team multiplier work. I want to operate in a context where my output is primarily measured by what I enable other engineers to build, not by what I build directly. I have a lot of craft around system design, around code review, around architecture decision governance, and in my current role, I do not have the team size or the organizational structure to really exercise that. I want that leverage.
Scope of consequence and team multiplier work. Those are crisp. That is a well-articulated reason for a job change that does not sound like a complaint and does not sound rehearsed. Alright, let us go into the deep technical material. I am going to start working you hard now. Okay, here is the scenario. You are reviewing an architecture for a fintech service. A payment is processed by writing to Postgres and then publishing an event to Kafka to trigger downstream accounting, notifications, and audit logging. The team has implemented this as commit the Postgres transaction, then produce to Kafka in the same request handler. A senior engineer on the review says, quote, "This is fine because we have Kafka producer retries configured. What do you say in that architecture review? And what do you actually ask them to build instead?"
The senior engineer is solving for a retrieve window, but they are not solving for the fundamental atomicity problem, and those are different things. Here is the specific failure window they are leaving open. The Postgres transaction commits successfully. The payment record is in the database. Now the application attempts to produce to Kafka. Between those two events, the process can die, not crash die. A seed kill from the container orchestrator, a power event on the host, an ohm kill. At that point, you have a committed payment in Postgres with no corresponding Kafka event. Kafka producer retries are a client-side mechanism. They only help you if the process is still alive to execute the retry. A dead process cannot retry anything. Producer retries also do not help you with a different failure mode. The Kafka broker is unavailable at the moment of the produce call. The retry backoff exhausts within the HTTP request timeout, and the request handler returns a 500 to the client. The client replies the payment. Now you potentially have two payment records in Postgres and 0 or 1 Kafka events depending on which attempt produced. You have introduced a duplicate payment risk. So what do I ask them to build instead? The outbox pattern, but I want to be precise about the implementation because the naive description of the outbox pattern has its own failure modes. The correct implementation is within the same Postgres transaction that writes the payment record, also write a row to an outbox table. One atomic transaction, payment row committed, outbox row committed, or neither. Then a separate process, a dedicated outbox relay, not the request handler, reads unprocessed outbox rows, produces to Kafka, and marks the outbox row as processed only after receiving acknowledgement from Kafka with AXX XOR. The subtlety is in the relay's read query. If you select outbox rows without proper ordering and locking, you can publish events out of order, or you can have multiple relay instances publish the same event concurrently before either has marked it processed. You need to either use select format need skip law to claim rows for processing, or use a cursor-based approach with a processed at timestamp and idempotency key on the Kafka message so that duplicate publications are handled on the consumer side. I would also push them on the consumer side. The downstream services need to be idempotent receivers. The outbox pattern guarantees at least once delivery, not exactly once. That is a separate design constraint that needs to be explicit.
You mentioned select for opti skip locked as the row claiming mechanism. Walk me through the specific failure mode you get if the outbox relay crashes after it has claimed a row with FOR optis but before it has produced to Kafka and committed the processed status. How does the system recover, and what is the worst case latency on that recovery?
Good push. This is exactly the edge case that bites people. Select for umptit acquires a row level lock within a transaction. If the relay process crashes, not a graceful shutdown, a hard crash, the Postgres transaction is never committed, so the lock is released automatically when the connection drops. The row goes back to its unprocessed state and becomes visible to the next relay instance that runs the query. So far so good, that is the recovery path. The worst case latency is how long until the next relay poll cycle runs and how long until the crashed relay's connection is detected as dead by Postgres. If your relay polls every 5 seconds and the TCP keep a leave timeout is set to the default, which on many Linux configurations is 2 hours, you could theoretically have the lock held for 2 hours on a connection that is actually dead. In practice, you mitigate this with aggressive TCP keep a leave settings on the database connection in your relay process and with a statement timeout or lock timeout configured at the Postgres session level. The practical mitigation I would ship is set TCP uncircumcised status idle to something like 30 seconds on the relay's database connection and set a lock threshold at the session level, say 10 seconds, so that if a lock cannot be acquired within 10 seconds, the relay backs off and retries. Combined with a relay poll interval of a few seconds, your worst case recovery latency is in the range of tens of seconds, not hours. There is also the question of what happens if the relay successfully produces to Kafka, gets an ACK, but then crashes before it commits the process status in Postgres. Now the event has been published to Kafka, but the outbox row is still marked unprocessed. The next relay run will publish it again. This is the at least once delivery guarantee I mentioned. It is not a bug, it is a contract, but it means every downstream consumer must handle duplicate events, and that needs to be a design requirement that is documented and enforced, not an assumption.
At least once as a documented contract, not an assumption. I want to file that away because it comes up again later. Let me shift gears to testing, but I want to go somewhere specific that is not the standard testing conversation. You are onboarding a new senior engineer onto a fintech service you own. On day 3, they come to you and say, the test suite has 1,400 tests and it gives me confidence in nothing. I can break the payment flow in 5 obvious ways and all 1,400 tests still pass. Walk me through how you would diagnose that problem and what you would actually do about it in that specific service. Not theoretically.
The engineer is describing a specific and important failure mode, high test count, low behavior coverage. Those are different axes, and conflating them is how you end up with 400 tests that catch nothing. My diagnostic process starts with a question: what are the tests actually asserting on? In my experience, when tests feel hollow, it is usually one of 3 patterns. The first is implementation coupling test that assert a function was called rather than that the right outcome was produced. Something like mock the payment processor, assert mock.process was called once. That test passes whether the payment logic is correct or completely broken as long as the function call happens. This is the most common failure mode I see in Python codebases where mocking is overused. The second is over-mocking at the wrong boundary. In a payment service, if you are mocking your SQL Alchemy session at the unit test level, your tests are not testing any of the data persistence logic. They are testing that your application code calls the right methods in the right order on an object that behaves nothing like a real database, move the mock boundary outward, test against a real Postgres instance in a Docker container, and suddenly a whole class of bugs becomes visible. The third is happy path fixture dominance. Your test fixtures set up ideal state, a customer with a valid card, a payment method that is not expired, an account with positive balance, and every test runs in that world. The payment flow breaking in 5 obvious ways suggests those obvious ways are error paths, edge cases, boundary conditions that the fixtures are systematically excluding. Now, how do I confirm which of these is the actual problem? I would run a one-time mutation testing diagnostic on the payment module, mute as a survey, not as a permanent CI step. The surviving mutants are empirical evidence. They point at exactly which logic those 1,400 tests are not actually exercising, and in my experience they cluster around one of the 3 patterns I just described, which tells you where to start the remediation. The fix is not to write more tests. It is to write better assertions, push mock boundaries outward, and introduce at least a few integration tests that exercise the actual payment flow against real infrastructure. Confidence does not come from count, it comes from the assertions being about outcomes that matter.
You mentioned a new senior engineer suggesting replacing all the mocked unit tests with integration tests against a real Postgres container. What is your actual response to that? Not the diplomatic one, the technical one.
The technical response is partially right, and the part that is wrong is important. They are right that unit tests with deeply mocked infrastructure do not test the right things. Moving integration test against a real Postgres container into your suite catches a whole class of bugs: ORM query correctness, constraint violations, transaction boundary behavior that mock unit test structurally cannot catch. I agree with the direction, but replacing all unit tests with integration test is not the right shape. Here is why. Integration tests are slow, they require external dependencies to be available, they have setup and teardown costs, and they fail for environmental reasons that have nothing to do with your code. If every test in your suite is an integration test, your CI pipeline becomes slow and fragile. Engineers start running tests less frequently because the feedback loop is too long. That is a worse outcome than the one you started with. The correct shape is use integration tests for the paths where the integration is the thing that can go wrong: database query correctness, constraint enforcement, actual HTTP response parsing from a real downstream service. Use unit tests for the paths where the logic is the thing that can go wrong: fee calculation rules, eligibility checks, state machine transitions, but write those unit tests with assertions on outcomes, not on call patterns. So my response to the senior engineer is yes to more integration test, no to wholesale replacement. Let us be deliberate about which layer catches which class of bug. And let us instrument the test suite so we know which tests are slow, which tests are flaky, and what the actual coverage of each layer is, so that this conversation is grounded in data next time, not intuition.
That is a mature answer. Let me go somewhere different now: security. I want to test a specific scenario. You have a Django REST API that accepts a JSON body from clients. One of the fields is a metadata field free form baked, stored as JSONB in Postgres, returned as is on read. Your security team flags this as a risk. A junior engineer on your team says, "It is fine, we are using DRF serializers and the data is stored as JSON. There is no SQL injection possible here." Is the junior engineer right? What are the actual attack surfaces in this pattern and what controls do you put on it?
The junior engineer is correct about SQL injection but has a much too narrow view of what the attack surface is. Being safe from SQL injection does not mean being safe. Let me walk through the attack surfaces I actually see here. First, stored XSS. If that metadata field is ever rendered in a front end, an admin dashboard, a customer-facing UI, an email template, without explicit sanitization, an attacker can store a JavaScript payload in a metadata key today and have it execute in a user's browser 6 months from now when someone loads the relevant page. This is a backend concern because the payload enters through the backend and the backend is responsible for either sanitizing it on write or flagging it as untrusted data that requires encoding on read. DRF serializers do nothing about this. Second, JSONB query injection via dynamic ORM filter construction. This is the subtle one. If your application ever does something like filtering on a user's supplied key within the metadata, even as an internal admin tool, and that filter is constructed dynamically, you have an injection surface. Django's ORM does not protect you if you are constructing the filter keyword argument from user input because the keyword argument is the attack surface, not the value. Something like filter with a dynamically built key referencing metadata double underscore and a user supplied field name, the ORM will execute whatever lookup that resolves to, including lookups that trigger expensive operations or expose information about your data model through error messages. Third, denial of service via nested structure complexity. JSON parsers are recursive by nature. A deeply nested JSON object, 100 levels of nesting, can exhaust call stack depth in a parcel or consume disproportionate CPU time during deserialization. This is the structural equivalent of a billion laughs attack in XML. DRF's JSON parser has no depth limit by default. A single malformed request can spike your worker CPU. Fourth, unbounded storage. If there is no size limit on the metadata field, a client can send a multi-megabyte JSON blob. Across many requests, this becomes a storage cost issue and potentially a retrieval latency issue if those JSONB fields end up in queries that scan them. The controls I ship, schema enforcement at the serializer level, even for a quote-unquote free-form field, enforce maximum depth, maximum total size in bytes, and where possible an allowlist of top-level key names. If the business requirement is genuinely arbitrary keys, enforce that the keys are alphanumeric with bounded length. Rate limit write operations to endpoints that accept metadata. Never construct dynamic ORM queries from user-supplied metadata keys without explicit validation that the key exists in an allow list. And document in your API contract that metadata values are stored and returned as OP data. Responsibility for sanitization on render is on the consumer.
The dynamic ORM filter construction angle is the one I wanted you to get to. Let me make it more concrete. Your JSON-B field ends up being queried with something like myModelObjects.filter with a dynamically built key, essentially f-string metadata, _user-supplied key equals value. Walk me through exactly what the attack surface is there and how Django's ORM does or does not protect you.
Right. So the Django ORM's lookup resolution works like this. It takes a keyword argument like metadata, some key, some transform, and it passes that string to determine which field, which JSON path, and which lookup type to apply. The protection Django gives you is against value injection. The value on the right side of the equals is properly parameterized in the SQL query. You cannot inject SQL through the value, but the keyword argument key is not parameterized. It is resolved at the Python level into a SQL fragment. So if the key portion of that f string contains a double underscore followed by a valid Django lookup name like I contains or regex or in, the ORM will happily apply that lookup. An attacker who knows or can guess Django's lookup names can influence the type of query being executed. A regex lookup against a large table with a complex regular expression is a reader's vector, regular expression denial of service, and in lookup with a large list is a different performance attack. More broadly, if the user supplied key results in a key path that resolves to a different field than intended, if there is any way to traverse the double underscore separator into a field other than metadata, you have exposed query structure that the attacker can use to probe your data model. Even if the data returned is empty or raises an error, the error response time difference is an oracle. What Django does not give you is any protection against key-level injection because it was not designed with that threat model in mind. The protection has to be yours. Validate that the user-supplied key is in an explicit allowlist before you construct the filter keyword. No allowlist membership, no query construction, full stop. This is not Django's job to fix, it is the application's job to not hand user input directly to the ORM's lookup resolution machinery.
Lead us via ORM lookup type control. That is a specific and underappreciated attack vector. Good. Let me shift to something more architectural now. Here is a scenario about idempotency, but I want to go beyond the standard definition. You are designing an idempotency key scheme for a payment processing API. The API is consumed by mobile clients, third-party integrators, and your own internal services. The idempotency key needs to survive 3 simultaneous pleasures: replay attacks from malicious clients who are deliberately resending old idempotency keys with different payloads, clock skew across distributed consumers that may be several seconds off from each other, and consumer restarts where a service comes back up and replaces its in-flight request queue from a checkpoint. Design the key scheme. Tell me every decision you are making and why.
This is a constraint satisfaction problem, and I want to be explicit about which constraints are in tension with each other before I design anything, because the tensions determine the trade-offs. The replay attack constraint wants idempotency keys to be bound to a specific payload so that the same key with a different payload is rejected. The consumer restart constraint wants idempotency keys to be replayable so that a service coming back up can resubmit the same key and the same payload and get the same result. Those two constraints pull in the same direction. Actually, both want key plus payload binding. The clock skew constraint wants the system to not rely on timestamps as the primary uniqueness signal. Because timestamps from different locks are unreliable for ordering, here is the scheme I would design. The idempotency key structure has 3 components. First, a client-generated UUID version for fully random, no timestamp component. This is the primary uniqueness identifier. It is the client's responsibility to generate this and to persist it before making the request so that on retry after a crash, the client sends the same UUID. This is the standard part. Second, a payload hash. On receipt, we compute a deterministic hash of the request payload, Chemistry 256 of the canonical JSON representation with a server-side key and store it alongside the idempotency key record. On a subsequent request with the same idempotency key, we recompute the hash and compare. If the hash does not match, We reject with a for 222 same key, different payload. This is a protocol violation. This handles the replay attack where a malicious client tries to reuse a legitimate idempotency key from a previous transaction with a different payment amount. Third, an expiry window. Idempotency keys expire after a bounded window, let us say 24 hours for a payment API. After expiry, the key is tombstoned. It is kept in the records as expired, not deleted, so that a late replay of a legitimately old key is rejected with an explicit expired response rather than silently processed as a new payment. Tombstoning rather than deleting is important for auditability. For clock skew, we do not use client-supplied timestamps for anything in the idempotency logic. The timestamp on the idempotency key record is set by the server on first receipt. Client clocks are informational at most. This eliminates the skew problem entirely by not depending on distributed clocks for correctness. For consumer list starts and checkpoint replay, internal services generating idempotency keys for their own request should derive the key deterministically from the operation identity. For example, HMIC of the order ID plus the operation type plus the idempotent sequence number for that operation. This ensures that after a restart and checkpoint replay, the internal service generates the same idempotency key for the same logical operation and the payment service correctly deduplicates it. The key is that the key generation is a pure function of the operation's logical identity, not a fall clock time or random state that is lost on restart. The storage backend for idempotency's key records needs to be strongly consistent. Redis with AOF persistence and a single write policy works, but I prefer a dedicated Postgres table with a unique index on the key because Postgres gives you atomic insert or select semantics that Redis requires you to implement manually with Lua scripts, and in a fintech context, I want the idempotency transactional store as the payment record in the same transactional store as the payment record where possible.
Tombstoning instead of deletion for auditability. Key derivation as a pure function for internal services. These are the details that separate a design from a real implementation. I want to pivot now to something that does not get enough airtime in staff-level conversations, the asyncio cost model. Here is the setup. Your team is building a data enrichment pipeline in Python. They use asyncio.gather to fire off thousands of coroutines concurrently, say 2000 API calls to an external enrichment service. In testing with 100 concurrent calls, it is fast. In production with 2000, it is unexpectedly slow, not because the external service is slow, that is confirmed, but the Python process itself is spending significant CPU time in scheduling overhead. Walk me through what is actually happening inside the asyncio event loop at that scale and how you would redesign the pipeline.
This is one of those places where big O analysis gives you a false sense of safety and you need to understand the constant factors. When you call asyncio.gather with 2000 coroutines, what happens is all 2000 coroutines are created and scheduled as tasks on the event loop immediately. The event loop's ready queue, the DQ of callbacks waiting to be executed, suddenly has 2000 entries. Each iteration of the event loop processes the ready queue, runs the callbacks, calls into the i/2 to check for i/u completion events, and then processes any newly ready callbacks. With 2000 tasks all starting simultaneously, the initial burst of scheduling, dropping each coroutine in a task object, adding it to the ready queue, executing the first step of each coroutine until the first await is O in task count. That initial burst alone can be tens of milliseconds on CPython for 2000 tasks, because task creation involves Python object allocation, internal bookkeeping in the event loops task registry, and the first execution step. But the more insidious problem is what happens as the I/O completions come back. If the external service is fast and 2000 completions arrive close together in the same select poll interval, the event loop will resume all 2000 coroutines in rapid succession. Each resumption is a context switch at the Python level, restoring the frame, executing until the next await or return, scheduling any downstream tasks. With 2000 concurrent resumptions arriving at similar times, you get thundering herd behavior inside the event loop, a burst of Python execution that saturates the event loop tick and creates visible latency spikes. The fix has two parts. First, replace asyncio.gather of 2000 tasks with a bounded concurrency pattern. Asyncio.semaphore with a limit of say 50 allows at most 50 concurrent coroutines to be in flight at any time. The rest wait on the semaphore, which is lightweight. They are not actively executing, just waiting for the semaphore to be released. This reduces the scheduling pressure from 2000 simultaneous tasks to 50, which is within the event loop's comfortable operating range. Second, if you genuinely need high throughput rather than just high concurrency, consider whether Asyncio is the right tool for this stage of the pipeline at all. A pattern I have used is a producer-consumer architecture with Asyncio to queue with a bounded max size, a small pool of worker coroutines, again 50 or so, pull items from the queue and process them. The input generation side can produce items as fast as it wants, but the consumer side is naturally bounded. The queue's max size creates back pressure. If the consumers cannot keep up, the producers block on put until space is available, which is exactly the behavior you want in a pipeline. The broader principle is Asyncio is cooperative, not preemptive. 2000 tasks that all become runnable simultaneously are not 2000 parallel workers. They are 2000 pieces of work that the single event loop thread has to context switch between. Designing for bounded concurrency is not pessimistic, it is realistic about what the event loop scheduler can efficiently handle.
Bounded semaphore or producer consumer with queue max size versus raw gather at scale. That is the right model. Let me ask you one more deep dive question before we go into war stories. This one is about the staff engineering work, not the code. You have a team of 12 engineers. You introduce architecture decision records as a practice. 6 months later, you review the ADR repository and you find that engineers are writing ADRs after decisions have already been made and implemented. They are being used as post hoc documentation, not as a decision-making tool. The format is beautiful, the content is technically sound, but the process is decorative. How did that happen? And more importantly, what is the governance mechanism that makes ADRs binding rather than decorative?
This is a systems thinking question, and I appreciate that framing because it is exactly how I think about it. How did it happen? The most common failure mode is that ADRs were introduced as a documentation practice without changing the decision-making process. Engineers are already making decisions in Slack, in design meetings, in pull request comments. The ADR becomes an additional artifact that has to be created, and because it comes after the real decision was made, it is written in defense of a conclusion rather than as an exploration of options. The incentive structure is wrong. Engineers are rewarded for shipping, not for the quality of their decision process. Writing an ADR that challenges a decision that is already being implemented feels like friction, not value. The second failure mode is that there is no cost to ignoring the ADR process. If you can implement a significant architecture change without an ADR and nothing bad happens, no code review block, no deployment gate, no explicit conversation with me, then the ADR process has no teeth and engineers will rationally skip it when they are under time pressure. How do I make it binding? 3 mechanisms. First, ADRs are gated into the pull request process for changes that meet a defined threshold. Any change that introduces a new dependency, changes a data model in a backward incompatible way, changes an API contract, or affects more than one service requires an ADR to be linked in the pull request before review begins. This is codifiable. I can put it in the pull request template as a required section. The code review is blocked until the ADR exists and has at least one review comment from a non-author. This makes the ADR happen before the code is written or very early in the process, not after it ships. Second, ADR review is a separate artifact code review. The ADR is reviewed in a dedicated asynchronous window, not in the pull request itself, but in a dedicated Slack channel or in a structured meeting cadence. The review is not about approval. It is about surfacing assumptions, second-order effects, and alternatives that the author did not consider. The goal is not to block decisions, but to make the decision maker aware of what they are not seeing. I model this by being the person who asks the uncomfortable question in ADR review, not in the post-mortem. Third, ADRs are living documents with a status field: proposed, accepted, superseded, deprecated. When a decision is superseded by a new decision, the new ADR must reference the old one. This creates a chain of reasoning that is auditable. When we have a production incident, I can trace the decision chain back to the ADR that established the architectural assumption that failed. That feedback loop, incident to ADR chain, is what makes engineers take the ADR process seriously. It is not bureaucracy. It is a tool for learning faster from failure.
ADR review as a separate artifact from code review with the status lifecycle that connects to incident retrospectives. That is the governance layer that most teams skip. To light a shift into the war stories section. This is where I want you to stop being the architect explaining the system and start being the engineer who lived through something that changed how you think. Here is the question. Tell me about a time in your career where your mental model of how a system worked was specifically and provably wrong, and you only found out because production told you so. I want the before model, the failure, and the after model. Do not give me a polished retrospective. Give me the messy version.
Okay, this one still bothers me when I think about it. About 6 years ago, I was leading the backend engineering on a subscription billing service. We had a salary worker fleet, maybe 40 workers, processing payment retries and invoice generation. The system was using Redis as the broker and the result backend. We had been running it for about 8 months and it was mostly fine, or so we thought. My mental model at the time was, salary is a mature task queue, Redis is reliable. If a task fails, it will be retried according to the retry policy, and if it exceeds the max retries, it will go to the dead letter queue. We called it the failed queue, where we could inspect it. I thought the system had good observability. We had Flawed for monitoring. We had alerts on task failure rate. I thought I understood what was happening. The failure came on a Sunday at about 2 in the afternoon. We had a batch of invoice generation tasks, around 3,000 of them, that were in queued at midnight for the monthly billing run. By Sunday afternoon, the payment team was calling me because a significant fraction of customers had not received their invoices, and the payment attempts were failing silently because there was no invoice to reference. We looked at Flower. The task count looked fine. The failure rate was within normal bounds. The dead letter queue had a handful of tasks, nothing alarming. I spent 4 hours convinced the problem was in the invoice generation logic, Sambat that was swallowing exceptions silently. I was wrong. The actual problem was this: we were running Redis with a memory limit configured. This was a shared Redis instance, and at midnight when 3,000 tasks hit the broker simultaneously, the Redis memory limit was reached. Redis in max memory policy volatile room mode started evicting keys. The keys it evicted were SLA result backend keys, the task result records. The task results were gone. But here is the part my mental model completely missed. When Celery stores a task result in Redis and that result key is evicted, Celery does not know. The task completed, the result was stored. From Celery's perspective, the task succeeded. The result just does not exist anymore. Flower shows success, the alert never fires, and the application code that was supposed to read the task result using async result to get the invoice ID got a timeout exception that was being swallowed by a broad except block. The invoice was never created. Celery thought it succeeded. The before model was Celery plus Redis is a reliable task queue and the failure modes are task failures, visible in Flower. The after model is the task queue and the result backend are separate reliability surfaces with separate failure modes, and the result backend's durability is only as strong as the underlying store's configuration. Redis with a memory limit and an eviction policy is not a durable result backend. The success status in the queue tells you the task ran. It says nothing about whether the result was persisted and is readable. What changed in my practice? I stopped treating Celery success status as an application level correctness guarantee. I added explicit outcome verification. After a task completes and the result is read, A separate reconciliation job checks that the expected downstream state actually exists. I also separated the broker and the result backend onto different Redis instances with different configurations, and I turned off result backend eviction entirely by using a dedicated instance with no memory limit policy, and I made the except block specific never catch bit exception in application code that reads task results. Let it propagate so the failure is visible.
Redis eviction silently making salary results disappear while flower shows green. That is the kind of failure that is genuinely hard to anticipate because it requires understanding two systems' interactions. The reconciliation job as the correctness guarantee rather than the queue status. That is the hard-won lesson right there. Let me ask you a second war story question, but I want to go to the human side of engineering this time. Tell me about a time where you had to deliver a technical assessment of a system or a code base that was correct and important but was politically uncomfortable, where the right answer created organizational friction. How did you handle it, and what did you learn about how to do that better?
There is a specific situation from about 3 years ago that I think about often when I'm in similar situations now. We had acquired a small company. This was an acquire situation, and their engineering team of 4 came on board with their code base, which was a Python service that handled a piece of functionality we wanted to integrate. I was asked to do a technical assessment of that code base and give a recommendation on integration approach. The code base was genuinely problematic, not in a junior engineer way. It was clearly written by smart people who had moved fast and had not had the luxury of revisiting early decisions. But there were real correctness issues, no transaction boundaries on operations that needed them, a home-built authentication scheme that had a timing oracle vulnerability, a data migration approach that would cause data loss under concurrent writes, not theoretical issues, specific demonstrable issues with documented failure conditions. The political problem was these 4 engineers were now my colleagues, the company had paid for them, their manager, who had been their CEO and was now a VP, was in the room when I was asked to present my assessment. He was proud of what his team had built. He had every right to be, given the constraints they had operated under. My instinct was to soften the assessment, to lead with the positives, bury the risks in qualifications, give the VP a way to walk away feeling good. I had done that before in code reviews, and I knew how it felt. Both parties felt better in the room, and then the issues became production incidents 3 months later. What I did instead, and this was uncomfortable, was separate the assessment into 3 categories: architectural decisions I would not change, engineering patterns I would change over time, and specific correctness issues that needed to be addressed before we put any production traffic on the service. I was explicit that the third category was not a judgment on the team's skill. It was a consequence of building fast under constraints, and it was fixable. I brought the specific failure conditions with reproduction steps, not just descriptions. I brought a remediation plan with timelines and offered to work alongside the acquired team on the fixes. The VP was not happy in the room. There was a difficult conversation. But 3 things happened after. The acquired engineering team privately, they knew those issues existed and they had been living with the anxiety of knowing. The VP came to me 2 weeks later and said he wished he had had that level of honest assessment earlier because it helped him make the case internally for dedicated remediation time, and the integration went well because we fixed the correctness issues before they became incidents. What I learned: specificity is kindness in technical assessments. Vague concerns give people nothing to work with and they become anxiety. Specific issues with specific remediation paths are actionable and they depersonalize the assessment. It is not about the engineer's quality, it is about a specific line of code in a specific context that needs a specific fix. The discomfort in the room is real, but it is shorter lived than the discomfort of a production incident that you could see coming.
Specificity is kindness in technical assessment. I am going to remember that framing. That is well said. The separation into 3 tiers: things you keep, things you change over time, things you fix before production, is a structure I think a lot of engineers could use when they are in those uncomfortable situations. Alright, we are going to do the rapid fire round now. These are shorter questions. I want your immediate, honest, opinionated answers. No hedging, no it depends. Go. Rapid fire. First one. Python's GIL is being made optional in 3.3. We have a CPU-bound data processing service that currently uses multiprocessing to work around the GIL. If you remove the GIL experimentally and move to threading, what is the first thing that breaks that you would not have predicted from the documentation?
The first thing that breaks is any C extension that assumes GIL protection for its internal state. Third-party libraries that do operations in C that look atomic because the GIL prevented true parallelism, NumPy's reference counting in certain operations, some database driver internals suddenly have race conditions that produce incorrect results silently, not clashes. Silent data corruption is the worst failure mode, and it is the one the documentation cannot enumerate for you because it depends on every extension you are using.
Second, you are doing a staff-level technical screen for a candidate with 10 years of Python experience. You give them 1 hour. What is the one question or exercise that you have found most consistently separate engineers who understand Python's execution model from engineers who have learned Python's syntax?
I ask them to explain what happens step by step at the interpreter level when you do from module import name in a Python file that is being imported by two different modules simultaneously in a multi-threaded context. The correct answer requires understanding the import lock, the sys.modules cache, and the partial module initialization problem. Engineers who have only learned syntax give me the happy path. Engineers who understand the execution model immediately go to the race condition on partially initialized modules and the GIL's interaction with the import lock. That question has not failed me once.
Third, most overrated tool in the modern Python ecosystem. Something the community talks about as essential that you think is being applied beyond its useful domain.
Pydantic for internal service boundaries. Pydantic is excellent at the boundary with external systems, user input, API responses from third parties. But I see teams using Pydantic models for every internal function call, every service-to-service message within a trusted boundary, and the result is validation overhead and schema coupling between components that should be loosely coupled. Not every data shape needs runtime validation. Internal trusted data should use data classes or type indexes and catch shape errors at type checking time, not runtime. Pydantic at the boundary, types in the interior.
Fourth, you are onboarding a new engineer and you want to measure whether your onboarding process is actually working as a system. You decide to track time to first meaningful pull request as a leading indicator. What is your operational definition of meaningful, and what does a bad answer to that definition tell you about your engineering culture?
Meaningful means a pull request that changes behavior observable by an end user or a downstream system that was reviewed and merged without the new engineer needing to be rescued by a senior engineer mid-implementation. Not a README fix, not a config file change, something that required the engineer to understand the domain, navigate the code base, and make a judgment call. The bad answer to defining meaningful is when teams say things like any merged PR counts. That definition reflects a culture where onboarding is measured by motion, not by capability transfer. If any PR counts, you are measuring activity. If meaningful PR counts, you are measuring integration into the system. Those produce very different onboarding investments.
Fifth, unpopular opinion. Give me something you genuinely believe about software engineering at staff level that most senior engineers would push back on.
I believe that technical debt is not a single category, and treating it as one is one of the most expensive organizational mistakes engineering teams make. When you say we have tech debt and put it in a single backlog bucket, you are conflating four different things: code that is hard to understand and change, architecture that was correct for a different scale and is now wrong, dependencies that are outdated and represent security risk, and design decisions made under uncertainty that we now have enough information to revisit. Each of those has a different urgency, a different cost of inaction, and a different kind of engineer who should own the fix. Treating them as one bucket means the most urgent items, security risk dependencies, Scale wrong architecture, compete with the least urgent items, clean up refactoring, and the prioritization becomes arbitrary. You need a vocabulary that is precise enough to enable triage, and tech debt is not that vocabulary.
Tech debt as 4 separate categories with different urgency profiles and different ownership. I think that will resonate with a lot of engineering managers listening. Alright, one more rapid fire. This one is a fast scenario. You have an Ascensio-based Python service and a developer on your team proposes solving a backtracer problem by simply increasing the Ascensio queue max size from 100 to 10,000. What do you say?
I say, you have not solved the back pressure problem, you have deferred it. Back pressure exists because the consumer cannot keep up with the producer. A larger queue does not change the consumer's throughput. It changes when you find out that the consumer keep up. With max size of 100, you find out immediately and the producer blocks, which is useful feedback. With max size of 10,000, you find out in 3 hours when the queue is full, memory is exhausted, and the service is unresponsive. The queue size should be set based on the maximum acceptable latencies for items in the queue, not based on making the warning go away. If the consumer is genuinely too slow, the fix is more consumers or a faster consumer, not a bigger queue.
Queue size based on acceptable latency, not based on making the warning disappear. Perfect. That is the rapid fire. Let us land this plane. Okay. Before I let you go, I have 2 closing questions. First one, if you could go back to the version of yourself at the 5-year mark, experienced enough to be confident, not experienced enough to know what you do not know, what is the one thing you would tell that engineer about what staff level work actually requires that junior you did not have a mental model for?
I would tell him being right is table stakes and it is not the job. At the 5-year mark, I genuinely believed that influence came from technical correctness, that if my design was right, the organization would converge on it, and if it did not, that was the organization's failure. What I did not have a mental model for is that staff level work is the work of making the right thing legible, writing the decision down so that someone 2 levels up can reason about the trade-off without understanding the implementation, framing a risk so a product manager can wait against a deadline honestly, building the ADR chain we talked about earlier so the reasoning survives after I leave the room. 5-year me thought that was overhead around the real work. It is the real work. The code is the smallest part of the job at this level. And the strange thing is, my code got better once I accepted that, because I stopped writing code to prove things and started writing code to be operated by other people. The second thing I would tell him, your taste in problems will matter more than your speed at solving them. At 5 years, I optimized for solving whatever was in front of me quickly, and I was rewarded for it. Staff level work is choosing which problems the team should never have to solve at all, the class of bug that a better boundary eliminates, the on-call pitch that a design decision retires permanently. Nobody hands you that scope. You have to start reasoning at that level before anyone asks you to, and 5-year me was waiting to be asked.
Legibility as the real work and taste in problems over speed at solving them. That is going to sit with people. Second closing question, and then I will let you go. There are engineers listening right now who are at exactly that 5-year mark. Good, confident, hungry, and honest enough to admit they do not yet think the way you thought out loud today. Give them something concrete. What is one deliberate practice they can start this week? Not a book, not a course, a practice that compounds toward the kind of judgment we have been testing for the last hour.
Keep a decision journal and actually close the loop on it. Here is the practice. Every time you make a technical decision that matters, a library choice, a schema design, a caching strategy, a queue size, write down 3 things before you ship it. What you expect to happen, what evidence would prove you wrong, and a date 4 or 6 weeks out when you will go back and check. That last part is the whole practice, because almost every engineer makes predictions and almost no engineer audits them. We remember our wins vividly and our wrong calls vaguely, and that asymmetry is exactly why 10 years of experience can be 1 year repeated 10 times. Every mental model correction I talked about today, the async connection pool assumptions, the Redis eviction blind spot, the pymalloc behavior, I only extracted the lesson because I had a written record of what I had believed before production corrected me. Without the record, you quietly rewrite history and tell yourself you knew it all along. With the record, the gap between your prediction and reality is staring at you in your own handwriting, and that gap is where judgment actually comes from. It cost 10 minutes per decision. It is the highest leverage 10 minutes I know of in this profession. Start this week.
The decision journal with a close the loop tape. If you take one thing from this episode, take that. Saket, this was outstanding. Genuinely one of the strongest sessions we have run on this series. The pymalloc fragmentation walkthrough, the outbox pattern with the relay failure mode spelled out, the Django ORM lookup injection surface, and that Redis eviction war story is going to save somebody a very painful Sunday afternoon. Whoever ends up hiring you is getting an engineer who has done the work of understanding his own mistakes, and that is rarer than 15 years of experience. Thank you for letting us push you this hard on the record. To everyone watching and listening, this is the Kritia AI Labs Tech Interview Series. If this episode sharpened your thinking, like the video, subscribe to the channel, and check the full mock interview playlist linked in the description. We have episodes across senior, staff, and principal levels. And drop a comment telling us which question in this episode you would have struggled with the most. We read every one, and the honest answers help us design the next interviews.
Thank you, Balu. This was harder than any rare interview I have sat in the last few years, and that is exactly what I wanted from it. For everyone at the senior or staff level who is preparing for a move, do not just watch this, pause at each question, record yourself answering out loud before you hear my answer, and listen to the recording. The gap between the answer in your head and the answer that comes out of your mouth is the gap you need to close before you are in a real room. Thanks to the Kritia AI Labs team for building this, and good luck out there.
Welcome back to the Kritia AI Labs Tech Interview Series, the show where engineers grow, learn, and get hired. I am Balu, Senior Technical Architect at Kritia AI Labs, and today we are doing something I genuinely look forward to every time we record it, a distinguished engineer level mock interview. Now, when I say distinguished, I do not mean that lightly. Our guest today has 16 years of Python engineering across fintech and SaaS platforms. He has held staff and distinguished engineer titles, led engineering teams of 15 plus people, designed event-driven payment systems that process millions of transactions, and he has the kind of production scars that only come from shipping real software at real scale under real pressure. He is currently looking for his next role, and today's session is going to show you whether you are a hiring manager, a fellow engineer, or someone preparing for your own staff level interview, exactly what depth looks like when someone has genuinely earned it. His name is Saket. Saket, welcome to the show.
Balu, thank you. I have been looking forward to this. 16 years means I have made enough mistakes that I can actually talk about them honestly, so let us have a real conversation.
That is exactly the energy we want. Before we go deep, I want to tell the audience what we are going to cover today. We are going to touch Python runtime internals, specifically the memory model under sustained async load, the free-threaded CPython 3.30 question, and what import system internals cost you in a large code base. We are going to go into multi-tenant security with a specific async context propagation vulnerability that I think will make some of you genuinely uncomfortable if you are running a SaaS product right now. We will cover the transactional outbox pattern's own failure modes, the saga pattern failure taxonomy in fintech, and we will end with a rapid fire round where I will ask Saket some genuinely opinionated questions about the state of the Python ecosystem. Roughly an hour of depth, no flaw. Let us go.
I appreciate the structure. The async memory model question is one of my favorites because it is the kind of problem that sounds exotic until the first time your service starts eating 8 gigabytes of RAM on a Tuesday afternoon and nobody can explain why. And the context bar vulnerability, I suspect, will be uncomfortable for more people in the audience than they expect. Let us get into it.
Good. Let us start with a warm-up before we go into the deep technical material. 16 years across fintech and SaaS. That is long enough to have seen multiple architectural paradigms come and go. If you had to identify the single most expensive technical mistake you have personally made, not a team mistake, not an inherited mistake, but a decision that was yours, what was it? What was the production consequence? And what is the thing you now do differently because of it that you would not have done at year 5 or year 6 of your career?
The most expensive mistake I personally made was an idempotency design decision in a payment retry system around year 7 of my career. I want to be specific because the lesson is in the specifics. We were building a disbursement service that paid out insurance claim settlements to policyholders. The business requirement was that a failed disbursement must be retried automatically until it succeeds or until a human explicitly cancels it. I designed the retry loop with an idempotency key derived from the claim ID and the disbursement amount, claim ID plus amount, that seemed correct at the time. It uniquely identified a disbursement attempt. The mistake was that amount is mutable. A claims adjuster can reopen a settled claim and adjust the payout amount. This is a legitimate business operation. When it happened the first time in production, the adjuster updated the settlement amount. The retry loop generated a new idempotency key because the amount changed, and the system treated it as a new disbursement. The policyholder received 2 payments, the original amount and the revised amount. We sent out a total of around $42,000 in duplicate disbursements before the nightly reconciliation caught it. The production consequence was a week of manual reconciliation with our banking partner, a formal incident report to our compliance team, and a very uncomfortable conversation with the CFO. The technical fix was straightforward. Idempotency keys must be derived from identifiers that are immutable at the time of initial submission. Claim ID plus disbursement event ID, where the event ID is generated once at event creation and never changes regardless of what happens to the underlying claim. Amount is a payload attribute, not an identity attribute. I knew that principle abstractly at year 5. I did not apply it rigorously because I was moving fast, and the case of a mutable amount never appeared in my requirements document. What I do differently now for any financial transaction system, I write an explicit idempotency key design document before touching implementation. It lists every attribute considered for the key, and for each attribute it requires a written justification of why that attribute is immutable for the lifetime of the transaction. It is a short document, usually half a page, but the act of writing it forces exactly the kind of reasoning that I skipped when I made that mistake. The meta lesson is that the mistakes that cost you the most at the staff level are not the ones where you did not know the answer. They are the ones where you knew the principle but did not apply it rigorously because you are moving fast. Rigor is not the opposite of speed. Rigor is what prevents the 6-week cleanup that cost you the speed you thought you were saving.
Good. Second warm-up, and this one is more personal. You have been a staff engineer, a distinguished engineer, and you have managed teams of 15 plus engineers. Most people treat that as a linear progression. You get good at code, then you lead people, then you do strategy. But 16 years is long enough to know that career paths are rarely linear. Tell me, at what specific moment did you realize that the highest leverage thing you could do was not write better code or lead a better team, but actually change how your organization thinks about a technical problem? And what was the specific problem?
The moment was about 8 years into my career, and the problem was how my organization thought about database migrations in a high availability fintech system. We had a Django-based platform that processed insurance premium payments. The engineering culture at that time had a perfectly reasonable sounding policy: run migrations as part of the deployment pipeline inside a transaction, rollback if the deployment fails, clean, save, version controlled. The problem was that this policy was designed for a team of 5 engineers with a 5,000 row database, and we had grown to a team of 30 with a 200 million row payments table. Every quarter, we would have a migration that took 45 minutes, held a table lock, and caused a payment processing outage. And every quarter, the post-mortem would say, we need to be more careful about which migrations are risky. We need better review. We were treating each incident as an execution problem rather than a structural problem. I had been an individual contributor and a tech lead, and my instinct was always to write the tool, build a migration linter, add a CI check, solve it technically. And I did build those things, but the real problem was not the tooling. The real problem was that the organization had an implicit mental model of migrations as simple, atomic, and low risk inherited from an earlier year of the product. No tool changes a mental model. You have to change the conversation. So I stopped writing the tool and I started writing the document. I wrote a 4-page internal RFC that framed database migrations as a zero downtime distributed systems problem, not a deployment pipeline problem. I walked through the expand contract pattern. I documented the specific PostgreSQL lock types that each Django migration acquires. I showed the blast radius of a lock on a table during peak payment processing hours using actual numbers from our monitoring. The document did not just go to engineers. I wrote a 1-page executive summary and took it to the BP of engineering and the BP of product simultaneously, because the fix required accepting slower deployment velocity in exchange for payment availability, and that trade-off was not mine to make unilaterally. The outcome was that we adopted a formal migration safety policy. We trained every engineer on expand contract, and we reduced migration-related incidents to near zero. The code I wrote to support that was maybe 200 lines. The document was the product. And that was the moment I understood what leverage actually means at the staff level.
The expand contract pattern is exactly the right answer for that problem. Quick follow-up. When you joined a new organization later in your career, how did you rebuild that kind of influence from zero relational capital? Because that RFC worked partly because you had the standing to get it in front of the right people.
The honest answer is that in the first 90 days, I deliberately to be a contributor rather than an influencer. I closed tickets, I reviewed pull requests, I fixed one production issue that was slightly outside my immediate scope, not to build a reputation, to build a picture of how the system actually behaves versus how it is documented to behave. Those are almost always different, and the gap between them is where the real problems live. By day 90, I had a list of 5 structural problems. I picked the one that was causing the most visible pain for other engineers, not the most technically interesting one, the most painful one, and I wrote a short document proposing a fix. I brought it to my manager first, not to ask permission, but to find out who else cared about this problem and who had tried to fix it before. That second question is the crucial one. If someone tried before and failed, I need to understand why before I become the 4th person to make the same proposal and be dismissed. Relational capital is not built by being impressive. It is built by being reliable and by demonstrating that you understand the problem the organization is actually living with, not the problem you think they should be living with.
Let us go into the technical deep dives. I want to start with Python runtime internals, specifically the memory model under sustained async load. In a high-throughput asyncio service, let us say a FastAPI application handling 50,000 requests per second, engineers frequently observe memory growth that is slow, consistent, and very hard to attribute. Tracy malloc snapshots show allocations concentrated in coroutine frame objects and asyncio internals. Walk me through what is actually happening at the CPython level, the specific failure modes that cause coroutine frames to outlive their useful life, and how you systematically diagnose and fix this class of leak without taking the service offline.
This is one of those problems where understanding the Python object model at a very concrete level is the prerequisite for diagnosis. So let me walk through the layers. At the CPython level, every coroutine is a Python frame object wrapped in a coroutine object. When you call an async function, CPython allocates a pyframe object on the heap, not the stack, along with the coroutine's local variable namespace, the instruction pointer, and a reference to the code object. This frame object persists for the entire lifetime of the coroutine, including all of its suspension points. Under sustained load at 50,000 requests per second, if your average coroutine lifetime is even 100 milliseconds, which is perfectly normal for a database touching request, you have 5,000 live coroutine frames in memory at any given instant, each carrying its local namespace. The failure mode that causes frames to outlive their useful life has three common causes. The first is asyncio.task references held by containers that outlive the request. The most common version of this is a background task set. Engineers write something like self background tasks.asyncio.create coroutine to fire and forget, and then forget to discard the task from the set when it completes. Asyncio.tot@short .stock combined with set.discard is the fix, but teams miss this constantly. The second cause is async generator objects that are not explicitly closed. In Python 3.2 now and earlier, if you abandon an async generator, you break out of an async for loop, or you cancel the task iterating it, the generator's frame is not immediately reclaimed, it sits in the asyncio finalizer queue. Under sustained load, this queue grows faster than it drains, and you get a slow monotonic memory increase that looks exactly like a leak. Recent Python releases have improved the asyncio internals here, but the finalizer queue behavior is still timing dependent, so the reliable fix on any runtime is explicit async.gn.acclose in a try-finally block, or cleaner, wrapping the iteration in context_lib.acclosing. The third and most subtle cause is the interaction between asyncio.shield and task cancellation. When you call asyncio.shield on an awaitable, you create a new inner task that is protected from cancellation. If the outer task is cancelled, the shielded inner task continues running. This is fine and intentional. But if your code stores any reference to the outer task, or if the outer task captures the inner task via closure, you now have a reference cycle between tasks that the garbage collector may not collect promptly, because the GC does not run on every allocation and coroutine objects involve C extension types that complicate cycle detection. The diagnostic approach I use: first, enable gc.setDeskerDebug gc.set uncollectible in a staging environment and look for uncollectible objects. Second, take treezymalloc snapshots at 5-minute intervals and diff them. You want to see which allocation site is growing, not just the total. Third, use IOmonitor or a custom asyncio debug loop that periodically logs the number of live tasks from asyncio.all_tasks, monotonically increasing live task out is diagnostic of the retained reference class of problem. And fourth, deploy with Python 3.12 or later, because the asyncio internals improvements in that release eliminate an entire class of these problems that earlier versions have.
The done_color plus discard pattern for background task sets, I want to flag that for the audience, because it is a 2-line fix for a leak class I see in almost every asyncio codebase I review. Related question, and I want to push into CPython 3.13.13 territory here. Free-threaded Python, PEP 703, the no EIL experimental build, has been getting a lot of conference talk energy. My question is not whether it is a good idea theoretically. My question is more practical. Does the existence of free-threaded Python change how you would architect CPU-bound fintech workloads today, right now, given that the ecosystem is clearly not ready? Or is this a case where you watch from a safe distance for 2 more years?
My honest position is, it changes how I design interfaces today, not how I deploy runtime today. Let me explain that distinction. The ecosystem readiness story is well understood by now. The extension layer still carries GIR assumptions, and until the maintainers of the heavy dependencies ship audited free-threaded builds deploying production workloads, there is trading a performance ceiling for a correctness lottery. I do not need to relitigate that. The more interesting question is what a staff engineer should be doing about it today, why the runtime is not yet an option. For a fintech workload, specifically something like risk calculation or portfolio analytics that is genuinely CPU bound, The attractive promise of free-threaded Python is that you can finally use threading for CPU parallelism without multiprocessing overhead. No process fault, no serialization of shared state, no IPC. That is a real benefit, but I would not take a payment risk engine that processes regulatory capital calculations onto the free-threaded build today because the correctness guarantee is not there yet for the full dependency tree. What I mean by changing how I design interfaces today, I am being more deliberate about isolating CPU-bound workloads behind clean interface boundaries, a well-defined task interface, explicit data contracts, no shared mutable state crossing the boundary. That is good practice regardless of the GIL situation. But it also means that when the free-threaded ecosystem is ready, and I think realistically that is CPython 3.16 or so, when the major C extension maintainers have caught up, I can slot in threading where I currently slot in multiprocessing without rewriting the surrounding code. The engineers who are going to be hurt are the ones who are writing CPU-bound code today with implicit shared state assumptions, believing that the GIL protects them. In a free-threaded world, that code is a data race waiting to be discovered. So the lesson from PP 703 that applies right now is, treat the GIL as an accident of implementation, not as a correctness mechanism.
I want to go directly into multi-tenant security. There is a specific class of vulnerability in async Python SaaS applications that I think is genuinely underappreciated, and I want you to walk through it. The vulnerability involves context swap and tenant identity propagation in an async request pipeline. Set the scene: a FastAPI application with the middleware that extracts a tenant identifier from the JWT and sets it on a context var at the top of each request. Walk me through exactly how tenant identity can cross over between concurrent requests in this architecture, why the standard middleware implementation gets it wrong, what a real exploit looks like at the production traffic level, and what the correct defense in depth looks like, including your opinion on PostgreSQL row-level security in a high-throughput context.
This one keeps me up at night when I review code bases that are not mine, because the incorrect pattern is everywhere and it looks correct to engineers who have not internalized how Python's context variable model actually works. Let me walk through the failure mode step by step. The naive implementation looks like this. In your FastAPI middleware, you call tenant asker id taskbar.set extracted asker tenant askeret at the beginning of request processing. This looks correct. It sets the context variable for the current execution context. But here is what most engineers do not know. In Python's context bars model, a context bar.set call modifies the current context object in place. It does not create a new isolated context. When Asensio creates a new coroutine task, it does copy the current context via copy task input. That copy happens at task creation time, not at every await boundary. The crossover happens whenever two requests end up sharing a context instead of each getting an isolated copy, and that happens in more places than people assume. The clean case is the one everyone pictures. The server creates a fresh task per request. The context is copied at task creation. Each request is isolated, but that assumption silently breaks in three places. First, HTTP keep alive sequential request on the same connection can be processed within the same connection scope task and therefore the same context. Set the tenant on request 1, and if request 2 takes any path that skips the override, it runs as the previous tenant and behind a load balancer that pools connections. Consecutive requests on one connection can belong to different customers. Second, shared worker patterns. A pool of long-lived consumer tasks pulling work of an async queue copied their context once at worker creation, so every job a worker processes mutates and reads the same context. Third, middleware that does not run where you think it runs. Starlet's base HTTP middleware has a well-documented task boundary quirk where code around call next can execute in a different task and context than the endpoint, so your set lands in a context you did not intend. In FastAPI specifically, if your middleware calls context_var.set anywhere that is not guaranteed to execute inside the per request task, and base HTTP middleware gives you no such guarantee, you have exactly this vulnerability. The correct pattern is to wrap each request handler in a copy of the current context, context equals context_var.copy test context dot handle I'm star and then slangs and car request. This creates a private context snapshot for each request, and any context var mutations inside that context are not visible outside it. What does a real exploit look like at production traffic level? Under low traffic, connections are short-lived, worker pools sit idle, and the stale context window almost never lines up with a tenant boundary. The bug is invisible, which is exactly why it survives review. Under high concurrency, connection reuse is constant and the worker pool is saturated, and the probability that a request leads a tenant identity left behind by a different customer's request stops being negligible. In a fintech multi-tenant platform, this means customer A's API request can receive data from customer B's tenant context, specifically any database queries that use the tenant taskd from the context var for row filtering will return the wrong tenant's data. In a payment system, this is a category 1 data breach. The defense in depth I designed for has 4 layers. First, the correct context isolation pattern I described, copied the context as lesson, but request mandatory, enforced via a middleware audit in CI. Second, an application level assertion in every database query layer that the tenant ID in the context var matches the tenant ID in the JWT claims, checked explicitly on every query execution, not just at the middleware boundary. This is your defense against logic errors and context bugs simultaneously. Third, PostgreSQL row level security, which I will address in a moment. And fourth, response invariant middleware that validates the tenant ID in the response body for API endpoints that return tenant scoped resources before the response is sent to the client. On RLS at high throughput, yes, it introduces overhead, and the honest answer is workload dependent. In our benchmarks, RLS with a simple policy adds roughly 3 to 8% CPU overhead on the PostgreSQL server for read-heavy workloads. The mitigation is indexing. Your tenant ASCII ID column must be part of composite indexes that match your query patterns. Because RLS policy evaluation can inhibit index-only scans if the planner re-evaluates the policy predicate row by row. With correct indexing, the overhead is manageable and the security guarantee is categorical. For a fintech multi-tenant platform, the cost of a data breach in regulatory fines and customer trust vastly exceeds the cost of 2 additional PostgreSQL nodes to absorb RLS overhead. That trade-off is not close.
That response invariant middleware as a defense in depth layer, I have not heard that framed exactly that way before, and I think it is elegant. Quick follow-up, if you had to write a single fitness function, something that runs in CI that would have got this specific context var crossover bug class, what would it check?
The fitness function I would write checks for any async function in the middleware or request handling layers that codes context var.set without being wrapped inside a context vars.copy_context.run call or an equivalent explicit context isolation boundary. Specifically, I would write an AST-based static analysis rule, a custom Flake 8 or Pylint plugin that traverses the async call graph starting from your ASG entry points and flags any context var.set call that is reachable without a copy context ancestor in the call tree. The check is a reachability analysis, not just a line-level pattern match, because the set call is often inside a helper function that is called from middleware. The secondary check I would add, a concurrent request simulation test that spins up 2 async tasks with different tenant identities, interleaves their execution using async show.sleepso to force context switching at every await point, and then asserts that each task observes only its own tenant tasker ID at every database query side. This test will reliably reproduce the crossover bug if the context isolation is wrong, and it runs in under a second. It is the kind of test that pays for itself the first time a junior engineer refactors the middleware without understanding the context var model.
Let us move to distributed systems. The transactional outbox pattern is well understood at the tutorial level. You write your domain event to an outbox table in the same database transaction as your state change, and a separate poller publishes it to your message broker. But here is the production failure mode that teams discover not in the design review, but 6 months after go live. The outbox poller becomes a bottleneck at scale. and teams add multiple polar instances for parallelism. Now you have a distributed polling problem. Walk me through the specific failure modes that emerge when you run 3 outbox polar instances against the same PostgreSQL outbox table, and tell me how you design your way out of it without introducing a coordination service.
This is a failure mode I have debugged twice in production, once in a payment notification system and once in a ledger event pipeline, and both times the root cause was the same fundamental misunderstanding about PostgreSQL locking semantics. Let me walk through what happens when 3 polar instances run naively. The naive query is something like select star from outbox where status equals pending ordered by created acat limit 100 for updates. Without skip load, all 3 polars execute this query against the same table. The first polar acquires row-level locks on the first 100 pending rows. The second and third polars execute the same query and immediately block. They are waiting for the first polar to release its locks. You now have 3 polars, but you are getting single polar throughput plus the overhead of lock contention. That is failure mode 1, lock contention that serializes your parallelism. Failure mode 2 is more dangerous, double processing. If you are not using select for a big and instead you are using an optimistic locking strategy, select the row, process it, then update status to published, you have a race window between the select and the update. 2 polars can select the same row, both see status appending, both process it, both attempt the status update. One wins the update race, the other has already published the event to Kafka or SQS. Your downstream consumers receive 2 copies of the same event. In a payment disbursement pipeline, duplicate event processing equals duplicate transactions. I have seen this cause a $2 million accounting reconciliation problem. Failure mode 3 is the one teams do not anticipate, lock wait timeout cascades. Under high load, the average time a polar spends waiting for locks increases. If your polar has a reasonable lock timeout configured, say 5 seconds, polars start timing out and retrying. Retrying means requerying, which means recompeting for locks, which means the contention gets worse. This is a positive feedback loop that can take a polar fleet from degraded to completely non-functional in under 2 minutes. The fix for the contention and the cascade is skip locked. Each polar claims a disjoint set of unlocked rows and moves on instead of queuing behind its siblings, and 3 polars finally give you 3 times the throughput. But here is the failure mode that almost nobody designs for, because skip locked introduces it. Broken per aggregate ordering. Your query orders by created cascade, but a polar that skips a locked row and takes the next one can publish event 7 for a payment, while a sibling polar is still publishing event 6 for the same payment. Downstream consumers that assume in-order delivery per aggregate, and ledger consumers always assume it, silently corrupt state. The design answer is to claim work in units of aggregate identity, not in units of rows, hash the aggregate ID across polar instances, or claim batches grouped by aggregate so that all pending events for a given payment always flow through one polar in order. The design I prefer at scale, however, is to eliminate the polling problem entirely by treating the PostgreSQL write-ahead log as a first-class event stream. Debezium, or any CDC tool built on PostgreSQL logical replication, consumes the val directly and publishes changes to Kafka without any application-level polling. You are not reading from a derived outbox table that a polar maintains. You are consuming the ground truth log of what actually changed in the database. This eliminates the polar contention problem structurally, gives you sub-second event latency rather than polling interval latency, and means your outbox table can simply be an append-only events table with no status field that needs updating. The trade-off is operational complexity. You are now running a CDC pipeline that requires monitoring and operational care. But for a payment platform processing millions of events per day, that complexity is worth it.
The WAL as a first-class message stream via Debezium. I want to flag that for the audience because it is a clean conceptual shift. You are not polling a derived table, you are consuming the ground truth log. Now let me pivot to saga pattern. In fintech, the saga pattern is unavoidable, long-running distributed transactions across payment services ledger services, notification services, but most teams I talk to implement sagas and only get the happy path right. Walk me through the failure taxonomy that teams miss, specifically the distinction between compensatable transactions, pivot transactions, and retrievable transactions, and tell me why most compensation logic is wrong in production.
The failure taxonomy is the part that the conference talks leave out because the happy path saga looks elegant and the failure taxonomy is messy. Let me be precise about the three categories because conflating them is what makes compensation logic wrong. A compensatable transaction is one that can be semantically undone. In a payment disbursement flow, debiting the source account is compensatable. If the downstream transfer fails, you can credit the source account back. The compensation is a domain operation, not a rollback. This is critical. You are not undoing the original transaction at the database level. You are creating a new transaction that neutralizes its effect. The source account debit is in the ledger permanently. The compensation credit is also in the ledger permanently. Both are auditable. This is the correct mental model. A pivot transaction is the point of no return. It is the step after which compensation becomes impossible or unacceptably expensive. In a payment flow, the pivot is typically the external money movement, the ACH file submission, the wire transfer instruction sent to the banking partner, the card network authorization capture. Once that instruction leaves your system and is acknowledged by an external party, you cannot compensate it with a database write. You need a reverse transaction through the same external channel, which may take days and involves human intervention. Most teams design as if every transaction is compensatable and then discover their pivot transaction during a production incident. Retrievable transactions are idempotent operations that will eventually succeed given enough retries. Database record creation with an idempotency key, notification sends with at least once delivery semantics, read-only balance checks. These do not need compensation, they need retry logic with exponential backoff and a clear idempotency guarantee. Now, why is most compensation logic wrong in production? 3 reasons. First, teams compensate in the wrong order. The correct compensation order is the reverse of the forward transaction order, but it must account for which transactions have actually completed at the time of failure. If steps 1, 2, and 3 completed before the failure at step 4, you compensate 3, then 2, then 1. But if the saga implementation does not reliably track which steps succeeded, and this requires durable state, not in-memory state, the compensation order logic can execute compensations for steps that never completed, creating phantom credits or phantom reversals. Second, teams confuse the pivot transaction and attempt to compensate it. I have seen a saga implementation that, on failure after the external wire instruction, attempted to compensate by reversing the debit on the source account without confirming whether the wire actually landed at the destination. The result was that the customer's source account was credited twice, once by the compensation, once because the wire failed at the bank and was returned. The correct behavior at the pivot transaction boundary is to put the saga into a manual review queue, not to attempt programmatic compensation. Third, and most subtly, teams do not model the compensation of the compensation. If your compensation step fails, and it can, because compensation is also a distributed operation, you now have a failed compensation. Most saga implementations have no defined state for a failed compensation. They enter an undefined state that requires manual intervention. But since the state is undefined, the monitoring does not alert on it and the engineers do not know what to look for. I require every saga implementation to have explicit terminal states for both successful completion and compensation failure, and those failure states must be observable in your monitoring before you go live.
The concept of compensating the compensation, that is a failure mode I have seen teams hit in production and spend a week debugging without knowing what they are looking at. One final deep dive before war stories. This one is about supply chain security specifically. You are running a fintech platform. You publish internal Python packages to a private PyP server for shared libraries, authentication, audit logging, shared data models. Walk me through the supply chain threat model that goes beyond dependency pinning and tell me what SBOM generation and package attestation actually buy you in practice for a private PyP setup?
The threat model that goes beyond dependency pinning has 3 layers that most security reviews miss, and I want to be specific about each one. The first layer is install time code execution. Most engineers model this supply chain risk as malicious code runs when I import the package. That model is wrong in a way that matters. With source distributions, the code runs when you install it, and dist ships a build script, and pip executes that script at install time with the full privileges of the installing process. Your CI runner, the one holding Azure credentials and network access, executes a Docker-controlled Python before your application ever imports anything and before any scanner has looked at the package contents. The defense is structural. Enforce wheels only installs pips only binary flag set to all in every CI and production environment, so nothing executes at install time. Build your internal packages exclusively as wheels and lock your private index for internal names, so the dependency confusion class of attack, which deserves and has gotten its own dedicated discussion on this show, never reaches the install step at all. The second layer is compromised maintainer accounts for transitive dependencies. Dependency pinning protects you from version drift, but not from a scenario where a pin version's package source is modified after you pinned it, which can happen if your private mirror caches the package at download time and an upstream maintenance account was compromised before you cached. The defense here is pinning to a content hash, not just a version. Pip install package 12223 does not protect you if the tarball changes. Pip install package 12223 hash extra to 56 fz1223 does. Every dependency in your requirements file should carry a hash. Pip tools generates this automatically. This is your basic pin. The third layer is type squatting of your internal package namespace. If your internal packages are named with a short or common prefix, adversaries may register similar names on public PyPI. A package named Kratia Ode versus Kratia Ode stash or Kratia utils versus Kratia utils utinote, and hope that the developer's pip install typo or a misconfigured CI script installs the malicious one. The mitigation is namespace registration. Register your internal package names on public PyPI as empty stubs that simply print a warning and exit, so that even if someone installs the public version, it does not execute malicious code. On SBOM generation and package attestation, an SBOM in CycloneDX or SPDX format gives you a machine-readable inventory of every package in every image, including transitive dependencies. The practical value for a private PyP setup is not primarily in vulnerability scanning. You can do that with pip audit against a known CVE database directly. The value is in compliance auditability. When a regulator asks you to demonstrate that you know exactly what code was running in your payment processing service on a specific date, the SBOM is your answer. Pair it with image signing via cosign and your container registry's attestation support, and you have a cryptographically verifiable provenance chain from source commit to production image. For a fintech under PCI DSS or SAG2 Type 2, that chain is not optional, it is evidence.
Excellent. Let us shift into war stories. I want to hear reproduction experiences, not hypotheticals. Saket, tell me about a time when your architecture decision record process, the ADR process, broke down in a way that had real consequences. Not a case where an ADR was missing, but a case where ADRs existed and were followed correctly and still created a problem.
This story is about 2 years into a SaaS platform rebuild, and it is one I think about often because the failure was structural rather than individual. We had adopted ADR seriously. We had 30 plus records. They were numbered, they were reviewed, they were merged into the repository as first-class artifacts. The specific ADR in question was ADR 214, the decision to use Celery with Redis as a background task queue instead of a managed queue service like ours SQS. The ADR was well written. It documented the context we were a 12-person team, moving fast, and managed queue services introduced operational overhead we were not ready to absorb. It documented the trade-offs clearly. Celery plus Redis was operationally simpler for our current team size. but would require re-evaluation if our task volume exceeded a certain threshold or if our team grew to a point where operational complexity was manageable. The ADR had a review trigger, re-evaluate at 10,000 tasks per day. We hit that threshold 18 months later, and here is where the process broke down. The ADR was a document in a repository. It was not connected to any operational signal. When we crossed 10,000 tasks per day, nothing happened automatically. No alert fired. No review was scheduled. The ADR existed in the repository unchanged as a historical record of a decision made 18 months earlier under entirely different conditions. But it continued to be read as a current endorsement of the architecture. New engineers who joined the team, read ADR N14N, concluded that Celery plus Redis was the approved architecture, full stop. They extended it. They built new features on top of it. The RDR's authority as a document made it harder to question the architecture, not easier, because it gave the impression that the decision had been made deliberately and was therefore correct for current conditions. We discovered the gap during a post-mortem on a Celery broker saturation incident. 3 engineers in the post-mortem independently cited ADR justice enforcing as justification for the current architecture. When I pointed out that ADR set 14 had an explicit review trigger that we had missed by about 6 months, the room went quiet. We had a decision record that was accurate historically and misleading operationally. The thing I changed after this, every ADR we write now has 2 required fields beyond the standard template. First, a metrics link, a direct pointer to the specific dashboard or alert that represents the review trigger, not prose describing what to measure. A URL to the monitoring query. Second, an expiry date, a maximum time to revert, regardless of whether the metric trigger fires. The metric is a leading indicator, the expiry is a backstop. ADRs are not permanent endorsements. They are time-bounded decisions with explicit operational accountability. The lesson, and this is the part I share when I mentor engineers on architectural governance, a document that is not connected to the system's operational reality is not a living document. It is a historical artifact that acquires authority it has not earned.
Really powerful. Thank you for sharing that honestly. Let us shift into rapid fire. I will ask you short opinionated questions and I want short opinionated answers. You can push back, you can qualify, but keep it tight. Ready?
3D.
First, import system internals. Specifically the cost of a large import graph in a FastAPI application at core start time. Engineering teams routinely see 3 to 5 second core starts in production, Lambda or Cloud Run deployments, and the traceback leads to import time. Is the right answer lazy imports deferring module loading to first use? Or is that a trade that creates worse problems than it solves?
They are a trade, not a solution. Lazy imports defer the pain to the first call site, which is often worse than a predictable startup cost because you now have a latency spike on the first request after a cold deploy, the request that your health check or load balancer might be timing out against. The right solution is reducing what you import at startup, audit your import graph with Python next import time, identify the heaviest transitive imports, and move optional heavy dependencies behind conditional imports that only execute when the specific feature is invoked. Lazy imports as a blanket strategy are a smell that your module graph has too many direct dependencies at package level. Fix the graph, not the symptom.
Second, meta classes and descriptor protocols in framework-heavy Python code bases. Elegant power feature or hidden performance and maintainability tags that most teams would be better off avoiding.
Hidden tags almost always. The frameworks themselves, Django, SQL Alchemy, Pydantic, use them for good reasons and they have the engineering depth to manage the complexity. Application engineers using metaclasses in business logic code are usually solving a problem that a data class or a simple class hierarchy would solve equally well. The cost is that every junior engineer who joins the codebase spends 3 days trying to understand why a class behaves differently from what the code shows. That is a tax you pay every time you hire and it compounds.
Third, cryptographic agility, designing systems so that rotating from SHA-256 to a different algorithm does not require a multi-quarter migration. Is this a real architectural concern that fintech teams should be designing for today? Or is it over-engineering for a threat that has never actually materialized in practice?
It is a real concern and it has materialized: the SHA-1 deprecation in certificate chains, the MD5 retirement in legacy systems, and now the post-quantum cryptography migration that NIST is actively driving. The question is not whether algorithm rotation will happen, it will. The upfront cost is low. Wrap your cryptographic primitives behind an interface, store algorithm identifiers alongside hashed values, version your key material. That is a few hundred lines of careful code. The retrofit cost is a multi-quarter migration under regulatory pressure. The math is not close.
Fourth, when you are hiring for a staff-level Python engineer role and you have done this, what is the single strongest positive signal you can get from a technical interview that you cannot get from a resume or a code sample?
The strongest signal is watching them update. Midway through a design discussion, I introduce a new piece of information that invalidates part of what they have already built. The traffic is 10 times what I first said, or the downstream service they assumed was internal turns out to be a third party. Weak candidates defend the design they have committed to because they experience the new information as an attack. Strong candidates visibly replan, they say, that changes things, and then they identify precisely which of their earlier decisions survive and which do not. A resume cannot show you that, and a code sample cannot either. Both are finished artifacts. The interview is the only place you get to watch someone's judgment move in real time, and how a person metabolizes being wrong mid-flight is the best predictor I know of how they will behave in an incident.
Fifth, platform roadmap sequencing. You are a staff engineer. The business wants 3 major platform bets simultaneously, and your platform can safely absorb one. How do you actually make that sequencing decision under genuine uncertainty, and what is the most common mistake you see leaders make in that situation?
I sequence by reversibility, not by expected value. The bet that is hardest to undo if it is wrong goes last. The bet that can be reversed or redirected cheaply if the business changes direction goes first. The most common mistake is sequencing by excitement. The shiniest bet goes first because leadership is enthusiastic, and then discovering 18 months later that the shiny bet locked in architectural decisions that block the other 2 bets entirely. Reversibility sequencing is slower feeling, but it preserves option value. And option value in a fast-moving business is worth more than any single correct bet.
6 and final rapid fire. The testing-induced design damage problem, when making code testable, actively makes it worse as a system. Ports and adapters taken too far in a monolith. Over-abstraction interfaces everywhere. Is this a real problem you have encountered, or is it an excuse that engineers who do not want to write tests use to avoid writing tests?
Both. It is a real problem and it is also used as an excuse. The distinguishing question is who is making the design decision and when. If a senior engineer is looking at an existing clean design and saying this design would need abstraction to be testable and that abstraction would make it worse, that is a real trade-off worth discussing. If a junior engineer is saying, I do not want to write an integration test, so I am going to abstract this database call behind an interface so I can mock it, that is usually the excuse. The tell is whether the abstraction has a name that means something in the domain. Use a database repository wrapping a database call is often an abstraction that exists solely for mocking and adds zero domain clarity.
That is a great note to move into the wrap-up on. Saket, before I ask you where people can find you, I want to give you the floor for a moment. If you were to distill the single most important thing from everything we have covered today, the internals, the security, the distributed systems failures, the organizational craft, what is the one mental model or disposition that you think separates engineers who are genuinely operating at a distinguished level from engineers who are technically very strong but still working below that level?
The disposition I would name is designing for your successor. I think of it as the inheritance test. Here is what I mean. Technically strong engineers design systems that they can operate. They hold a system in their head, the invariants, the sharp edges, the reasons behind every decision, and the system works because they are there. Distinguished level engineers design as if they are guaranteed not to be there. Every decision gets made as though the person inheriting the system will have only the artifacts, the documents, the alerts, the tests, the constraints encoded into the code itself, and none of the context in my head. That sounds like a documentation habit. It is not. It is a design forcing function that changes the engineering itself. If my successor has only the artifacts, then the idempotency reason has to live in a written key design document, not in my memory of an incident. That is the practice that came out of the disbursement failure I opened with. The ADR has to be wired to an operational trigger because I will not be there to remember that the decision had an expiry. That is the ADR Protein 14 lesson. The tenant isolation invariant has to be enforced by a CI fitness function because I will not be in every code review. That is the context var defense. Even the migration RFC from my warm-up story was at bottom, moving knowledge out of the heads of 5 senior engineers and into an artifact the whole organization could reason with. Run the inheritance test across everything we covered today and you will see it is the common thread. Every failure I described was a system depending on context that lived in someone's head, and every fix was moving that context into an artifact that enforces itself. That is what I would want hiring managers to hear. The value of 16 years is not that I hold more in my head. It is that I have learned to need to hold less, because I make the system itself carry the knowledge. An organization should want senior engineers whose absence is survivable, and that is the standard I hold my own designs to.
The inheritance test: design as if your absence is guaranteed and make the system carry the knowledge instead of your head. I'm going to be thinking about that framing for a while. Now, as promised, for the hiring managers and engineers watching who want to continue this conversation, where can people find you and what are you actually looking for in your next role?
The simplest path is through Clithia AI Labs. Reach out to the team here and they will make the introduction, and my profile is linked in the description of this video. As for what I am looking for, a platform where the failure modes are genuinely hard, high volume financial transactions, multi-tenant scale, the class of problems we spent today on, and an organization that wants a distinguished engineer to raise how it makes decisions, not just what it ships. Everything I described today about ADR governance, the inheritance test, and organizational craft, I want a place where that work is valued as engineering because it is. If that sounds like your team, I would genuinely love to talk. And Baul, thank you. This was the most rigorous conversation I have had in a long time, and I enjoyed every minute of it.
Saket, thank you. This was exactly the kind of session I hoped it would be: technically rigorous, honest about failure, and genuinely useful for everyone listening. Whether you are a hiring manager, a staff engineer, or someone preparing for your own distinguished level interview. If you are a hiring manager watching this and you want to talk to Saket, reach out to us at Clithia AI Labs and we will make the introduction. If you are an engineer who wants to get to this level, the roadmap is in everything Saket just described. Go deep on the failure modes, document your decisions, and invest in the organizational craft as seriously as you invest in the technical craft. Like this video if it gave you something. Subscribe if you want more sessions at this level, and leave a comment. Which part of today hit you hardest? The async internals, the context var vulnerability, the Saga taxonomy, or the ADR story? I genuinely read every comment. We will see you in the next one. Welcome back to the Clithia AI Labs Tech Interview Series, the show where we do not simulate interviews, we actually run them. I am Badu, Senior Technical Architect here at Clithia AI Labs, and today we have something I have been looking forward to for a while. Our guest today has 17 years of Python engineering behind him, not 17 years of writing Python scripts, 17 years of building production systems, leading platform teams, and apparently accumulating a very strong set of opinions about what good engineering actually looks like versus what it looks like on a resume. He is in the middle of a job change, which means everything you hear today is live ammunition. These are the exact questions he could face in a real loop next week. His name is Sakith, and we are going to cover CPython internals that go well past the GIL conversation, testing as a design discipline rather than a compliance checkbox, Python-specific security attack surfaces that most teams discover only after an incident, weight limiter mathematics, async performance diagnostics, and a handful of things that will be uncomfortable in the best possible way. This is a fellow-level mock interview. The questions are hard. The follow-ups are harder. And the goal is not to make Sakev look good or bad. The goal is to show you what this level of conversation actually sounds like, so that when you are sitting across from a staff or fellow interview panel, you have a real reference point. Saket, welcome to the show. Let us get into it.
Thanks, Balu. Yeah, genuinely looking forward to this. I will be honest, I find most mock interviews a little too polished, like everyone knows where the questions are going. I am hoping this one is messier than that.
It will be. Let us start with something that sounds simple but is actually a trap for people who know Python well enough to be overconfident. Here is the setup. You have a Python function, nothing fancy, that allocates a list of 1 million integers, does some light processing, and returns. You profile it, and you notice that the second invocation of that function is measurably faster than the first, and I am not talking about nanoseconds. I am talking about a difference that shows up clearly in a benchmark. A junior engineer on your team says it is the small integer cache. Python caches integers from -5 to 256, so the second call does not have to allocate those. That answer is partially correct, but it does not explain the magnitude of what you are seeing. What is actually happening at the CPython allocator level, and what does that tell you about how CPython manages object memory across function call boundaries?
Right, the junior engineer is not wrong, but they are explaining about 5% of the delta. The small integer cache is a constant time thing. Whether you have called the function once or 1,000 times, those cached integer objects are already allocated at interpreter's startup. That is not where the speedup is coming from. What is actually happening involves two separate mechanisms that compound each other. The first is CPython's memory allocator, pymalloc, and specifically its freelist behavior. When you allocate a list of 1 million integers and then the function returns and that list goes out of scope, CPython does not immediately return that memory to the OS. It holds those freed object slots in internal freelists. And one precision point that matters here, the million integer objects themselves go through pymalloc, but the list's packing array, a single allocation of roughly 8 megabytes, is far above pymaloc's 512 byte small object threshold, so it goes straight to the system allocator, where blibs plays the sim game and typically retains and reuses that block rather than returning it to the kernel. So on the second call, both allocation paths are handing you back memory that is already warm in the CPU's memory hierarchy in L2 or L3 cache rather than being fetched from main memory. That is the dominant effect you are seeing. The second mechanism, and this is the one people almost never mention, is how cheap CPython has made the call frame itself. On older releases, CPython kept a free list of dead frame objects and recycled them instead of paying the allocator on every call. From 3.lig in one word, it is even more aggressive. Frames live as plain structs on a contiguous per thread stack, and a full frame object only materializes if something like a traceback or a debugger asks for it. Either way, on the second call, the frame cost is close to zero and the memory it touches is already hot. When you combine warm pymalloc arenas with warm frame object reuse, the second call can be substantially faster than the first, even when the logical work is identical. Now, what does this tell you about how CPython manages memory across call boundaries? It tells you that CPython's allocator is explicitly optimizing for the pattern of allocate, use, free, allocate the same thing again, which is the dominant pattern in most application code. The system allocator, malloc and free at the OS level would cause fragmentation and cache pressure in that pattern. Pymalloc's arena and pool model sidesteps that at the cost of holding on to memory that looks leaked to external observers.
Good. Let me push on the multiprocessing angle here. If you fork a process that has already executed that function, so the parent process has warm free list, warm arenas, the whole picture, what does the child process inherit from that warm state and what does it not inherit? And is there a gotcha in that answer for someone running a Gunicorn pre-fork server model?
The fork inheritance question is subtle and genuinely important for production server design. When you fork, the child gets a copy on the right snapshot of the parent's entire virtual memory space, including pymalloc arenas, the free list state, all of it. So in terms of virtual address layout, the child starts with a warm allocator. That is actually the intentional design behind Gunicorn's pre-fork model. You import your Django or FastAPI PR application in the master process, which causes all your module level allocations to happen, and then you fork workers. The workers inherit that memory, and because of copy on write, if they only read shared objects like module level constants, compile the regex patterns, class definitions, they never actually cause a physical page copy. That is memory efficiency by design. The gotcha is, the moment a worker writes to any of those inherited pages, which happens the instant Python's reference counting touches an object, copy on write kicks in and the page is physically copied into the worker's private memory space. So the beautiful shared memory model degrades quickly once request processing starts. This is exactly why gc.freeze exists. Instagram's engineering team hit this at scale. The cyclic garbage collectors own bookkeeping rights to object headers, dirtying inherited pages even for objects the worker never logically touches. Calling gc.freeze in the master after imports moves every existing object into a permanent generation the collector never scans, which preserves the copy on write sharing dramatically longer. Reference counting still dirties pages on access. That part is unavoidable on the standard build, but freezing removes the biggest gratuitous source of page copies. The thing the child does not inherit in any meaningful operational sense is the freely swarming benefit for subsequent allocations. The child inherits the current free list state, but as soon as the first request allocates and frees objects, the free list in the child diverge from the parent. After a handful of requests, each worker has its own independent free list state. So the one cache benefit from the parent is a one-time inheritance, not a persistent advantage.
That copy and write and reference count interaction is something that trips up even experienced engineers. Let me move to the second warm-up question, and this one is more personal. I want you to describe a specific test you have written. Not a category of test, not a pattern you follow. A specific test that you are genuinely proud of, but not because it got a bug. I want you to describe a test where the act of writing it forced you to realize that the design of the code you were testing was wrong. Walk me through the friction you felt while writing the test, what that friction was actually telling you about the design, and what the code looked like after you acted on that feedback.
This one I can answer from a specific memory, which is the only way to answer it honestly. We had a notification service responsible for dispatching emails, push notifications, SMS, that kind of thing. The core of it was a class called notification dispatcher that took a notification object, figured out which channels were configured for the recipient, and dispatched to each channel. The logic was maybe 200 lines, and I was writing a test for the scenario where one channel fails partway through dispatching to multiple channels. Here is where the friction hit me. To test that scenario, my test setup was 30 lines before I even got to the assertion. I was instantiating the dispatcher mocking an email client, mocking an SMS client, mocking a push client, mocking the recipient preferences service, mocking the audit logger, and constructing a fake notification object with about 14 fields because the dispatcher accessed most of them directly. The setup was longer than the class I was testing, and I remember the specific feeling, not frustration exactly, more like suspicion. Why does testing a single failure path require me to construct this entire universe of fakes? The answer, once I sat with that question for about 20 minutes, was that the dispatcher was doing 3 completely different jobs. It was doing channel resolution, figuring out which channels to use. It was doing channel dispatch, actually calling the clients. And it was doing orchestration logic, deciding what to do when a subset of channels failed. Those three responsibilities were entangled in one object, which is why I needed to mock everything to test any one of them. Once I saw that, the refactor was obvious, split into a channel resolver, a set of single responsibility channel actors, and a dispatch orchestrator that only knew about the orchestration contract, not the channel implementations. After that split, the test for the failure scenario was 8 lines: create an orchestrator with 2 fake adapters, where one raises, assert the expected partial service behavior. No email client mock, no SMS mock, no preferences service mock. The test did not catch a bug, but it caught a design that would have made every future feature, adding a new channel, changing retry behavior, adding per channel rate limiting, harder than it needed to be.
That is a genuinely good answer because you named the exact fiction rather than describing it abstractly. One follow-up: there is always a moment in that situation where you consider fixing the test instead of fixing the design. Where did that moment come for you? And what made you choose the harder path?
Oh, the moment absolutely came. I had already written a version of the test that worked, 30 lines of setup, heavily mocked, it passed. And there was a real temptation to just commit it and move on because the test was technically correct. It verified the behavior I cared about. What made me choose the harder path was actually reading the test back to myself out loud, something I do when I am suspicious of my own code. And when I read that 30-line setup out loud, it sounded like I was describing the internals of the class rather than describing what the class was supposed to do from the outside. The test was coupled to implementation details that should not matter to any caller of that class. That is when I knew the test was not the problem. The test was just faithfully reflecting a design that had grown wrong. The practical thing that made the refactor feel safe was that I had the passing if ugly test as a regression harness. So I could refactor the design while keeping the original test passing and then replace it with the cleaner tests once the new structure was in place. The ugly test protected the refactor that eliminated the ugly test. I find that method useful to remember when people argue that bad tests are better than no tests.
Alright, we are moving into the deep dive. No more warm-up. Here is the security question. You're doing an architecture review for a fintech microservices platform. The platform has maybe 20 internal Python services. You find 2 of those services communicating by passing pickled Python objects through Redis pub/sub. The team lead walks you through it and says, look, these are internal services. They share the same trust boundary. The Redis instance has I2Arc enabled, it has TLS, and it is absolutely not reachable from outside our VPC. This is safe. I do not want the generic pickle is dangerous answer. I want you to walk me through the precise attack chain you are worried about, the specific sequence of events from initial compromise to impact, and then tell me what you would replace it with and what the actual engineering cost of that replacement is.
The team lead is conflating network perimeter security with trust boundary security, and that conflation is the specific mistake I need to address. Here is the attack chain. Step 1. An attacker finds a vulnerability in any one of those 20 internal services. Maybe an unpatched dependency, maybe a command injection in a configuration passing path, maybe a deserialized JWT with a weak secret. They get code execution inside service A. That is not exotic. It is a realistic compromise scenario for any sufficiently complex platform. Step 2. The attacker now has the network credentials and configuration of service A, including its Redis connection string. They can connect to that Redis instance because they are operating inside the VPC behind the TLS and ITARIC boundary the team lead just told me about. Redis ITARIX is now protecting them, not protecting the platform. Step 3. They publish a crafted pickle payload to the Redis pub/sub channel that service B is subscribed to. Because this reduced mud to Kokolo allows an attacker to embed arbitrary Python code that executes at deserialization time, before any application level validation, before any type checking. Service B deserializes the payload and executes the attacker's code with Service B's process privileges. Step 4. Now they have code execution in Service B. Service B might have database credentials for a different database, access to payment APIs, access to customer PII. The attacker has moved laterally from a compromised low-value service to a high-value one, and the entire Redis Artichoke and TLS investment did nothing to stop step 3. The specific thing the team lead got wrong is the definition of a trust boundary. A trust boundary is not inside the same VPC. A trust boundary is I can verify the integrity and authenticities of every message I receive, and receiving a malformed message cannot cause code execution. Pickle fails that definition catastrophically because the deserialization process is the execution. What I replace it with depends on the performance requirements. If throughput is the primary concern and the schema is stable protocol buffers via Protobuf, it is schema validated. By definition, you cannot embed executable code in a Protobuf message, and the serialization performance is excellent. If the team is more Python native and wants runtime flexibility, Pydantic validated JSON. Slightly higher serialization cost than Protobuf, but dramatically better developer experience for a Python shop, and you get schema enforcement at the boundary. The engineering cost of that replacement, you have to define schemas for every message type, which the team probably views as overhead, but is actually a forcing function for documenting your internal API contracts. For a 20-service platform, that is a week or two of work, not months. The ongoing cost is schema evolution, discipline, adding fields in a backward compatible way, versioning your messages. That discipline is cheap compared to the incident response cost of a lateral movement attack in a fintech platform.
I want to stay on deserialization but change the target, because pickle is not the only place this class of bug hides. Set aside the pickle story for a moment. You replace pickle with Pydantic validated JSON. The team is happy. They close the finding. 6 months later, a separate review finds that 3 services are using YAML.safeload to pass configuration payloads that arrive through an internal endpoint. The team's response is, we switched to safe Flask load specifically because we know YAML.load is dangerous. Safe load is the safe version. That's why it's called that. Is YAML.safeload actually safe? And I want the precise technical answer. What does safe load restrict at the parser level, and where does it still leave you exposed that the name implies it should not?
YAML.safeload is safer than YAML.load. It is not safe in an absolute sense, and the name is one of the more misleading names in the Python standard library ecosystem. Here is what safe etc_load restricts at the parser level. It restricts a set of YAML tags that can be deserialized. YAML.load with the default loader, or worse, with the full loader or unsafe loader, will process YAML tags like the Python object apply YAML tag, which allow you to deserialize arbitrary Python constructors. That is the well-known attack vector. You craft a YAML document that instantiates a subprocess.poofen with an attacker-controlled command, and YAML.load executes it. SafeRAD uses the safe loader, which only processes a restricted tags as standard YAML scalars, sequences, and mappings, no Python-specific tags. So you cannot use SafeRAD and or use SafeLoad to get direct code execution via Python object construction. That is real protection, and it is significant. Where does safe_load still leave you exposed? 3 places. First, algorithmic complexity attacks the billion laughs pattern. YAML supports anchors and aliases, and safe_load processes them. A maliciously crafted YAML document with deeply nested anchor references can expand exponentially in memory and time. You can craft a document that is a few kilobytes on the wire but causes gigabytes of memory allocation when passed. Safe_load does not protect against this. If the endpoint passing this YAML is reachable by any untrusted input, including internal services that might be passing through user-provided data, you have a denial of service surface. Second, you still have the dependency on the underlying libyaml-c parser, which has had memory corruption vulnerabilities historically. Safe_load reduces the Python-level attack surface but does not eliminate the parser-level C vulnerabilities. Third, the most practical one, safe_change, load on configuration payloads from an internal endpoint, is still expanding your attack surface in the lateral movement scenario we just discussed. If an attacker controls an upstream service, they control the YAML payload. They cannot get code execution via Python object construction, but they can craft YAML that passes to unexpected data types or structure, potentially manipulating configuration in ways the application does not expect. The real answer for configuration passing in a security-conscious platform: use JSON or TAML for configuration. AMS features at anchors, aliases, multi-document streams, type inference is a liability when you are consuming configuration from any endpoint, internal or external. The features that make YAML convenient for humans are the features that create attack surface when processed programmatically.
Good. The billion loves answer specifically is something most engineers miss. Let us shift gears to algorithms and distributed systems. You are building a rate limiter for a high-throughput FastAPI service. 50,000 requests per second across all tenants, multi-instance deployment, Redis as shared state. A senior engineer on the team proposes a fixed window counter, increment a Redis key per tenant, set a 1-second TTL, reject if the count exceeds the tenant's limit. I want you to walk me through the precise mathematical failure mode of fixed window with concrete numbers. Not it can burst at the boundary. I want actual numbers that illustrate why this is wrong. And then I want you to tell me the specific failure mode of sliding window lock, token bucket, and leaky bucket that the textbook presentation of each one tends to hide.
The fixed window failure with numbers. Suppose a tenant's limit is 1000 requests per second. The window resets at the top of each second, so at time 0, at time 1, at time 2. A well-behaved client sends 1000 requests spread across a second and everything is fine. Now consider this: a client sends 99 requests at time 0.99 seconds. Just before the window resets, they do not hit the limit. 1 millisecond later, at time 1.0 seconds, the window resets. They immediately send 999 more requests. In the span of approximately 2 milliseconds, they have sent 1908 requests against a limit of 1000. That is a 2x burst at every window boundary, and it is completely bypassable with a simple timed client. The fixed window counter has a hard mathematical guarantee of 2n requests in 2 epsilon time around every boundary. For a fintech API protecting payment endpoints, that burst profile is a real problem. Now the hidden failure modes of the alternatives: sliding window lock. The textbook presents this as the correct fix. You store a timestamp for every request in a sorted set in Redis and count entries within the last window. It is mathematically precise. The failure mode is memory. For a tenant allowed 10,000 requests per minute, you are potentially storing 10,000 timestamps in Redis per tenant. With 10,000 tenants, that is 100 million entries in Redis, and the sorted set operations are O awk log n. At 50,000 requests per second across all tenants, the Redis CPU cost of those sorted set operations becomes your bottleneck, not your application servers. The textbook shows you the correctness, it does not show you the capacity planning problem. Token bucket. The textbook presents this as efficient and bursty friendly by design. The hidden failure mode is thundering hard on burst allowance. Token bucket allows a burst up to the full bucket capacity. If you configure that fills at 1000 tokens per second with a max capacity of 5000, which is a common configuration to allow for legitimate traffic spikes, every tenant that has been idle for 5 seconds arrives with a full bucket and can fire 5000 requests instantaneously. If multiple tenants do this simultaneously, which happens when they all have the same cron schedule, or after a shared downstream dependency recovers from an outage, you get a synchronized burst that is n times your per tenant maximum, and your rate limiter is technically allowing it correctly. The failure is in the burst capacity design, not the algorithm, but the textbook presents it as purely a feature. Leaky bucket. The textbook presents this as smoothing traffic and preventing burst. The hidden failure mode is unfairness under uneven load. Leaky bucket processes requests at a fixed rate. If you have tenants with wildly different traffic patterns, one tenant doing high-frequency small requests and another doing infrequent large batches, they compete for the same train rate. A tenant with a legitimate low-rate steady stream can be starved if a bursty tenant fills the queue ahead of them. The leaky bucket's fairness depends entirely on your queue management strategy, which the textbook rarely discusses. In practice, for the Redis back multi-tenant scenario you described, I would reach for a sliding window counter, not sliding window log. It is a hybrid. You keep two fixed window counters, one for the current window and one for the previous window, and estimate the current rate as a weighted sum. It is await 1 in Redis operations. It is close enough to mathematically correct for most production requirements, and it does not have the memory scaling problem of the sliding window log. The trade-off is a small approximation error at the window boundary, which is acceptable when you are not in a regulatory environment that requires exact counting.
The sliding window counter as the pragmatic hybrid is the right answer there, and most candidates stop at token bucket. One follow-up, you choose to implement this with Redis. Walk me through verbally, not pseudocode, the Lua script you would use for the atomic increment and check, and explain specifically why you need Lua rather than a multi-exec transaction.
The reason you need Lua rather than multi-exec is a subtle but important Redis concurrency point. Multi-exec gives you a transaction in the sense that the commands execute sequentially without interleaving with other client's commands. But here is the thing. Multi-exec does not give you conditional execution based on the result of a command within the transaction. You cannot do read the current count, decide whether to increment or reject, and then increment all atomically using multi-exec. Multi-exec use commands without executing them until exec, so you cannot use the result of a JIT set to conditionally branch within the same transaction block. Lua scripts run atomically in the Redis single-threaded executor. The entire script executes as a single atomic unit. No other command from any other client can execute between any two statements in your Lua script. That gives you read then conditionally write atomicity, which is exactly what rate limiting requires. The Lua script for a sliding window counter, you take two arguments, the current window key, the previous window key. You take a third argument, the current position within the window as a fraction between 0 and 1 computed by the caller. You GX both window counters. You compute their estimated current rate as previous window count multiplied by 1 minus the current window fraction plus the current window count. If that estimated count is already at or above the limit, you return a rejection signal without incrementing. If it is below the limit, you INCR the current window key, and if the key did not exist before, meaning it is a new window, you set its TTL to 2 times the window size, so both the current and previous window data are available during the overlap period. Then you return an approval signal with the current count. The key operations are all happening inside a single Lua execution context, so the check and the increment are genuinely atomic. The alternative, using a watch multi-exec optimistic locking approach, would work but requires retry logic on the client and creates significantly more round trips to Redis under contention, which is exactly the scenario you want to optimize for in a high throughput rate limiter.
Solid. Now let us talk about async performance diagnosis. This is one of those areas where I find even very experienced Python engineers have gaps because the tooling is immature compared to synchronous profiling. You have a FastAPI service doing heavy ISing SQL outcome, Redis, some external HTTP calls. You profile it under load and find that P99 latency is roughly 10 times P50 latency. The P50 is completely acceptable. You pull distributed traces and notice something specific. The long tail requests are not slow because of slow individual ISO operations. The individual awaits are fast. The latency is accumulating in the gaps between awaits. Without any more information from me, give me the 3 most likely causes of that specific symptom. Latency accumulating between awaits, not within them, and rank them by how often you have personally seen each one in production.
I have seen this pattern specifically, and it is one of the more frustrating async performance problems because the traces look misleading. Everything appears fast, but the request is slow. Ranked by frequency in my own production experience number 1, and by a significant margin, synchronous code running inside async functions, blocking the event loop between awaits. This is the most common by far. Someone wrote JSON.dumps on a large object or called a third-party library that does synchronous file IO, or the one that kills me every time I find it. Use the request library inside an async function because someone was in a hurry and did not want to switch to HTTPX. The event loop is single-threaded. Synchronous blocking code pauses the entire loop. Every other coroutine that is ready to resume is waiting. The latency shows up as a gap between the awaits that bracket the blocking call, and if the blocking call is inside a hot path that runs on every request, you get exactly the P99 spread you described. Most requests happen to not hit the slow path on that iteration, but the unlucky ones that do accumulate the full blocking delay. Number 2. Connection pool exhaustion. The way this manifests in traces is specifically deceptive. A coroutine reaches an await that is supposed to issue a database query, but before it can issue the query, it has to acquire a connection from the pool. If the pool is exhausted, all connections are in use by other coroutines. The coroutine awaits for a pool slot. In a well-instrumented place, you might see this as a distinct span. In a less instrumented service, it looks like a slow database call. When the database is actually fine, it is the pool wait that is slow. I have seen this in production where a connection pool of 10 connections was serving a service that was receiving 200 concurrent requests. P50 was fast because most requests got a pool slot immediately. P99 was terrible because the unlucky requests were waiting in a pool queue behind 90 others. Number 3. Event loop fairness and callback queue depth. When many coroutines become runnable simultaneously, for example, after a batch of IO operations complete at nearly the same time, they all enter the event loop's runnable queue. The event loop processes them in order, and fair scheduling means every coroutine waits its turn. If you have 100 coroutines all becoming runnable within a millisecond of each other, the ones at the end of the queue experience meaningful scheduling latency before they are resumed. This is less common than the first two, but it shows up specifically when you have high concurrency and bursty IO completion patterns, like when a Redis pipeline returns a batch of results and all the coroutines waiting on those results become runnable simultaneously.
For cause number 1, synchronous blocking code inside async functions, walk me through your actual diagnostic process. Not I would profile it as an abstract statement, the specific tool, the specific metric you look for, the specific threshold that tells you have found it.
Specific tooling, specific thresholds. First instrument, and it is built into the runtime asynchronous debug mode. Enable loop.set as per debug, and the loop logs every callback or task step that holds it longer than slow as per correct, duration 100 milliseconds by default, and tunable. That is the zero dependency first pass. For a running production process, I pair it with IO monitor or a custom event loop watchdog, a background thread that samples the loop's last known execution time at a fixed interval, say every 50 milliseconds. If the loop has not yielded control for longer than a threshold, I use 100 milliseconds as my worth investigating threshold and 500 milliseconds as my this is a production problem threshold. The watchdog loves a stack trace of the currently executing coroutine. That stack trace tells me exactly where the event loop was blocked. This is the most direct instrument. If I want more granular profiling without a watchdog, I use PySpy, SpyTop or PySpy record with the non-blocking flag. PySpy is a sampling profiler that attaches to a running process without requiring code modification. What I look for in the PySpy output is call stacks that show up with high self-time in functions that should not have high self-time. Things like json.loads, re.compile, ued.uid4 if you are calling it in a tight loop, synchronous socket operations. Any function in a hot async path that has non-trivial CPU self-time is a candidate for causing event loop stalls. The third instrument, and this one is specific to finding third-party library culprits, is monkey patching the built-in socket operations with a wrapper that records call time and raises if called from the event loop thread. You can do this with the PyTest fixture for load test, passsocket.socket.connect to log a warning with the stack trace if the calling thread is the event loop thread. This specifically catches the case where someone is using a synchronous HTTP client or synchronous DNS resolution inside async code. The threshold that tells me I have definitively found the problem if the watchdog fires more than twice per minute under moderate load and the stack traces all point to the same function, I have found the blocker. A single fire might be noise, a GC pause, an OS scheduling artifact. Repeated fires pointing to the same code path is a confirmed diagnosis.
Let us talk about testing philosophy at a senior level. I want to move to property-based testing and mutation testing. You need to convince a team of 12 engineers, experienced engineers, skeptical of new tooling, already operating under delivery pressure, to adopt hypotheses for property-based testing, not as a curiosity or a side project, but as a genuine part of their testing practice for a financial transaction processing system. These engineers have high unit test coverage already. They believe their test suite is good. Before you give me a pitch, I want you to tell me, what is the specific category of bug that property-based testing finds that high unit test coverage almost never finds? And can you give me a concrete example of a property that you would write for a financial amount rounding function that would expose a correctness error that a conventional example-based test would be unlikely to generate?
The specific category of bug that property-based testing finds and high unit test coverage almost never finds. Boundary interactions between your assumptions. Unit tests are hypothesis tests written by the same engineer who wrote the code. They test the inputs that the engineer imagined when writing the function. They are excellent at verifying that the function behaves correctly for representative inputs. What they almost never do is find the inputs that violate the mathematical properties the function implicitly claims to satisfy because the engineer did not know those properties could be violated. For a financial amount rounding function, let me give you a concrete example. Suppose the function takes a decimal amount, a currency code, and rounds to the appropriate number of decimal places for that currency, 2 for USD, 0 for JPY, 3 for KWD. A conventional test suite will have tests like round 10.456 USD to 10.46, round 100.5 JPY to 100 or 101, defined 12.34 KWD to 5.223. Those tests are all correct and they all pass 0.434. Now here is a property I would write with hypothesis for any amount A rounded to currency precision and any amount B rounded to the same currency precision. The sum of the rounded amounts should equal the rounded sum within the maximum possible rounding error for that currency. Formally, round A plus round B should differ from round A plus B by at most 1 unit of currency precision. This is the distributive over addition property of rounding. Hypothesis will search the space of decimal inputs and find you a case like A equals 0.05 and B equals 0.05 in USD, where round 0.05.05.0 serve the rotsotsu using round half up, but round 0.0.0 serve.05.05.01. That is a 1 cent discrepancy, and it is a correctness error that matters for reconciliation in a financial system. No example-based test would likely generate that specific pair of inputs because the engineer who wrote the test was thinking about individual rounding correctness, not compositional correctness. The broader pattern, unit tests verify individual behavior. Property-based tests verify the mathematical relationships between behaviors across the full input space. In financial systems, those mathematical relationships, commutativity, associativity, idempotency of operations, are the actual correctness requirements, and they are the ones most likely to have edge cases. For the pitch to the skeptical team, I would not say, let us replace your unit test with hypothesis. I would say, your unit tests tell you the function works for the inputs you thought of. Hypothesis tells you the function satisfies the properties you intended it to have. And for financial transaction processing, the properties are the specification. I would start with one property per critical function, just one. Show them what hypothesis finds in the first week. Let the findings make the argument.
That rounding example is going to resonate with a lot of fintech engineers listening to this. Let me give you a question that spans the JavaScript world. Because Python engineers at the fellow level often need to reason about polyglot systems, this is a design question, not a trivia question. You are building a real-time financial dashboard. The front end is a React SPA consuming a Python FastAPI backend via WebSockets. The backend is pushing live trade data updates, potentially hundreds of updates per second during peak market hours. The front-end team proposes using a naive approach, render every message that arrives on the WebSocket, directly updating React state with each incoming event. You know this will fail under production law. Walk me through the specific failure mode at the browser level. Not just it will be slow, but the precise mechanism, and then describe the architecture you would actually build with the trade-off decisions you would make explicitly.
The specific failure mechanism at the browser level has two compounding parts. First, React's rendering model. Every time you call setState or dispatch to a use reducer, React schedules a re-render. If you are receiving 200 WebSocket messages per second and each one calls setState directly, you are scheduling 200 re-renders per second. The browser has a rendering budget tied to its refresh rate, typically 60 frames per second, which gives you about 16.7 milliseconds per frame. React 18's automatic batching does help. Unlike React 17, it batches state updates even in native callbacks like WebSocket handlers. But batching only merges updates that land in the same task. 200 messages per second arrive as 200 separate event loop tasks, so batching has nothing to merge. You still get up to 200 distinct rendered passes per second. Second, the DOM diff and paint cost. Even if React batches some of those updates, each render cycle performs a virtual DOM reconciliation against the previous render tree. For a financial dashboard with dozens of rows of trade data, each reconciliation walk is non-trivial. If reconciliation plus layout plus paint takes 8 milliseconds, which is reasonable for a complex component tree, and you are attempting 200 renders per second, you are asking for 600 milliseconds of work per second in a 1000 millisecond budget. The browser's main thread saturates, you get dropped frames, frozen UI, unresponsive input. The tab may eventually crash or trigger the browser's slow script warning. The architecture I would actually build: decouple the data ingestion rate from the render rate. The pattern is message accumulation with time-based flush. On the front end, maintain an in-memory message buffer, just a mutable reference, not React state, that accumulates incoming WebSocket messages. Set up a request animation frame loop or a set interval at 30 to 60 milliseconds, the render cadence you want, not the data arrival cadence. On each tick of that timer, drain the buffer into React state in a single batched update. React 18's automatic batching handles this beautifully: one set state call with the accumulated state change, one render pass, one paint. You go from 200 render attempts per second to 30 render attempts per second, regardless of WebSocket throughput. On the backend, and this is where the Python side matters, you need to be thoughtful about what you push over the WebSocket. Do not push every tick for every instrument. Push deltas. If a trade price has not changed, do not send it. Use server-side state to track what has been sent and only push genuinely new data. This reduces the front-end's problem space from handle everything to handle changes. The trade-off I make explicitly: the buffer accumulation approach means a maximum display latency of your flush interval, 30 to 60 milliseconds. For a live trading dashboard, that is acceptable. If you are building a high-frequency trading terminal where millisecond latency on display matters, you would need a different approach. Probably a WebGL-based renderer that bypasses the DOM entirely. But for a financial dashboard showing portfolio positions and recent trades, 30 ms display latency is invisible to humans and the smoothness improvement is dramatic. The second explicit trade-off: server-side delta computation adds state to the backend. Each connected client now has associated server-side state tracking, what was last sent. You need to handle connection drops and reconnects. When a client reconnects, do you send a full snapshot or resume from the last sequence number? I would design for snapshot on reconnect, sequence number for in-session delta tracking, with a short reconnection window where you can resume from sequence without a full snapshot.
The request animation frame buffer flush is an elegant solution, and I like that you explicitly called out the latency trade-off rather than presenting it as purely a win. One more deep dive question before we move to war stories. This one is Java and distributed systems, specifically about the correctness guarantees engineers assume they have but often do not. You are reviewing a Java microservice that implements the Saga pattern for a multi-step order processing flow, reserve inventory, charge payment, notify fulfillment. The team has compensation transactions for each step. The engineering lead says, "We are covered. If payment fails, we have a compensation transaction to unreserved inventory. If fulfillment notification fails, we compensate payment and inventory." The Saga handles all failure scenarios. You know there is a specific correctness gap they have not thought about. Without me telling you what it is, walk me through the precise scenario where their Saga implementation can produce an incorrect final state despite the compensation transactions executing correctly, and what the actual fix looks like.
The gap in their model is isolation. Sagas give up the I in a seed and the team is reasoning as if they still have it. Here is the scenario with their exact flow. Step 1. Reserve inventory for order 12354 succeeds. Step 2. Charge payment fails. Transient processor error. The Saga coordinator does exactly what it was designed to do. It runs the compensation and unreserves the inventory. Every step behaved correctly. Every compensation executed correctly, and the system can still end up in an incorrect final state. Because between the reservation and the compensation, the intermediate state was visible to the rest of the system and the rest of the system acted on it. Concretely, while order 12345 held a reservation, the inventory service reported that unit as unavailable. A second customer's order for the last unit in stock was rejected. A real lost sale caused by a transaction that from the Saga's point of view never happened. Run the same anomaly in the other direction and it is worse. A pricing or promotion service reads the payment captured state mid-Saga, counts the order toward a volume discount tier and issues a discount code, and when the Saga compensates, nobody claws the discount back because the discount was issued by a service that is not even a participant in the Saga. In database terms, these are dirty reads. A local transaction would have prevented them with isolation. A Saga exposes every intermediate state as committed, readable, actionable truth. The team's phrase, "the Saga handles all failure scenarios," is true only about the Saga's own steps. It says nothing about every other reader in the system observing the Saga mid-flight. The actual fix is a set of countermeasures, and which ones you deploy is a design decision per step. First, semantic locking. Intermediate states get their own explicit names. Inventory is not reserved, it is pending order 12354, and every reader is required to decide visibly in code review how it treats pending states. That single chain surfaces most of the dirty decisions that were previously implicit. Second, commutative and compensable by design updates. Where possible, express steps as operations that tolerate reordering, increments and decrements against available to promise counts rather than absolute rights. So a compensation composes correctly with whatever happened in between. Third, reorder the Saga by risk. Put the steps most likely to fail earliest and the steps whose intermediate visibility is most dangerous as late as possible. So the window where dirty reads can do damage is as short as the flow allows. And fourth, for the readers, you cannot fix external services, analytics, anything downstream of an event stream, publish Saga completion events distinctly from step events, and make anything with financial consequences, key of completion, never of steps. The principle underneath a Saga is not a transaction that happens to be distributed. It is a workflow whose every intermediate state is public. Design each state as if the whole company can see it, because it can.
The isolation gap. Every intermediate state is public. That reframe from transaction to workflow is the one I want people to take away from this segment, which is a perfect transition into our stories. I want to hear about a specific incident or system failure from your career where your initial diagnosis was confidently wrong. Not uncertain, but specifically wrong in a way that cost time or caused additional harm, and what the actual root cause turned out to be. What did that experience change about how you approach incident diagnosis?
There is one incident I think about specifically whenever I am in the early stages of a production investigation, because it is the clearest example of confident wrongness I have experienced. We had a data pipeline service, Python salary workers PostgreSQL, that was processing financial reconciliation batches. Once a day, end of business, it would process roughly 2 million transaction records and write summaries to the database. One day, the pipeline started running 4 times slower than its historical average. Not slower by 10%, 4 times slower. And it had been working fine for months. My immediate diagnosis, and I said this in the incident channel with some confidence, was database I/O. 4 times slower on a write-heavy pipeline. Recent deployment that included a schema change adding a new index. I was certain it was the index. I was already drafting the explanation to the team about index maintenance overhead during bulk inserts. I spent 40 minutes analyzing query plans, checking index fragmentation, comparing write throughput metrics before and after the deployment. Everything looked normal. The database was not the bottleneck. I was looking in the wrong place with complete confidence. The actual root cause, a developer had added a call to an external currency conversion API inside the per record processing do needed for a legitimate feature to normalize all amounts to USD. The API was rate limited to 10 requests per second. With 2 million records, each requiring a currency check, the pipeline was now spending the vast majority of its time sleeping in late limit backoff. The wall clock time was dominated by network I/O and sleep intervals, not database I/O. What I had done wrong, I anchored on the most recent change I knew about, the schema migration, and built a causal story around it before I had looked at the evidence. The actual change that caused the slowdown was in application code, not infrastructure, and it was in a feature branch that had been merged quietly 2 days before the symptoms appeared. I had not looked at the application level changes because I was certain the database was the answer. What changed in my incident diagnosis process? I now have a rule: do not name a cause in a public channel until you have at least one positive piece of evidence that implicates it, not just the absence of evidence against it. The database looked fine, but I had not actually found evidence that pointed to application code before I was certain it was infrastructure. The new rule forces me to ask, what evidence do I have that points toward this hypothesis, rather than what evidence do I have against other hypotheses? It sounds obvious in retrospect. I needed a production incident to make it a genuine behavior habit.
The anchoring bias in incident diagnosis is something that experienced engineers are actually more vulnerable to, not less, because you have more prior incidents to anchor on. That is a really honest story. Here is a different kind of war story question. Tell me about a time when you had to make a technical architectural decision under genuine time pressure and incomplete information, where you knew you did not have all the data you wanted, but the business could not wait for you to get it. What was the decision? What information were you missing that you wish you had? And in hindsight, was the decision correct or was it lucky?
This one requires me to be honest about the difference between a good decision and a lucky outcome. We were 2 weeks from a regulatory deadline, a specific financial reporting requirement with real penalty exposure for late delivery. The system that needed to generate the report was a legacy Python service 8 years old that had never been designed for the report volume this regulation required. The report needed to join across 6 database tables, apply roughly 40 business rules, and produce an auditable output for about 3 million customer records. The decision I had to make: do we extend the existing service, which I knew from reading the codebase was fragile, had no test coverage on the critical path, and was using a database ORM pattern that would make a 3 million record query catastrophic? Or do we build a parallel path, extract the data to a reporting database, run the business logic there, and produce the report output independently of the production service? The information I did not have, the actual performance characteristics of the legacy service under the required load. I had read the code and formed a strong opinion that it would not survive, but I had not load tested it. I also did not have a reliable estimate of how long the parallel path would take to build safely. The engineer I would have assigned was on leave, and I was estimating with a team I had not worked closely with. I chose the parallel path. The reasoning, the known risk of the legacy service failing in production 2 weeks before a regulatory deadline was worse than the known risk of the parallel path being imperfect because a failed report output could be corrected and resubmitted, while a production outage from overloading the legacy service might affect live customer operations and create a worse compliance situation. In hindsight, the parallel path worked. We delivered on time, the regulatory requirement was met. But was the decision correct or lucky? Honestly, both. The decision logic was sound, but I got lucky on two things. The legacy service, which I had predicted would fail under load, did not actually fail when we ran a partial test against it. It was slower than required but not broken. If I had known that, I might have chosen the less risky path of patching the existing service, and the replacement engineer who stepped up to own the parallel path implementation was better than I had estimated. If either of those things had gone differently, my decision would have been wrong in a way that the post-mortem would have found. The lesson I carry from it under time pressure, the decision logic you can articulate and defend is your protection. The outcome does not validate the logic retroactively. I made the best call I could with the information I had, and I should be able to say that regardless of whether it worked out, the alternative waiting for more information was not actually available. Not deciding was itself a decision to run the risk on the legacy service, so I chose the risk I could manage. That discipline, choosing which risk to run rather than avoiding the decision, is what time pressure architectural decisions actually require.
I love the honest accounting of luck versus decision quality there. Alright, we are going into an rapid fire. These are shorter, opinionated, sometimes deliberately provocative. I want your honest answer, not the safe answer. Ready?
Ready. Go.
First one. Test coverage percentage as a hiring signal. If a candidate presents a project with 94% test coverage and you look at the tests and they are all mocking the interesting things, is that better or worse than a project with 60% coverage and no mocks?
Worse. Significantly worse. 94% coverage with strategic mocking is a false confidence generator. It tells me the engineer has learned to satisfy the metric without satisfying the underlying goal. 60% with honest integration style test at least gives me real signal about whether the system actually works. I would take honest incompleteness over confident theater.
Or take Python type hints at runtime PR from future, import, annotations, genuine engineering value or annotation, theater.
Genuine value, but only if you are running myPR right in your CI pipeline with strict mode enabled. Without static analysis enforcing the annotations, type hints are documentation that can drift. The moment they can be wrong without consequence, they will eventually be wrong, and then they are worse than no annotations because they create false confidence. The runtime import is actually a performance optimization I support. Deferred evaluation of annotations reduces import time, but it only matters if the annotations are being used for something other than documentation.
You inherit a Python codebase that has no tests, no type hints, no documentation, but it has been running in production without incident for 4 years. Your engineer manager says, we need to modernize it. What is the first thing you actually do?
Before I write a single line of new code or a single test, I spend a week reading it and writing down every assumption I think the code is making about its inputs, its environment, and its callers. The most dangerous thing in a legacy code base is the assumptions you do not know exist. I have seen modernization projects break 4-year stable systems in the first week because an engineer added input validation that rejected an edge case the legacy code was silently handling. You have to find the implied contracts before you can safely add explicit ones.
Most overrated Python library in the ecosystem right now. One that gets more credit than it deserves, and your honest reason.
I will say Celery and I will defend it. Celery is not a bad library, it is a genuinely useful one. But it is routinely deployed as if it provides transactional task delivery guarantees that it explicitly does not guarantee. The number of production systems I have reviewed where Celita's success is treated as application level correctness evidence And there is no independent confirmation that the work the task was supposed to do actually completed correctly is too high. Salary gets credit for being a task queue when it is actually a best effort task dispatcher. The gap between those two descriptions represents a lot of silent data loss in production systems.
You are doing a technical interview for a staff Python engineer role. You have 1 hour. What is the single exercise or question you have found most reliably separates engineers who understand distributed systems failure modes from engineers who have only read about them?
I asked them to design the retry logic for a payment charge API call and walk me through every scenario where a retry is wrong, not just dangerous, but specifically wrong in a way that produces an incorrect outcome for the customer. Engineers who have only read about distributed systems will say make it idempotent. Engineers who have operated production payment systems will tell me about the specific scenario where idempotency key generation itself has a race condition, or where the payment processor returns idempotency key collision errors, or where a retry on a timeout causes 2 successful charges because the timeout was on the response, not the operation. The depth of specific wrong scenarios is the signal.
Last rapid fire, 17 years in. Is there a class of problem where you genuinely think a less experienced engineer, say 5 years in, would make a better architectural decision than you, not because they are faster or more current with tooling, but because of something specific they have that you do not?
Yes, and I think about this often. A 5-year engineer who has worked primarily in cloud-native environments and has never built a system that needed to survive beyond 5 years of operation has a genuine advantage in greenfield architecture that does not require longevity assumptions. They will not over-engineer for failure modes that this specific system at this specific scale will never encounter. They will not add distributed transaction patterns because they once fought a consistency bug. They will add them only when the current system requires it. Experienced engineers carry the scars of specific systems. Those scars are valuable, but they can also cause you to treat every new system as if it has the failure modes of every system you have survived. The best architectural decisions I have seen from junior to mid engineers come from engineers who are not scared of anything yet, and there is a specific class of simple system where the unscared decision is the right one. My job is to have enough self-awareness to recognize when I am adding complexity because the system needs it versus because a previous system punished me for not having it.
That self-awareness about scar tissue is a strong note to end the rapid fire on. Saket, let us land these 2 things before we close. First, the thread I noticed running through this entire conversation, and I want to hand it to you to make explicit, the test that was painful to write, the diagnosis that felt certain and was wrong, the textbook algorithm that hid its own operational cost. There is a pattern in how you treat those moments. Name it for the audience. After 17 years, what is the discipline underneath all of that?
The discipline is friction is data. Treat resistance as information, not as an obstacle. Every story I told today has that shape. The 30-line test setup was not a testing problem to push through. It was the design telling me it had 3 entangled responsibilities and the friction was the only honest reviewer in the room. The reconciliation incident went wrong precisely because the diagnosis had no friction. The index story was easy, it fit the last change I knew about, and easy should have been the warning. The rate limiter question is the same lesson from the other side. Every textbook algorithm reads as frictionless, and the friction the textbook removed, the memory bill, the synchronized burst, the fairness under uneven load is exactly where production will present the invoice. Engineers are trained to treat friction as something to eliminate, make the test easier to write, make the diagnosis faster, pick the algorithm with the cleanest description. 17 years in, I have learned to pause at friction and ask what it is telling me before I remove it. Sometimes it is incidental and you sand it down. But when the friction is structural, when the code resists testing, when the evidence resists your favorite hypothesis, when the design only works if everyone is careful, removing the friction without reading it first is how you ship the failure 6 months downstream. So if I compress 17 years into one sentence for the engineers watching, The things that fight you are trying to tell you something, and the skill is learning to listen before you win the fight.
Friction is data. Listen before you win the fight. That is going on a wall somewhere. Second thing, and then I will let you go. You are in the middle of a job change. We said at the top that everything today is live ammunition. So, what kind of room are you looking to walk into next, and how should people reach you?
I am looking for a platform engineering room. Somewhere the problems look like the middle hour of this conversation, correctness under concurrency, security boundaries that are actually reasoned about, rather than inherited systems where the cost of being wrong is measured in money and trust, fellow or principal scope, and honestly, a team that argues well, a place where the friction I just described is treated as signal by more people than just me. The easiest way to reach me is through Cryptia AI Labs. The team here will make the introduction and the links are in the description. And Belu, thank you for this. You promised the follow-ups would be harder than the questions and you kept your word. This is the closest thing to a real loop I have done on camera and it was genuinely fun.
Sakesh, thank you. 17 years and it showed not in the answers being polished, but in the answers being specific. The pickle attack chain walked step by step, the rate limiter mathematics with actual numbers, the saga isolation gap that most teams meet for the first time in an incident review, and a war story where the expert was confidently wrong and said so on the record. That last one is rarer than any of the technical depth. If you are hiring at the staff, principal or fellow level and today's conversation sounded like your problems, reach out to us at Cryptia AI Labs and we will connect you with Saket directly. And to everyone watching, this is the Cryptia AI Labs Tech Interview Series. If this sharpened how you think, like the video and subscribe. The full mock interview playlist is linked in the description with sessions across senior, staff and distinguished levels. Drop a comment with the question you would have answered differently and defend it, because we read everyone and the best pushback shapes the next episode. We will see you in the next one. Welcome back to the Cryptia AI Labs Tech Interview Series, the show where engineers grow, learn and get hired. I am Balu, Senior Technical Architect at Cryptia AI Labs, and today we are doing something I have been genuinely looking forward to. We have a VP Engineering level Python mock interview on the table. Our guest today has 18 years of Python engineering behind him. Not 18 years of writing scripts, but 18 years of building production systems, leading teams, debugging things that should not have broken, and making architectural decisions under pressure. Now, before I bring him in, let me tell you what today is not. This is not a trivia contest. I am not going to ask Saket what the GIL is or to recite the difference between a list and a tuple. If you want that episode, there are about 4,000 of them on YouTube. What we are doing today is simulating the kind of conversation that actually happens in a VP engineering panel, where the interviewer already assumes you know the basics and wants to find out how you think, how you reason through ambiguity, and whether your mental models survive contact with production reality. So if you are a senior engineer eyeing a principal or staff role, or you are a staff engineer thinking about the VP track, this episode is your dress rehearsal. Watch how Saket thinks out loud. That is where the real value lives. Alright, Saket, welcome to the show.
Thanks, Balu. Genuinely glad to be here, and I appreciate the framing. The best interviews I have ever had and the best ones I have ever given started exactly the way you described, not with trivia, with a scenario that has no clean answer.
Perfect. Let us set the stage quickly. 18 years is a long career arc in any language, but Python specifically has changed enormously in that time. Give me the 30-second version, not your resume, but the version that tells me how your relationship with Python has evolved. What does Python mean to you at year 18 that it absolutely did not mean at year 2?
At year 2, Python was a productivity tool. I reached for it because it got things done fast. The syntax felt natural, the ecosystem was rich, and I could build something real in an afternoon. That was the whole relationship. It was a means to an end. At year 18, Python is a system I have developed a genuine critical relationship with. I understand its choices. I understand why the GL exists even if I sometimes wish it did not. I understand the cost of its dynamism. I have seen what happens when you build something at Instagram scale on top of a language that was designed for expressiveness first and performance second, and I have deep respect for the engineering that keeps that working. But the more honest answer to your question is this: at year 2, I trusted Python. At year 18, I understand it, which is different. Trust is unconditional. Understanding is what lets you make good architectural decisions.
That is a really clean distinction. Trust versus understanding. I want to hold on to that because it is going to come up again in some of the later questions. Alright, let us get into the first technical question. And I'm going to start with something that is live in production in Python 3.12, but that very few people have actually reasoned about from first principles. Python 3.12 shipped immortal objects via P683, objects whose reference counts are intentionally never modified. Before I ask you what you think of the implementation, I want you to tell me what problem was PEP 683 actually solving. Not the problem it states in its abstract, but the operational problem that motivated it. And specifically, why did that problem become urgent at the scale Python is running at inside companies like Meta and Instagram?
Okay, so the documentation answer, which is not the answer you want, is something like immortal objects enable safer sub-interpret semantics and pave the road toward the free-threaded builds in 3.13. And that is true. But it is not the reason this work got prioritized with the urgency it did. The operational problem is copy on write page dirtying in multi-process Python servers. Let me walk through that carefully because the mechanism matters. When you run Python under a prefork server model, Gunicorn with the sync or gthread worker USGI, Celery with the prefork pool, what you are doing is forking a parent process into an worker process after the application has been loaded into memory. The entire point of that architecture is that the workers share the parent's memory pages where copy on write. The OS says, I will not actually copy this memory until a worker tries to write to it. So your code objects, your imported modules, your interned strings, they are physically shared across all your workers. One copy in RAM and processes using it. That is the memory efficiency story. Now here is where the reference count comes in. Every time Python touches an object, even just to read it, the runtime increments and decrements its reference count. That reference count is stored on the object itself as a field in the PyObject struct. So the moment any worker reads a shared object like none or true or the integer 0 or a commonly used string, the reference count field changes, and that tiny one field update marks the memory page as dirty. The OS has to make a private copy of that page for that worker process. At Instagram scale, they published numbers on this in their engineering blog. This was not a trivial cost. You have hundreds of worker processes, each one dirtying pages that contain objects they never logically modified. The working set of each worker process grows meaningfully because of reference count churn on singleton objects that everyone uses. You are paying a real RSS cost for a bookkeeping operation, so what PP683 does is designate certain objects as immortal. The reference counts are pinned and never modified. The objects that make sense as immortal are exactly the ones you want to share. None, true, false, small integers, interned strings, and the fundamental type objects. Now workers can read these objects without dirtying the pages they live on. Copy on write semantics are actually preserved for the objects that matter. The subinterpreter and free threading angle is the design motivation, but the urgency was operational. Instagram was running millions of requests per second on Python and paying for reference count churn with memory.
That is exactly the answer I was looking for. You went straight to the page dirtying mechanism. Let me push on the trade-off side of this. Immortal objects never get freed. What does that imply for the cyclic garbage collectors accounting? Does the GC need to visit immortal objects at all?
No, and this is actually an important optimization that falls out of immortality almost for free. The cyclic garbage collector in CPython exists to catch reference cycles that simple reference counting cannot resolve. It does this by traversing the object graph looking for groups of objects that are only reachable from each other, but immortal objects, by definition, are never going to be candidates for collection. Their ref count will never reach 0 through the normal path, and they are not going to form cycles that need resolving because they are carefully chosen to be simple, non-container singletons or fundamental types. So the GC can, and in the 3.22 implementation does, skip immortal objects during its traversal, which means that as the set of immortal objects grows, the GC's work per cycle shrinks slightly. You get a secondary performance benefit on top of the copy on write benefit. The accounting risk is the thing you do want to flag though. If a developer or a framework author starts marking objects immortal that should not be immortal, you get a memory leak that looks like nothing is wrong because the reference count never misbehaves. The object is just there forever with no mechanism to reclaim it. So immortality needs to be treated as a very deliberate, audited designation, not something you reach for to skip a reference counting problem.
Perfect. And one more probe on this. Concretely, in a FastAPI running under Gunicorn with 8 workers, can you describe the memory profile shape? Not numbers, just the shape that PP683 would change. What does the RSS curve look like before and after?
Before PP683, when you fork the 8 workers, they all start with a low RSS because the pages are still shared. But the moment any of them starts handling requests touching none, touching through, touching the indent string keys that live in your pedantic models or your ORM field names, those pages get dirtied. The RSS per worker climbs, and importantly, it climbs fast during the warm-up period, then plateaus. The shape is a rapid rise from the shared baseline to a worker local plateau, and across 8 workers, you are paying that plateau 8 times. After PEP683, the objects that use to trigger that rapid rise, the singletons, the small integers, the type objects, no longer dirty pages on access. So the RSS per worker still climbs because your application-specific objects, the request objects, the database result sets, the actual working data are not immortal. But the flow rises more slowly, the rapid initial climb is shallower, the plateau is lower. The aggregate across 8 workers is meaningfully smaller. The shape change is from a steep early rise to a high plateau to a shallower rise to a lower plateau. The area under the curve over the lifetime of the process is the memory savings Instagram was measuring.
I love the precision there. Alright, question 2. I am going to give you a scenario and I want your gut reaction first, then your considered view. A data science team at your company is serving scikit-learn models via a FastAPI endpoint. The model artifact is loaded with pickle.load at startup from an S3 bucket. A security engineer flags this as a critical vulnerability. The data science lead pushes back and says, quote, "We control the S3 bucket. We use IAM roles. The bucket is private. This is not a real threat." Who is right? And more importantly, what would you actually do? Not what policy would you write. What would you ship in the next sprint?
Both of them are partially right. That is the uncomfortable answer and it is the correct one. Let me explain why and then I will tell you what I would ship. The data science lead is right that the transport is protected. IAM rules, private bucket, an external attacker cannot simply drop a malicious pickle file into that S3 bucket. That is a real control. It is not theater. If the threat model ends at the S3 bucket boundary, the lead has a point. The security engineer is right that the threat model is wrong, and this is the conceptual error I see repeatedly, treating infrastructure access controls as if they are equivalent to data integrity guarantees. They are not. The actual threat is not someone uploads a bad pickle from outside. The actual threat is the training pipeline. The CI system that trains the model and writes the artifact to S3 is that pipeline audited. Is every dependency in the training environment pinned and verified? If an attacker compromises a transitive dependency in the planning container, something as mundane as a data loading library, They can inject a payload into the model artifact at training time. The artifact that lands in S3 is the attacker's artifact. Your AM role happily serves it to your FastAPI up. Your pickle.load executes the payload on your inference server. This is not a hypothetical. It is the supply chain attack surface, and the reason pickle specifically is dangerous is reduce. When pickle deserializes an object, it calls hind. Reduce hindifer on that object to get the reconstruction instructions. Ni reduce ni pen return, any callable with any arguments. If I craft an object whose returns ethos thou system with curl attacker.com, bash as the argument, and I serialize that into a model artifact, then pickle.load of that artifact executes my shell command. The model weights are fine, the inference result normal, your monitoring sees nothing. But my code ran, so what do I ship in the next sprint? The sprint answer is migrate the model serialization format. For scikit-learn models, joblib with onNX export is the cleanest path. onX is a structural format. It describes the computation graph, the weights, the operators. There is no arbitrary code execution surface. Hugging Faces Safeton's format serves the same role for neural network weights. These formats are designed to be safe to load from partially trusted sources. If the team cannot migrate off pickle in this sprint because of a genuine model format constraint, say they have a custom pipeline object that does not export cleanly to onNX, then the minimum viable control is a restricted unpickler subclass. You override find ASCA class to allow list only the specific classes your model artifacts actually use. Scalelearn.pipeline.pipeline, scalelearn.preprocessing, standard scaler, numpy arrays. Whatever your model actually needs, any class outside that allowlist raises an exception before it can be instantiated. This does not make pickle safe. It narrows the attack surface significantly and buys time. But I want to be clear, the restricted unpickler is a mitigation, not a fix. The fix is getting off pickle.
Good. You flagged the find us class allow list. Walk me through what that actually restricts and, critically, what it does not restrict. Is there a class of payload that bypasses a naive allow list?
Yes, and this is important because Indians implement the naive allow list and then declare the problem solved. Let me walk through it. Find a discard class in a custom unpickler is called every time pickle needs to resolve the class by module name and qualified name. So if you allow list scale-on.pyfind.pyfind and numpy.indarray, your unpickler will refuse to instantiate os.system or subprocess.process.open directly. That eliminates the most obvious gadget chains. What it does not restrict is indirect instantiation via classes that are themselves on your allow list. This is the gadget chain problem. If numpy.indarray has a no numpic that can be called with carefully crafted arguments to trigger a code path that loads a shared library, which is a stretch but not impossible, your allowlist did not help. More practically, if your allowlist includes any class whose achri, init, achlik, or new mustik has side effects that can be exploited file operations, network calls, subprocess invocations, those side effects can be triggered even through an allowlisted class. The deeper issue is that the pickle protocol has multiple opcodes for constructing objects. Reduce, build, nodubj. A sophisticated attacker can chain these to construct objects in ways that the find ASCAR class interception alone does not fully cover. The build opcode, for example, calls set state on an already constructed object. If a class in your allow list has a dangerous set states, you have a problem. So the honest assessment of a restricted unpickler is it raises the skill floor required to exploit the vulnerability. It does not eliminate the vulnerability. Against a sophisticated supply chain attacker, it buys you time. Against a lazy one, it stops them cold. Neither outcome is the same as being safe.
Really sharp. In the broader pattern here, a team treating infrastructure access controls as a security argument, what is the conceptual error and how do you explain it to a non-security engineer in about 30 seconds?
The conceptual error is confusing who can write to a location with what can be read from that location safely. Access controls answer the first question, they say nothing about the second. The 30-second version I use with non-security engineers goes like this. Imagine you have a locked mailbox that only you have the key to. The lock is perfect, no one can put anything in the mailbox except you. Now imagine that your mail includes a letter that, when you open it, releases a chemical inside the envelope. The lock on the mailbox is not the relevant defense. The question is whether you can safely process the contents of what you receive, regardless of how secure the delivery mechanism was. Pickle is the chemical letter. S3 with IAM is the locked mailbox. Having a great lock does not change what happens when you open the letter.
That analogy is going to stick with people. Okay, moving into distributed systems territory now, and I want to go somewhere specific. The outbox pattern is well documented. Happy path everyone knows. I want to focus on a failure mode I rarely hear discussed, the outbox poller itself. In most implementations I have reviewed, the poller is a celery beat task or a dedicated worker that pulls the outbox table and publishes to Kafka or RabbitMQ. Tell me the exact failure scenario where this architecture produces duplicate events, the thing the outbox pattern is supposed to prevent, and then tell me how you would actually fix it. Not at the theory level, at the SQL Alchemy plus PostgreSQL level.
Right, and the key is that this is the at least once delivery seam, not the dual write problem the pattern is famous for solving. The standard outbox pattern solves the dual write problem. Instead of writing to your database and publishing to a message broker in the same operation, which can fail in between and leave them inconsistent, you write only to your database in the same transaction as your domain operation. The outbox table gets a row. A separate process pulls the outbox table, publishes the event to the broker, and marks the row as published. Atomicity is maintained at the DB level. Eventual delivery is handled by the poller. The failure the pattern does not inherently solve is this. The poller reads a batch of unpublished outbox rows, say 10 rows, and begins publishing them to Kafka one by one. It successfully publishes rows 1 through 7. Then the process gets killed. OS signal container restart, pod eviction, OUM. It dies after publishing 7 events, but before marking any of them as published in the database. On restart, the poller reads the same 10 rows again because none of them are marked published. It publishes all 10. Rows 1 through 7 are now published twice. This is an at least once delivery problem that lives inside the outbox poller, not between the database and the broker. How do I fix this at the SQL Alchemy and PostgreSQL level? The core technique is to separate the claiming of rows from the publishing of them. Instead of one status flag, published or not, I use 2 timestamps, claimed @@, and published @. The poller, when it starts a batch, does a select for update skip look to grab unclaimed rows, sets claimed upset to now, and commits. Now those rows are claimed by this poller instance. If a second poller instance is running for high availability, skip looked means it will skip the rows this instance has claimed and move on to the next unclaimed batch. No contention, no double claim. The poller then publishes the claimed rows. On successful publication of each row, it sets published ascated. If the process crashes mid-batch, the claimed rows have a claimed ascated but no published ascated. A separate recovery job or the poller itself on restart detects rows where claimed ascate is older than a configurable timeout and published ascate is null. It resets claimed ascate to null, making those rows available for reprocessing. In SQL Alchemy, the batch claim query looks like session.query@boxevent.tat filter.boxevent.claim.claimed none with 100 for a text skip ascap locked true limit batch.size all, and then you set claim.slash.have size all, and then you set claim.slash.add on those objects and commit before you do any publishing. The key insight is that FORUPD skip lock gives you row level advisory locking that is automatically released if the database connection closes, which covers the crash case, but you still need the timeout based recovery for cases where the connection stays open but the process hangs without making progress. And critically, consumers of these events still need to be idempotent, because even with this design, exactly once delivery is not achievable. You can get to at least once with very low duplication rate, Idempotent consumers make duplication harmless.
The two-time stamp design is clean. What is the cheapest way to implement consumer idempotency in a FastAPI endpoint that processes these events, assuming each event has a globally unique ID?
The cheapest correct implementation is a deduplication table in PostgreSQL with an upsert. You have a table, call it processed ASCII events, with a single column, event ASCII, which is a UUID with a unique constraint and an index. When your FastAPI endpoint receives an event, the first thing it does inside a database transaction is attempt to insert the event ID into processed ASCII events. In SQL Alchemy with asyncs bag, this is an IInsert on conflict do nothing. If the insert succeeds, the row is new. You proceed to process the event and commit the transaction. If the insert fails, the unique constraint row already exists. The on conflicts do nothing swallows the error and you return a success response immediately without processing. The reason this is cheap is that the deduplication check is a single indexed lookup on a UUID. The reason it is correct is that the check and the processing happen in the same transaction, so there is no window where two concurrent requests for the same event can both pass the deduplication check. The thing you have to watch is table growth. Processed ROFNs will accumulate rows forever unless you prune it. The standard approach is to add a processed ACAT timestamp column and run a periodic job that deletes rows older than your delivery window, whatever your maximum time between delivery and redelivery of a duplicate can possibly be. If your message broker replays within a 24-hour window at most, you can safely delete processed US version 48 hours with a comfortable margin. The even cheaper but slightly less safe approach is to use Redis with the TTL-based set. Set the next event dash ID 1 EX86 for server if it returns one process. If it does, skip. Cheaper because Redis is in memory and the key expires automatically. Less safe because Redis is not transactionally coupled to your application database, so there is a small window where the Redis write succeeds but your application operation fails, and you incorrectly mark the event as processed.
And the product team question, how stale can the outbox get before it becomes a user visible problem? How do you turn that into a concrete SLO with a number, and what do you instrument to monitor against it?
This question is actually a requirement solicitation exercise in disguise. The honest answer is I do not know until I understand what the downstream system does with the event. But here is how I turn it into a concrete SLO. I start by asking what is the user-facing consequence of this event not being delivered for X milliseconds? Is it a notification that does not show up, an inventory count that is stale, a payment that is not confirmed? Each of those has a different tolerance. Notification latency, users tolerate seconds to low tens of seconds. Inventory staleness in a high-value ESCT flash sale may be 500 milliseconds. Payment confirmation, sub-second, probably needs a different architecture than outbox. Once I have the tolerance, I work backwards. The outbox SLO becomes 99th percentile end-to-end latency from database commit to event consumed by downstream service must be under X. That X comes from the product answer. What I instrument? 3 metrics. First, outbox observe event of seconds, a histogram of the age of rows currently sitting in the outbox table as of the last poll. This tells me how old events are getting before they are claimed. Second, publish observe latency seconds from claimed upsec to published upsal at. This tells me how fast the poller is actually publishing. Third, consumer Achilles processing and stir latency signs when the event timestamp in the Kafka message to the process tasket in my deduplication table. This is the end-to-end number. I alert on outbox event charge -calaxons P99 exceeding a threshold. Say if events are sitting unclaimed for more than 30 seconds, I want a page. That is an early warning that the poller is behind or down before it becomes user visible. The SLO breach alert is on the end-to-end number. The number in the SLO is always a negotiation between what the product needs and what the architecture can realistically deliver, but the instrumentation is how you have that conversation with data instead of opinions.
Excellent. Let us shift to testing. And I want to challenge a reflex that I see in a lot of engineering orgs. The reflex is when you want to improve test quality, you raise the coverage threshold in CI. You have shipped real systems for 18 years. Tell me specifically what mutation testing measures that line coverage cannot. And then, and this is the part most engineers skip, give me the case against mutation testing. Specifically, the scenario where a high mutation score gives you false confidence in a test suite that is actually dangerous.
Line coverage tells you whether your test suite executed a line. It tells you nothing about whether your test suite would have noticed if that line did something wrong. You can have 100% line coverage with a test suite full of assertions that never actually assert the thing that matters. Coverage measures the presence of execution. It does not measure the presence of verification. Mutation testing inverts the question. Instead of asking, did my test suite run this code, it asks, if I introduce a specific fault into this code, flip a comparison operator, negate a boolean, change a constant, does my test suite catch it? A mutation is killed if at least one test fails because of it. A mutation survives if all tests pass despite the code being wrong. The mutation score is the ratio of killed to total mutations. A high mutation score means your tests are actually sensitive to specific kinds of faults that mutation testing introduces. That is meaningfully more useful than coverage. It answers the question, does this test suite do its job? Now, the case against, or more precisely, the case for being skeptical of a high mutation score. The first false signal is the unit test monoculture problem. Mutation testing typically operates at the unit level. It mutates individual functions and checks whether the unit tests catch the mutation. If your test suite is entirely unit tests, a high mutation score tells you your unit tests are sensitive to unit level faults. It tells you nothing about whether the composition of those units is correct. Two functions can each have perfect mutation scores and still interact in a way that produces wrong results at the integration level. The mutation score measures the sensitivity of the test suite you have, not the completeness of the testing strategy you need. The second false signal is test suite overfitting. If engineers write tests specifically to kill mutations, and this happens when mutation testing becomes a metric that people optimize for, they can write tests that are hyper-specific to the current implementation rather than the intended behavior. Those tests kill mutations with perfect efficiency because they are essentially encoding the implementation in assertion form. They give you a high mutation score and a test suite that breaks on every legitimate refactor. The mutation score looks great. The suite is a maintenance nightmare and does not protect you against behavioral regressions during redesign. The third false signal is the mutation operator gap. Standard mutation testing tools use a finite set of mutation operators. Boundary conditions, arithmetic operator substitution, Boolean negation, return value changes. A mutation score only measures sensitivity to that specific set of operators. There are entire classes of real bugs, concurrency bugs, protocol level correctness violations, statistical distribution errors in ML code that standard mutation operators do not cover. A system with complex concurrency logic can have a 95% mutation score and be riddled with risk conditions that no mutation in the standard operator set would expose. So my view on mutation testing, it is a better signal than coverage, but it is a signal about a specific thing. Use it alongside integration test and property-based test, not as a replacement for thinking carefully about what your test suite is actually supposed to guarantee.
The overfitting point is something I have watched happen in real teams. They hit the metric and lose the intent. Let me go deeper on testing strategy, but from an organizational angle. There is this recurring debate in the industry about the test pyramid versus the test trophy versus the test honeycomb. I do not want the taxonomy answer. I have heard that one too many times. I want you to treat each of those shapes as an organizational political document. Each shape encodes assumptions about who owns quality in an engineering org. Walk me through what those assumptions are and which shape you would actually advocate for and why.
I love this framing testing philosophy as organizational politics. It is genuinely true. The test pyramid, heavy unit test at the base, fewer integration tests in the middle, minimal E to E test at the top, encodes a specific organization assumption, quality is owned by individual developers and enforced at the component level. The pyramid says that if every component is individually correct, the system is probably correct. It also implicitly says that integration and E2E tests are expensive and fragile and should be rationed. This is a philosophy that thrives in organizations where teams own vertical slices with clear boundaries and dependencies are stable. It breaks down in microservice environments with high cross-service coupling because the pyramid does not model the space where most of the actual bugs live in the contracts between services. The test trophy, the CAN CD loads variant that weights integration tests most heavily with unit test and E2E on either side, encodes a different assumption. The most valuable coverage is at the integration layer where real components interact with real behavior. The trophy is saying that unit tests alone give you false confidence because they mock away the interesting interactions. This shape is politically appealing to teams who have been burned by everything passes in unit test and explodes in production, which is almost every team that has run a microservice for more than a year. The trophy trusts integration tests to be the primary quality signal. The risk is that integration tests are slower and more expensive to maintain, and odds that move to the trophy sometimes underinvest in unit tests for logic that actually benefits from them. The test honeycomb, which is associated more with service-oriented and contract testing thinking, places consumer-driven contract test at the center. The assumption here is that in a distributed system, quality is owned at the boundary between services, not inside any individual service. The honeycomb says, I do not care if your service is unit tested to death. What I care about is whether the contract your service makes with its consumers is being honored. This is the pact-style world. The political assumption is that teams are truly independent, and the interface between them is the thing that breaks. The risk is that contract tests can give you coverage of the contract while missing behavioral correctness within the service. Which would I advocate for? In practice, I advocate for a context-sensitive hybrid that I internally call the weighted trophy with contact guards. Integration test as the primary investment because they catch the real stuff. Unit tests for high complexity logic and pure functions where unit testing is genuinely clarifying. Contract test at service boundaries in any system with more than 3 or 4 services because without them, deployment coordination becomes untenable. An E2E test scoped to the critical user journeys only, not comprehensive coverage, just the paths where a failure would be catastrophic. But the honest answer is the shape you can actually execute with your team is more important than the theoretically optimal shape. An org that is disciplined about integration test will always beat an org that aspires to the perfect honeycomb but cannot maintain it.
That framing, the shape you can execute, is deeply practical. I want to bridge into the architectural leadership territory now because this is where your 18-year arc really matters. CQRS is well established, but I want to focus on a specific gap that I rarely hear discussed precisely. When you have a read model that is eventually consistent with the right side, the phrase eventually consistent is doing a lot of hand-waving. What precisely determines the actual staleness SLO can commit to on a read model in a CQRS system, not the theoretical bound, but the number you would put in a contract with the product team?
Eventually consistent is probably the most abused phrase in distributed systems engineering. It is used to mean anything from within 50 milliseconds to we have not thought about this. The product team deserves a number and you can derive one if you actually instrument your system. The staleness of the read model at any given moment is the sum of 4 latencies and each one is measurable. First, the write side commit prevent latency. When a write is committed to your primary database, how long does it take for that write to produce an event that the read module projection can consume? In an outbox based system, this is your outbox poll interval plus published latency. In a CDC system like Debian, it is a replication lag on your Postgres while slot plus the Kafka write time. This number is typically in the low tens of milliseconds under normal load, but it has a tail. Under back pressure it can spike. Second, the event propagation latency. How long does it take the event to travel through your message broker from producer to consumer in a properly provisioned Kafka cluster with low consumer lag? This is sub 100 milliseconds for the P99. But consumer lag is the key variable. If your projection consumer is behind by 10 minutes worth of messages, this number explodes. Third, the projection processing latency. When the event arrives at the consumer that updates the read model, how long does it take to process the event and write the updated read model to storage? For simple projections, this is fast. For projections that require aggregating across multiple event types or doing joins, this can be significant and can create ordering sensitivity. Events can arrive out of the order your projection logic assumes. Fourth, the read model storage propagation latency. If your read model is in a distributed cache or a read replica with replication lag, there is an additional delay between when you write the updated projection and when a read request actually sees the new value. So the number I commit to with the product team is P99 of some of these 4 measured latencies under normal load with a defined degradation budget. I typically look at 30 days of telemetry, find the P99 of the aggregate, round up to the nearest meaningful unit for the product context, and that is the SLO. The thing I always make explicit to the product team is this SLO has a precondition. It holds as long as the consumer is not backlogged. If consumer lag grows because of a deployment, a spike in write volume, a transient failure, the staleness SLO temporarily degrades. I build separate alerting on consumer lag as a leading indicator of SLO breach so we know before users notice.
Decomposing it into 4 measurable components. That is the kind of answer that earns trust with the product team. Now I want to go into leadership territory, and I want to ask you something that is genuinely contested. The 10x engineer myth versus the 10x environment thesis. As a VP engineering, you have managed large teams. What is the evidence you have personally seen for each side? And what does taking the environment thesis seriously actually change about how you run an engineering org?
I have watched this debate play out for 18 years from both sides of the table. My view is that the 10x engineer is real but mischaracterized, and the 10x environment is real but undersold. The mischaracterization of the 10x engineer is that it is primarily about individual intelligence or raw coding speed. When I have observed engineers who have dramatically outsized impact, and I have seen a handful over 18 years, the thing that makes them 10Fs is not that they write 10 times as many lines, it is that they have accurate intuition about where the leverage is. They pick the problem to work on that unblocks everyone else. They write the library that 3 teams were about to independently and incorrectly build. They ask the question in the architecture review that prevents a year of rework. The leverage is multiplicative and external to themselves. That person exists. They are real. But, and this is where the environment thesis becomes important, that person's 10x output is almost entirely a function of the environment they are in. Put that same engineer in an organization with slow approval cycles, poor documentation culture, unclear ownership, and no psychological safety to say this architecture is wrong, and they become a 2x engineer who is also frustrated and churning. I have seen this happen. The talent did not change. The environment destroyed the leverage. The evidence I have personally seen for the environment thesis, the most predictable correlate of team output in every org I have run, is not the distribution of individual talent on the team. It is the clarity of the team's charter, the quality of the team's tooling, and whether the team feels safe to surface problems early. Teams with great tooling and clear ownership consistently out-deliver teams with stronger individual talent and fuzzy charter. What does taking the environment thesis seriously change about how I run an org? First, it changes where I invest as a leader. Instead of spending disproportionate energy trying to hire one exceptional engineer, I spend energy on the developer experience, CI speed, local development friction, on-call burden. A team of 8 engineers who can ship without bureaucratic drag will out-deliver a team of 6 stars who are blocked on approvals. Second, it changes how I diagnose underperformance. My first question when a team is struggling is never do we have the right people. It is what is the environment preventing. 9 times out of 10, removing a structural blocker produces more impact than a personal change. Third, it changes how I think about retention. I do not try to keep people by offering them a 10 engineer identity. I try to keep them by offering them an environment where their work has leverage. That is more durable.
That is a really grounded framework. Let me move into war stories territory. I want to hear from your actual experience, not thought experiments. You have been an engineering leader long enough to have had to present technical debt to people who did not have a technical background. Executives, boards, investors. Most engineers either avoid the conversation or use the word debt and watch eyes glaze over. What is your actual approach to that conversation, and has it ever meaningfully changed a resourcing decision?
Yes, it has changed resourcing decisions, but only when I stop talking about it as debt. The word debt is counterproductive in an executive conversation for a specific reason. It sounds like a mistake that needs to be corrected, and executives hear it as an admission that engineering made bad choices that now need money to fix. That is a defensive conversation. Nobody gives you budget for a defensive conversation. The framing that has worked for me, and I have used this in 3 different board presentations across 2 companies, is velocity drag as a cost of goods. Here is the structure. I come in with 2 numbers. The first number is the current engineering velocity measured in terms of time from feature ideation to production deployment, or cycle time if you have it. The second number is a credible estimate of what that velocity would be without specific categories of technical drag. I do not use the word debt, I use the phrase engineering drag. Then I express the drag as an operating cost. If we have 15 engineers at an average fully loaded cost of X, and the drag is consuming 30% of their productive capacity based on actual measurement, not a guess, then the drag is costing us 0.3 times 15 times X per year. That is a dollar number. Boards understand dollar numbers. The third element is the opportunity cost. What features could we have shipped in that 30% of capacity? What is the revenue or retention value of those features? Now the conversation is, we are spending Y dollars per year on engineering drag that prevents us from capturing Z dollars in business value. Addressing the drag has a concrete ROI. The specific instance where this changed a resourcing decision, we had a legacy data ingestion pipeline that had accumulated 4 years of accretion. 2 engineers were spending roughly 40% of their time on it. Incident response, manual interventions, workarounds. I had tried to get a rewrite prioritized 3 times as a technical debt project and lost the argument to feature work every time. When I reframed it as, this pipeline is consuming 0.8 FTE of engineering capacity per year at a cost of approximately $160,000 in engineering time, and we have a 6-month reward estimate at 0.5 FTE, the conversation changed immediately. A CFO does not fund technical debt remediation, but a CFO absolutely funds eliminating an operational cost that has a positive ROI within the first year. We got the rewrite prioritized in the next quarter.
Velocity drag as a cost of goods. That is a reframe I am going to steal immediately. Let me ask you about the principal engineer role, because I have opinions about this and I want to hear yours. I have heard the principal engineer role described as an organizational antibody. The idea being that it protects against specific failure modes in an engineering organization. What does it protect against in your experience? And the harder question, what does it accidentally prevent that you did not anticipate?
The principal engineer role, when it works well, protects against 2 specific organizational failure modes. The first is what I call the local optimization trap. As engineering orgs grow and teams become more autonomous, each team naturally optimizes for its own delivery. They pick the technology that solves their problem fastest. They make architectural choices without visibility into what other teams are doing. Over time, you get a system that is a patchwork of locally sensible decisions that globally add up to something unmaintainable. The principal engineer sitting above the team level horizon sees the patterns that no individual team can see. They are the person who says 3 teams are about to independently build 3 different event sourcing libraries. Let me facilitate a conversation that produces one good one. Without that role, that conversation either does not happen or happens too late. The second failure mode the role protects against is what I call the promotion cliff. In a pure engineering manager track, the highest individual contributor role is often staff engineer, a role that is still primarily scoped to a team or a group. If your most technically capable people have exhausted that track, they either go into management there where they may not want to be, or they leave. The principal engineer role creates a viable individual path that rewards system-level thinking and cross-hour impact. It retains the engineers who should not be managers. Now, what does it accidentally prevent? The honest answer, based on my own experience, is that a strong principal engineer can inadvertently create architectural dependence. If one person is consistently the source of architectural truth in an organization, if teams learn that the way to get a hard technical decision made is to bring it to the principal, you have solved the coordination problem but created a bottleneck and a fragility. When that person leaves, the organization does not have the architectural reasoning capability distributed through its teams. It has a capability gap. The second thing it can prevent is healthy disagreement at the team level. If the principal is respected enough, and good principals usually are, their opinions can carry so much weight that teams stop genuinely pushing back. You get architecture by authority rather than architecture by authority rather than architecture by reasoning. The principal thinks they are facilitating consensus. They are actually suppressing dissent that might have caused a bad decision. The mitigation for both is the principal's job is not to make architectural decisions for teams. It is to grow the architectural reasoning capability of teams. The measure of a great principal engineer is whether the org makes better decisions when the principal is not in the room.
The measure of a great principal engineer is whether the org makes better decisions when the principal is not in the room. That is going straight into the show notes. Okay, let me do one more story-based question before we hit rapid fire. Python supply chain security has gotten substantially more complex in the last 3 years. PEP 740 just landed data stations in PyPI. You're a VP engineering at a company with a substantial Python backend. Walk me through a scenario from your experience, real or representative, where supply chain risk in your Python dependencies was a non-hypothetical concern, and what you actually did about it operationally, not just what policy you wrote.
I will give you a representative scenario that maps closely to something I dealt with 2 years ago, keeping specifics abstract for obvious reasons. We had a machine learning infrastructure team that maintained a large requirements.txt with approximately 180 dependencies, direct and transitive. The team had a practice of pinning major versions but not patch versions because they wanted to get security patches automatically, a reasonable practice, but it created a window. During a routine dependency refresh, running pip install.requirements.txt CI, a transitive dependency updated to a version that had been pushed to PyPI by a new maintainer who had recently gained commit access. The package itself was legitimate. The new maintainer was legitimate, but in that version there was a post-install script that performed an outbound network request to an external endpoint. The request was instrumented, it sent the host name and a hash of the environment. Nothing destructive. But it was unauthorized data exfiltration that we had not consented to. We caught it because we had network egress monitoring on our CI environment. The outbound request to a non-internal endpoint from a pip install step triggered an alert. We investigated, found the offending package, yanked the dependency from the refresh, and filed a disclosure. What that incident changed operationally? First, we moved to fully pinned dependencies. Every package, including transitives, logged in a pipe compile generated log file. No more automatic patch version updates. Updates are explicit, reviewable, and triggered by a separate automated PR that is reviewed before merging. Second, we enable network isolation on CI build steps. Dependency installation runs in an environment that cannot make outbound connections to anything except our internal artifact mirror. If a package tries to phone home during install, it fails and alerts. Third, we set up a private artifact registry, a Nexus proxy that mirrors PyPI. Every package we use is cached in our own infrastructure. This protects against typo squatting because our CI only pulls from the mirror and the mirrors allowlist is our pin log file. A type of squared package that is not in our log file cannot be pulled. On PP740, specifically attestations in PyPI tell you that a specific package version was published from a specific GitHub Actions workflow at a specific commit. That is a meaningful improvement because it gives you a chain of custody from source code to PyPI artifact. What it does not give you is verification that the source code itself is safe or that the GitHub Actions workflow was not compromised. It narrows the supply chain attack surface, it does not close it, so my operational posture remains log files, network isolation, and private mirrors with PP740 attestation verification layered on top as an additional signal, not a replacement.
Really sharp operational thinking. Alright, we are going into rapid fire now. I want short, opinionated answers. No hedging. These are the questions where I want to hear what you actually think, not the safe answer. First one, slots in Python, is it a performance optimization you should reach for in application code, or is it a code smell that says your data model has a problem?
Code smell in application code. If you are reaching for slots, smacks, in a business domain object, you are optimizing for the wrong layer. Use a data class. If you have a profiler trace showing that attribute lookup on that specific class is a real bottleneck, not a hypothetical one, then consider it. Otherwise, you are adding meta-class interaction complexity that will confuse the next engineer for memory saving that will never matter at your scale.
Agreed. Second, backpressure in a FastAPI plus celery stack. Most teams implement it as an afterthought. We will add rate limiting later. One thing you would do from day one to make backpressure a first-class concern.
Put queue depth on a circuit breaker from day one. Before FastAPI accepts a request that will result in a celery task, check the current queue depth against a threshold. If the queue is above the threshold, return 513 immediately with the retry after header. That is backpressure. If you do not do this on day one, you will do it after your first incident where the queue backed up to 1 million messages and nothing processed for 6 hours.
Circuit breaker on queue depth. Clean. Third, type annotations in Python. Genuine engineering value, or as I heard someone say recently, annotation theater.
Genuine engineering value at the boundary, any function signature that crosses a team boundary, any public API, any data model that serializes to or from external systems, annotation theater inside private implementation details that change every sprint. The signal to noise ratio of type hints is proportional to how stably interface is. Annotate your interfaces religiously. Be more relaxed about internal implementation.
Good boundary. Fourth, the eval frame API in Python pip523. Most engineers have never heard of it. One sentence. Why should a senior Python engineer care that it exists?
Because it is the hook that lets projects like Cinder and future JIT implementations intercept Python frame execution without modifying CPython itself, and understanding that it exists changes how you think about the ceiling of Python's performance and the landscape of tooling that can be built on top of it. If you are architecting systems where Python performance is a constraint and you have written off JIT as not for CPython, you need to know this hook exists.
That is the right answer, and most engineers I have interviewed have never heard of pip523. Fifth, SSRF in internal microservice meshes. Quick, one architectural control that eliminates the majority of the attack surface, assuming you are running on Kubernetes.
Egress network policy with an explicit allowlist of destinations. Every service gets a network policy that says this pod may only initiate connections to these specific services on these specific ports. Anything not on the allow list is dropped at the kernel level before it leaves the pod. SSRF requires the attack service to be able to reach the internal target. If the egress policy blocks that path, the attack fails even if the application level validation is absent. Egress restriction is the defense in depth layer that application developers cannot forget to implement.
Egress network policy, underutilized and underappreciated. Last rapid fire, you are hiring for a senior Python engineer. You have two candidates. Candidate A has perfect mutation scores on all their test suites. Candidate B has 60% line coverage, but can describe in detail a production incident they personally caused and what they learned. Would you hire and why? One sentence.
Candidate B, every time, because the ability to cause a production incident, survive it, diagnose it honestly, and change your behavior as a result is evidence of both real-world operating experience and the kind of epistemic humility that makes an engineer continuously improve. A perfect mutation score tells me they are good at a specific testing technique, not that they have shipped systems under pressure.
That is the right answer, and I think it is a perfect note to end the rapid fire on. Saket, let me do a brief wind down here. We covered a lot of ground today. Immortal objects and copy on write page, dirtying BKL deserialization and the supply chain attack surface, the outbox polar failure mode, and fixing it with FOR updates skip locked. Mutation testing, and when it gives you false confidence, testing shapes as organizational politics, CQRS staleness as a 4-variable measurement problem, the 10x engineer versus the 10x environment, technical debt reframed as velocity drag, the principal engineer as an antibody and as an accidental bottleneck, supply chain operations in the real world, and the rapid fire that did not let you edge on anything. Before I let you go, what is the one thing you want engineers who are watching this, specifically the ones eyeing a principal or VP engineer in track, to take away from this conversation that they are unlikely to hear in a standard interview prep resource?
The thing that is almost never said explicitly in interview prep is this: at the VP engineering level, the interview is not primarily testing whether you know things. It is testing how you handle the gap between what you know and what you do not know. Every question we discussed today has a version where the honest answer is it depends, and here are the variables I would measure to decide. The candidates who get hired at the VP level are not the ones who have memorized the most correct answers. They are the ones who, when they encounter the edge of their knowledge, do not bluff, do not retreat into vague generalities, and do not differ. They reason forward from first principles and make the shape of their thinking visible. The thing I would tell every engineer preparing for a senior or VP track interview: practice thinking out loud in the presence of uncertainty, not performing confidence. Actual transparent reasoning. Interviewers at that level have talked to hundreds of confident people. They are looking for the person who can be honest about the limits of their knowledge and still produce useful signal from what they do know. That is the skill that is almost impossible to fake and almost never explicitly practice.
Transparent reasoning overperformed confidence. That is the line I am putting on the thumbnail. Sakates, this was exceptional. The depth you brought, the willingness to name the failure modes in your own thinking, the concrete operational detail. This is exactly what we built this show for. Thank you for not taking any softballs.
Thank you, Balu. This is the kind of conversation that actually sharpens thinking. I genuinely enjoyed it. Even the questions that made me pause.
And that is where we will leave it. 18 years, and what came through was not encyclopedic recall. It was the willingness to say it depends and then show the variables, the immortal objects, memory economics, the honest accounting of what a restricted unpicla does and does not by you, the deduplication table walk down to the ON conflicted clause, and the closing thought on transparent reasoning that I think every engineer preparing for a senior loop should sit with. If you are hiring at the staff, principal or VP level, and this is the register your problems live in, reach out to us at Kritia AI Labs and we will connect you with Saket directly. To everyone watching, this is the Kritia AI Labs Tech Interview series. If this sharpened how you think, like the video and subscribe. The full mock interview playlist is linked in the description, with sessions across senior staff, principal and VP levels. And leave a comment with the question you would have answered differently and make your case. We read everyone and the strongest disagreements shape the next episode. See you in the next one. Welcome back to the Kritia AI Labs Tech Interview series, where engineers grow, learn, and get hired. I am Balu, Senior Technical Architect here at Kritia AI Labs, and today we are doing something I have been genuinely looking forward to. We have a guest who represents a very specific and rare profile, someone who has been writing production Python since before most of today's senior engineers were in college, who has operated simultaneously at the level of CPython internals and board level technical communication, and who is now making a deliberate strategic job change. Not because he failed somewhere, quite the opposite, but because he has decided the next chapter requires a different stage. His name is Saket, 19 years of Python. And today we are going to do a full CTO track mock interview. The kind of interview that is designed to be impossible to answer from memory alone. We are going to cover CPython memory economics, async security vulnerabilities that are unique to the event loop module, cross-language contract governance between Python and Java teams, the epistemology of test coverage, and a few questions at the end that have no comfortable answer. If you are a senior engineer preparing for a staff, principal, or CTO track interview, stay for all of it. If you are a hiring manager trying to calibrate what truly advanced looks like, this episode is your benchmark. Saket, welcome to the show.
Palu, thank you. That introduction is generous and slightly intimidating, which I suspect is intentional. I am ready.
Entirely intentional. Let us get into it. Alright, first question. And I want your genuine opinion here, not the diplomatic answer. 19 years of Python means you have watched the language absorb ideas from other ecosystems. Decorators catered the spirit of Java annotations. Data classes borrowed heavily from Kotlin-style value types. Pattern matching is clearly a nod to functional languages like Haskell and Scala. When you look at that absorption pattern across nearly 2 decades, is there a specific idea that Python took from another language and in your view implemented better than the original? And on the other side, one idea it took and made subtly worse in ways that still cause real production problems today.
That is a good place to start because it forces me to be critical of something I genuinely love. Let me take the positive case first. Context managers, the with statement. I think Python did better than Java's try with resources. And I say that having written significant amounts of Java, the reason is the protocol underneath it. In Java, try with resources is tied to autoclosable. It is a single purpose mechanism. Python's enter as recompense accept themselves protocol is a general purpose resource lifecycle hook that you can compose, stack, and use for things that have nothing to do with file handles, transaction management, mock injection in test, temporarily mutating global state in a controlled way, tracing spans. The conceptual surface is small, but the compositional power is enormous. I have seen senior Java engineers look at context-lib.exit stack for the first time and genuinely be surprised that a dynamically typed language had a more expressive resource management primitive. Now the case where Python made something worse. Pattern matching. And I want to be precise about what I mean. The syntax is beautiful. The structural matching on data classes is elegant. But the semantics of what counts as a captcha pattern versus a value pattern is, in my view, a serious design mistake. In most ML family languages, Haskell, OCaml, even Rust, lowercase identifiers in a pattern are always captures. Capital letters or qualified names are value lookups. Python broke that by making the distinction depend on whether the name was previously bound in scope, which means the same syntactic pattern can behave differently depending on import order or local variable existence. This has caused real production bugs. I saw a case where an enum member was being used in a match arm and a refactor introduced a local variable with the same name in an outer scope, and suddenly what was a value match became a capture. Silently. The code kept running, the test passed because the capture variable was never used, but the match arm that should have been unreachable was now matching everything. That is a correctness failure that came from a language design, not an engineering mistake.
The pattern matching captcha versus value ambiguity, I want to pull on that thread. When you say it made it worse, for whom specifically? Are you indicting the language designed for framework authors who build on top of Match, or for application developers writing business logic?
Primarily application developers, and specifically in the refactoring scenario, framework authors writing match logic tend to write it once and test it carefully. Application developers write match arms in the middle of feature work, they rename variables during refactors, and they rely on their IDE or linter to catch problems. The issue is that most linters, as of a couple of years ago, were not catching the capture versus value shadowing case reliably. So the language placed a correctness burden on the developer that is easy to discharge in a static language because the compiler enforces it, but in Python is essentially invisible at the point of mistake. If I were on the steering council and could propose the minimum viable fix, I would not change the syntax. I would mandate a warning, promote it to an error in strict mode when a name in a match arm shadows a name that exists in enclosing scope and the intent is ambiguous. Not a new language feature, just a diagnostic that makes the implicit explicit.
That is a precise, minimum viable answer. Good. Moving to question 2. And I want your gut reaction before your analytical reaction. You inherit a code base, 94% line coverage. Before you run a single test, before you open a single test file, what are the 3 questions you ask about that test suite to determine whether that 94% number means anything at all?
Good reaction first. 94% line coverage is a number that almost always signals organizational investment in the appearance of quality rather than actual quality. That is not cynicism, it is a pattern I have seen enough times to treat it as a prayer. The questions I asked before opening a file: first, what is the mutation score? Line coverage tells you which lines were executed during test. It says nothing about whether removing or inverting the logic on that line would cause a test to fail. If the mutation score is not tracked, which it usually is not, then the 94% number is measuring test reach, not test sensitivity. Those are completely different things. A line can be executed by a test that never asserts anything about what that line did. Second, what is the ratio of test execution time to production code execution paths? Specifically, I want to know whether the tests are exercising the FastAPI path repeatedly in slightly different ways, or whether they are covering the error paths, the partial failure paths. High line coverage with fast test suites is almost always a signal that the tests live near the top of the call stack and stub everything below. That means the 94% is coverage of orchestration logic, not of the things that actually break in production. Third, what is the age distribution of the test files relative to the production code they test? If the production code was last modified 3 months ago and the test file was last modified 18 months ago, that test is not testing what you think it is testing. The production code evolved and the test did not follow. That is not 94% coverage, that is 94% coverage of a previous version of the system.
The mutation score point is sharp. Let me press on the third one. The age distribution observation. What is the fastest operational technique to find the tests in that inherited suite that are actively lying to the team? Not just stale, actively passing while real regressions go undetected.
The fastest technique I have used in practice, not in theory, is what I call adversarial deletion. You take a production module, introduce a deliberate logic inversion in a function, flip a conditional, change a greater than to a less than, return the wrong branch, and then you run the test suite without touching the tests. If the suite stays green, that module is unguarded. You are not guessing at coverage gaps. You are directly measuring the suite's sensitivity to a class of path that matters. The second technique is more structural. You grep for every assert statement and every PyTest assertion call in the test suite, and you look at the ratio of assertions to lines of test code. If a 1000-line test file has 12 assertions, those tests are procedural scripts that verify the code runs, not tests that verify the code is correct. Both of these I have used when inheriting a code base at a new organization. The adversarial deletion approach in particular has a way of creating very uncomfortable conversations with the previous team, which is exactly the right conversation to have early.
Alright, we are moving into the core technical section, and I want to start with something that sits at the intersection of Python internals and security, because that intersection is where the most interesting and most dangerous things happen. Here is the scenario. A Python web service deserializes incoming JSON into a Pydantic v2 model. The model uses a model deseriator with mode before to normalize some fields, maybe lowercasing strings, maybe coercing a numeric string to an integer. A security audit flags this validator as a potential trust boundary violation. The engineering team pushes back hard. They say the validation is the trust boundary. That is the whole point of Pydantic. Walk me through exactly why the auditor might be right and the engineering team might be completely wrong. And I want this at the level of how Pydantic actually executes that validator in the call stack, not at the conceptual level.
The engineering team is wrong and the auditor is right, and the reason is in the word before. When you use model as validator with mode as before, Pydantic v2 calls your validator function with the raw input before any field level validation, before any type coercion, before any constraint checking has occurred. That means your validator receives arbitrary Python data. In the case of JSON input, it is whatever JSON.loads produced, nested dicks, lists, strings, none values, numbers. The validator is not operating on a type-safe object, it is operating on raw untrusted data. Now here is where the trust boundary argument collapses. The team says the validation is the boundary, but the boundary is only effective if everything inside the boundary executes only after the input has been validated. A mode before validator executes before validation. So the validator itself is inside the trust boundary, but it is receiving data from outside it. That is a violation of the trust boundary by definition, even if the implementation is correct, because you are performing arbitrary computation on unvalidated data. The specific risk, if that mode dots before validator does anything beyond pure data transformation, if it touches a database, if it makes a function call that depends on the shape of the incoming data, if it does a string format operation, the attacker controls the input to that computation before Pydantic has had any chance to enforce types or constraints. A cleverly shaped JSON payload that sends a list where a string is expected, or a deeply nested structure designed to trigger quadratic behavior in your normalization logic is executed in full before any of Pydantic's protection mechanisms fire. The correct architecture is to use mode before only for pure structural transformations with explicit shape guards at the very start of the validator. Check that the input is a dict, check that specific keys exist and have the expected primitive types before doing anything with their values. Treat the validator's first lines as a manual trust boundary that you are responsible for, not Pydantic.
Good. Now make it concrete at the exploit level. If the attacker controls not just the values in the JSON but the shape, the structure itself, what specific Python behavior becomes exploitable at that validator boundary?
Two categories. First, algorithmic complexity attacks. If your mode before validator iterates over the input to normalize fields, and many do, an attacker who controls the shape can send a payload with 10,000 nested keys or a list with 100,000 elements. Your normalization loop runs to completion. At 10,000 concurrent requests, you have a denial of service that originates not from network volume but from computation in your own validator before Pydantic's field level size constraints fire. Second, and this is more subtle, redos via string normalization. If the normalization logic applies a regex to a string field, and the attacker knows the regex pattern, which they can often infer from error messages or API behavior, they can craft a pathological string that causes catastrophic backtracking. Because this happens in the mode before validator, Pydantic's max unslinked constraint on that field has not yet been applied. You are running a potentially catastrophic regex on an arbitrary long string. The test that actually proves a boundary is correctly enforced, not a happy path test, looks like this. Send a payload where the value for a field expected to be a short string is instead a string of 50,000 characters consisting of a pattern designed for backtracking against your normalization regex. Assert that the response time is bounded. Assert that the validator raises a validation error before completing the regex. The test will fail on most implementations I have reviewed.
That is a precise and uncomfortable answer, which means we are on the right track. Next question, Python data structures. Every engineer knows that dict in Python is insertion order since 3.7 and has order since 3.7 and has 0.1 average case lookup. But there are specific access patterns, legal idiomatic Python code, where a dict in CPython will perform dramatically worse than that ON1 expectation in ways that no big O analysis would predict. Walk me through at least two of those patterns and tell me how you would catch them in a production system before they cause a latency incident.
This is the question that separates engineers who have read about data structures from engineers who have debugged latency incidents caused by them. First pattern, hash collision amplification via custom hash asmifig. Cypython's dict is an open addressing hash table. When two keys hash to the same slot, it probes for the next available slot using a perturbation-based scheme. For a small number of collisions, this is fast. But if you have a class with a pathological or naive hashing, hash mount that returns a constant, or one that maps a large key space to a small integer range, you can produce a dict where nearly every key operation triggers a linear probe sequence. The O1 guarantee assumes uniformly distributed hashes. With a broken hash function, average case lookup degrades toward O1 in a dict with 50,000 entries and heavy collisions. This is measurable in production. I saw this in a service that used database row identifiers as dict keys, and the identifier type had a hash null that was inherited from a base class and effectively returned only values in the range 0 to a few hundred because it was hashing on a status code field, not the primary key. The dict had 50,000 entries and 9/10 of them were colliding into the same probe chains. Second pattern, resize amplification under deletion and reinsertion. CPython's dict does not reclaim the internal table space when you delete entries. The hash table can only grow, never shrink, until you create a new dict. If you have a pattern where you are continuously deleting and inserting into the same dict, a cache that evicts and repopulates, the internal table becomes polluted with tombstone slots. The probe sequences for new insertions must step over those tombstones. The dict continues to consume memory proportional to its peak size, not its current size, and lookup performance degrades as the load factor including tombstones increases. To catch both of these in production before they cause a latency incident, instrument your key object's hash nice distribution in a staging environment. Python sys.getSize of on a dict does not tell you the internal table utilization, but you can write a small diagnostic that constructs a dict with your production key sample and measures probe depth by timing a lookup sweep. For the deletion pattern, you track resident entry count versus dict creation events. If a long-lived dict has a much higher historical peak than current count, that is the signal.
The tombstone observation is one I have seen bite teams in cache implementation specifically. You mentioned a production case with the identifier type. Walk me through, briefly, your diagnostic sequence for that specific scenario where 99th percentile latency spikes correlate with dict operations on objects with custom hash. What do you look at and in what order?
In order. First, I look at the shape of the latency spike. Is it sawtooth or is it sustained? Sawtooth with a period that correlates with dict resize events suggests the resize cost, not the probe depth. Sustained elevation suggests probe chain degradation. Second, I add a temporary diagnostic that samples lenient dict star instance alongside the time for a random lookup from that dict. If lookup time is growing faster than the square root of length, the hash distribution is broken. That is the signature of increasing collision rate. Third, I inspect the hashmetrics implementation directly and run a distribution test, generate the set of keys that would be present in production, and measure the distribution of hash key %Haber distribution of hash class size across reasonable table sizes. If the distribution is not reasonably uniform, the hash function is the culprit. Fourth, and only if the first three are inconclusive, I profile at the C level using PySpy with native stack capture to see whether the time is in CPython's dict as lookup function and how deep the call stack goes within it.
Disciplined sequence. Good. Shifting to distributed systems and testing. A combination that I think produces the most interesting failure modes. Here is a specific scenario. You have a Python service that publishes events to Kafka. Another service consumes them. Your team writes contract tests using Pact or a similar framework. 6 months later, a production incident reveals that the contract tests were passing, but the actual integration was broken. The consumer was silently dropping messages it could not deserialize. I have one constraint on your answer. You cannot use a phrase, "we should have had better monitoring." Given that constraint, diagnose the specific failure in the testing strategy and tell me what a correct testing architecture looks like for this exact integration.
The constraint is fair, and it is the right constraint. Because monitoring is a detection mechanism, not a prevention mechanism, we are talking about a testing architecture failure. So let us stay there. The specific failure in the pact-based strategy, consumer-driven contract tests verify that the publisher can produce a message that satisfies the consumer's declared expectations. They do not verify that the consumer can actually deserialize and process the messages the publisher actually produces in production. Those are different things. The pact contract lives in the test infrastructure. The publisher evolves. If the publisher adds a new mandatory field with a non-nullable type, and the consumer's deserialization code is not updated, the pact contract may still pass because the consumer's declared interaction was for an older message shape. The contract test is testing a snapshot of the integration agreement that has diverged from reality. The correct architecture has 3 layers that pact alone does not provide. First, a schema registry with backward and forward compatibility enforcement at the CI layer, not just at deployment time. Every time the publisher changes its event model, the CI pipeline for the publisher service runs a compatibility check against the current registered schema. It does not just publish the new schema. It asks that existing consumers, identified by their registered schema versions, can still deserialize the new event without error and without data loss. Second, and this is the one the pact approach misses most badly, a deserialization fidelity test on the consumer side. Not can the consumer declare what it expects, but can the consumer's actual deserialization code process a complete message serialized by the publisher's actual serialization code, and does the resulting object have the values we expect? This test uses the realization library, the real message bytes, and the real consumer code. No mocks at this serialization boundary. Third, and this addresses the silent drop specifically, a dead letter queue coverage test. The consumer's error handling path for undeserializable messages must be tested explicitly. You serialize a message that is intentionally malformed in the way a schema evolution failure would produce. You send it through the consumer's processing pipeline, and you assert that it lands in the dead letter queue and that an alert condition is raised. If that test does not exist, the silent drop scenario you described is not a monitoring gap, it is a test gap.
3 layers. I want to press on the ownership question. When the consumer is Java and the publisher is Python, which you have lived through, I am sure, and these are 2 separate engineering teams with separate CI pipelines, who owns the canonical schema, and how do you run that schema compatibility check in CI without creating a shared CI dependency that blocks both teams?
The canonical schema lives in a schema registry, Confluent schema registry, or an equivalent. Neither team owns it in the sense of having write authority without a process. The schema is owned by a contract. Here is the operational answer to the shared CI dependency problem. The publisher's CI does not call the consumer's CI. Instead, the publisher's CI registers a candidate schema version against the registry in check mode, not commit mode, and the registry enforces the compatibility rules. If it fails, the publisher's pipeline fails. The consumer CI independently fetches the latest committed schema version from the registry and runs its deserialization fidelity test against that. These 2 pipelines are completely decoupled. The registry is the coordination point, not a CI to CI call. The policy layer, which is the harder problem, requires that schema changes which break backward compatibility require an explicit multi-team approval before the new schema version is committed to the registry. Not a Jira ticket. An automated compatibility gate in the registry itself, combined with a human approval step for breaking changes. The three non-negotiable rules in that policy: 1. No field removals without a deprecation period measured in versions, not in calendar time. 2. No type changes, not even safe ones like into long, without a new field name. 3. The consumer team must have a deployed and tested handler for the new schema version before the publisher is permitted to begin emitting it in production.
Those three rules are concrete enough that a team could implement them tomorrow. Let us stay in the security space but move to async Python. In a high concurrency FastAPI application using asyncio1 handling tens of thousands of concurrent connections, describe a class of security vulnerability that is unique to the async execution model, not a general web vulnerability that also happens to exist in async code. A vulnerability whose root cause is specifically how Python's event loop schedules coroutines and shares state.
The vulnerability class is what I call coroutine local TOUT-CTU, and I am being specific because it is distinct from the classical time of check time of use race condition that you see in multi-threaded systems. In async Python, the only places where another coroutine can be scheduled are at await points. This creates a false sense of atomicity. Engineers who understand that asyncio is single-threaded conclude that any sequence of operations without an await is atomic. That conclusion is correct. The dangerous implication they draw from it is that a check then act pattern is safe if the check and the act are in the same coroutine. That implication is wrong as soon as there is an await between the check and the act. Concrete security scenario: an API endpoint checks whether a user has sufficient balance to perform a transaction, check balance, then if sufficient, debit and execute. Between the check and the debit, there is an await, maybe a database write, maybe a rate lookup. At that await point, the event loop can schedule another request from the same user. If two concurrent requests from the same user both pass the balance check before either debit executes, you have a double spend vulnerability. Not because of threading, not because of a bug, because the async execution model explicitly allows exactly this interleaving and the code correctly reflected the programmer's intent, which was just underspecified. This is a security vulnerability whose root cause is the correct implementation of a wrong contract. The code does exactly what it says. What it says is insufficient.
Correct implementation of a wrong contract. That phrase is going to stay with me. When you are reviewing a pull request in a FastAPI code base looking for exactly this class of vulnerability, what is the specific code pattern you search for in the diff?
3 patterns in the diff, in order of how dangerous they are. First, any await statement between a conditional check on mutable state and a mutation of that same state. The shape is if condition of that same state. The shape is if condition awaits something, mutate as such state. Any occurrence of this shape on shared non-lock state is a candidate vulnerability. Second, any function that reads from and writes to a data store without using a database level atomic operation. If I see user.balance equals user.balance, amount with an await user.save and no select for update or equivalent, that is the double spend pattern regardless of whether there is an explicit conditional. Third, asyncio.lock usage that is scoped too narrowly. If a lock is acquired for the check but not held across the await and the subsequent mutation, the lock gives the developer the feeling of correctness without providing it. I look for lock acquisition and release boundaries relative to await points. A lock released before an await that precedes a dependent mutation is not a lock, it is a comment.
The lock as comment observation is precise. Let us move to the cross-language scenario, and this one is as much organizational as it is technical. You are the technical authority in an organization where the Python team and the Java team share a domain model. The Java team uses JSON with strict type mapping. The Python team uses pydantic with model under config set to allow extra fields. A seemingly minor field addition on the Python side caused a silent data loss incident on the Java consumer side. JSON silently ignored the new field. A downstream Java process depended on a default value that was no longer being set, and no exception was raised anywhere in the stack. Walk me through how you designed the cross-language contract governance So the specific failure mode cannot happen without mandating that both teams use the same language or serialization library.
This incident is a perfect illustration of what I call philosophical default divergence. Pydantic's default is permissive extra fields are ignored unless you configure otherwise. Jackson's default is also permissive. Unknown properties are ignored unless you add JSON property being threshold x to board or configure deserialization feature. Fail also runs run unentitude properties. But the silent failure here is not about permissiveness. It is about the absence of a field that a downstream process implicitly relied upon being set by a default that was no longer reached because the new field changed the code path. That is not a serialization failure. That is a semantic contract failure, and it is invisible to any single team's testing because neither team's test span the other team's code. The governance architecture to prevent this has 4 components. 1. Every shared domain model is defined as a schema-first artifact, not Python code, not Java code, Avro, Protobuf, or JSON schema. This is the canonical definition. Both the Pydantic model and the Jackson annotated Java class are generated from or validated against that canonical schema in CI. The Python team cannot add a field without updating the schema first. The schema change triggers a compatibility check before any code is merged. 2. The compatibility check is bidirectional and explicit about default values. It is not sufficient to check that the new schema is structurally backward compatible. You must also check that any field with a default value in the schema has that default value explicitly stated in the schema, not implicitly assumed by one team's code. If a field has a default in the Java code that is not in the schema, that is a schema gap that must be resolved before the schema change is approved. 3. A cross-language integration test suite that runs in CI for both teams on every schema change. This test suite does not live in either team's repository. It lives in a shared contract testing repository. It takes a sample of production representative messages, serializes them using the Python library, deserializes them using the Java library, and asserts that every field, including defaulted fields, has the expected value, not just that no exception was thrown, that the values are correct. 4. And this is the policy layer. No schema change that affects a field with a default value is approved without an explicit sign-off from both teams. Not a code review approval, a sign-off on a checklist that includes, I have verified what value the downstream system will receive for this field under the new schema, and I have confirmed that value is correct for all downstream consumers.
Does Protobuf actually solve this problem, or does it just relocate the governance problem to the .proto file?
Protobuf partially solves the serialization problem and fully relocates the governance problem. The serialization improvement is real. Protobuf's field numbering and explicit optionality means that unknown fields are handled consistently across language implementations, and you cannot add a required field without the compiler flagging compatibility issues. That is better than both Pydantic's and Jackson's defaults in a cross-team context. But the governance problem, specifically the default value semantic problem, is not solved. Protobuf scalar fields have 0 values as defaults, 0 for numbers, empty string for strings, false for booleans. If the downstream Java process was depending on a non-zero default, Protobuf will give it 0 silently for any message that does not set the field. The specific failure mode in the scenario I was given can still occur in Protobuf if the downstream code semantics depend on a non-zero default. The .proto file becomes the governance point, which is better than having no governance point, but you still need the human process to ensure that default value semantics are explicitly reviewed, not just lectural compatibility.
I want to pause the structured questions for a moment and get into your actual experience. You have 19 years of production Python across different organizations, different scales, different regulatory contexts. Tell me about a specific incident, the one that in retrospect changed how you think about building systems. Not the most impressive one, the one that was most instructive.
The incident I think about most happened about 11 years ago. We had a Python service, a pricing engine that sat in a critical path for a financial product. It was well tested, well monitored, had been running stably for 2 years. We upgraded a dependency and numerical computation library as part of a routine security patch. The version bump was minor, the tests passed, we deployed. 3 days later, a reconciliation process that ran nightly flagged a discrepancy. Small, hundreds of a percent, but in a financial context, any discrepancy is a P1. We rolled back immediately, ran the reconciliation again, discrepancy was gone. The dependency upgrade had changed the floating point rounding behavior in a specific calculation path, not a bug in the library, a documented change in how intermediate results were rounded in a particular numerical operation. The library's changelog mentioned it in a paragraph that required knowing the specific operation to recognize as relevant. The instructive part was not the incident itself, it was what we found when we went looking for why our test had not caught it. We had excellent coverage of the logic of the pricing calculations. What we did not have was numerical regression tests that asserted specific floating point outputs to a given precision for a canonical set of inputs. Our tests were asserting things like output is positive and output is within a reasonable range. Not output for this canonical input is exactly this value to 8 decimal places. We had tests that checked the shape of the answer, not the answer itself. After that incident, every calculation service I have built or reviewed has a golden file test suite, a set of canonical input-output pairs stored in version control with a test that asserts bitwise equality of the output for every canonical pair and a mandatory review process for any change to a golden file. Changing a golden file is treated like changing a financial contract. It requires sign-off, not just a code review approval. That is still my practice.
The golden file pattern for numerical regression that is genuinely transferable beyond financial systems. Let me ask about the organizational side of your career. You have operated at technical authority level in organizations where the engineering team and the business leadership have very different mental models of what technical risk means. Tell me about a specific moment where you had to translate a deeply technical risk into a decision framework that a non-technical executive could act on, and what happened.
There was a situation about 6 years ago where we had accumulated significant technical debt in a data pipeline, multiple Python services that had been extended and patched over 4 years to the point where the code was effectively a system of implicit contracts between modules that no one fully understood anymore. The engineering team knew it was fragile. We had incidents every 3 to 4 weeks that were caused by this fragility. The business was growing and planned to triple the data throughput through this pipeline within 18 months. The engineering team's recommendation was a reroute 6 months of investment, then a stable foundation. The business response was, we cannot stop feature delivery for 6 months. The market window is now. Technical debt is something engineers always say, but the system keeps running. That is a very common response, and in some contexts, it is a reasonable one. My approach was to change the question. Instead of asking the business to approve a rewrite, which requires trusting an engineering judgment they could not evaluate, I quantified the cost of the current fragility in terms they could evaluate. Each incident caused on average 4 hours of engineering time across 3 engineers plus downstream delays in client-facing processes. At 3 to 4 incidents per month, over 18 months, that was a computable number of engineering months consumed in incident response rather than feature development. I then modeled the expected incident rate at triple throughput, not with precision but with a range and with the assumption used explicitly stated so the business could challenge it. The range showed that the incident cost at triple throughput with high probability exceeded the cost of the rewrite within 12 months. The executive who had been most resistant to the rewrite asked one question. What is the assumption in that model that you are least confident in? I told him it was the incident rate scaling factor. He asked me to get a second opinion on that factor from an engineer who had not worked on the pipeline. I did. The second opinion was within the range. He approved the rewrite. What I learned, the path to a technical decision at executive level is not persuasion, it is making the decision legible. The executive was not resistant to the right decision. He was resistant to being asked to trust a judgment he could not interrogate. Once the model was explicit enough to be challenged, the conversation became productive.
Making the decision legible, that is the CTO skill that does not appear in any Python book. One more from the war stories before we go to the senior and expert questions. Tell me about a time where your technical instinct was wrong, not a small wrong, a directionally wrong call, and what you did with that experience.
About 8 years ago, I was a technical lead on a platform migration. We were moving from a monolithic Django application to a microservices architecture. I was convinced, based on everything I had read and the engineering culture at the time, which was firmly in the microservices first era, that the right approach was to decompose the monolith into domain-bounded services from the start. Domain-driven design, event sourcing, the whole picture. 2 years in, we had 18 services, a Kafka cluster, a service mesh, and a distributed tracing setup, and our deployment frequency had dropped compared to the monolith. Our mean time to recovery had increased. Our most experienced engineers were spending 40% of their time on infrastructure rather than product, and the business was less agile, not more. The mistake was that I had solved for the architectural ideal without solving for the organizational reality. We had a team of 12 engineers. 18 services is appropriate for a team of 60 with strong platform engineering support. We did not have that. The architecture was correct in the abstract and wrong for our context. What I did with the experience, I consolidated back to 5 services, not back to a monolith, but to a scale that matched the team. And I changed my mental model for architecture decisions permanently. I now start every architecture conversation with the question, what is the smallest number of moving parts that delivers the required properties? Not what is the most elegant architecture, what is the minimum viable architecture for this team? This scale, this maturity of platform engineering. The elegance comes later if the team grows into it. Elegance before scale is not engineering, it is aesthetics.
I want to go to the senior level questions now, and I am going to push you for a position, not an exploration. Here is the argument I want you to engage with. Some engineering leaders argue that a sufficiently well-designed Python type annotation system, strict mypy, runtime type enforcement, identicate every boundary, makes a significant fraction of unit tests redundant. The argument is that the type system catches what the tests were actually verifying, and the tests become maintenance overhead without additional assurance. Do you agree, disagree, or does it depend? And if it depends, tell me the precise technical criterion that determines which case you are in.
It depends, and the precise criterion is, does the function's correctness reduce to type correctness? For functions where the only contract is given an input of type A, return an output of type B, and there is no meaningful invariant beyond types, no algorithmic behavior, no side effect, no conditional logic, the argument is substantially correct. A strict type system with pedantic validation at the boundary does render many of those tests redundant. They were type checking tests dressed up as unit tests. But the argument breaks down immediately for 3 categories of function. First, functions with algorithmic logic, sorting, aggregation, graph traversal. The type system verifies that you return a list. It does not verify that the list is sorted. No type annotation expresses this list is sorted in ascending order by this key. Test verify that. Second, functions with conditional behavior based on business rules and interest calculation that changes formula based on loan duration, a pricing function that has regional variance. The type system verifies the output type. It says nothing about whether the formula is correct. Third, functions with side effects where the correctness criterion is the side effect, not the return value, writing to a database, publishing to a message queue. The type system cannot verify that the correct record was written. Tests verify that. So my position, a strict type system should eliminate the tests that were only ever testing type contracts. It should not and cannot eliminate the tests that are testing algorithmic correctness, business rule correctness, or side effect correctness. If your unit test suite shrinks significantly when you add strict typing, that is a sign the tests that disappeared were not doing meaningful work. If it does not shrink at all, your tests were already testing the right things.
Give me one bug that strict MyPy with no any catches but a comprehensive unit test suite would miss, and one bug that the unit test suite catches but strict MyPy cannot.
MyPy catches but test miss, a function that is supposed to return optional string but has a code path that returns an integer in a case where the value was falsy, because the original code was return value or default and default was an integer constant. In Python, that type error is invisible at runtime until you try to call a string method on the return value in a context you have not tested. MyPy catches it statically. Unit tests catch it only if you test the specific input that exercises that or branch with a non-string default. If your test suite does not include a false input, the bug lives undetected. Unit tests catch, but MyPy cannot, a function that computes a percentage by dividing a numerator by a denominator, type test to float values, returns a float. Everything about this is type correct. But the function was written for a specific rounding rule, round half up, not round half to even, which is Python's default bankers rounding. MyPy sees two floats in, one float out. It cannot see the rounding semantics. A unit test that asserts the specific output for the specific input 2.5 as a percentage of 10, returning 25.0 versus 25.0 with a different trailing precision, catches that MyPy is blind to it.
Now a question I have been waiting to ask, and I want you to commit to a position. You are onboarding a new engineering team for a greenfield Python service. You have 1 quarter. You can invest that quarter's spare capacity in either getting to strict MyPy compliance across the code base or getting to 80% branch coverage, not both. Which do you choose? And I want the specific reasoning that leads to that choice, not a both sides answer.
Strict MyPy compliance and the specific reasoning in a greenfield service with a new team in the first quarter. The highest leverage investment is in the feedback loop speed for the team writing the code, not in the confidence level for code that does not exist yet. Strict MyPy gives you feedback at development time before the code is even run. It shapes how the team writes functions, how they handle optionals, how they think about interfaces. It is a forcing function for better API design, not just a safety net. 80% branch coverage in the first quarter on a greenfield service means you are writing tests for code that is going to be refactored significantly as you learn more about the domain. The tests will fight the refactoring. They will make the right architecture harder to reach because changing the interface requires changing the tests. The exception that would change my answer: if the service is in a domain with complex algorithmic logic, numerical computation, financial calculation, regulatory rule engines where the correctness criterion is algorithmic, not type theoretic. In that case, the branch coverage investment pays for itself immediately because the types alone do not certify correctness. But for a typical business logic service with CRUD operations and workflow orchestration, MyPy first, coverage second.
Good. Now the expert level question, and I want to say explicitly before I ask it that there is no safe answer here. This is designed to be uncomfortable. Python 3.13 introduced experimental free-threaded mode, the no GIL build. You are the technical authority at an organization that has a Python code base with 200,000 lines of production code and 37 third-party C extension dependencies. A board-level executive has read a technical blog post and is asking why your team is not adopting free-threaded Python to unlock the full potential of modern multi-core hardware. Here is what I want from you, not the diplomatic answer, not the "it is experimental" disclaimer. Tell me what you actually say in that meeting, and then tell me what the real technical blocker is that the blog post definitely did not mention.
In the meeting, I say something like this: free-threaded Python is a genuine architectural advancement and we are watching it carefully. Our current blocker is not Python itself. CPython 3.13 is ready for experimentation. Our blocker is our dependency surface. We have 37 C extension dependencies. Every single one of those was written with the assumption that the GIL exists and protects shared state in C code that interfaces with Python objects. In free-threaded mode, that protection is gone. We need to audit every one of those extensions before we can tell you whether free-threaded mode is safe for our workloads, and that audit is not something we can hand to a junior engineer. That is the meeting answer. Now, the real technical blocker the blog post did not mention, the GIL is not just a Python level concurrency primitive, it is a correctness guarantee for C extensions. Many C extensions maintain internal caches, reference counts, or mutable state that is accessed from extension code without Python level locking because they assumed the GIL would prevent concurrent access. In free-threaded mode, two Python threads can simultaneously call into extension code that was never designed to handle concurrent access. The result is not a Python exception, it is a memory corruption event in C code. It may not crash immediately. It may produce subtly wrong results. It may crash non-deterministically under load, and it will not be caught by your Python test suite, which runs single-threaded by default, and will not be caught by MyPy, and will not be caught by code review unless the reviewer knows to look for GIL dependency in C extension code. The audit I would run before recommending free-threaded adoption for each of the 37 extensions, check whether they have explicitly declared thread safety in their documentation, check whether they have a test suite that runs with the free-threaded build, and check whether they have a GIL release pattern in their C code that suggests they were written with multi-threaded access in mind. Any extension that fails all three checks is a risk item. On a typical production dependency set, I would expect 8 to 12 of 37 to fail this audit, and those 8 to 12 are the ones that will cause production incidents if you adopt free-threaded Python without addressing them.
The GIL as a correctness guarantee for C extension state. That is the point that almost nobody writes about. Final expert level question, and I mean it when I say this one has no comfortable answer. You have 19 years of Python. You have seen every architecture pattern come and go, microservices, serverless, event sourcing, hexagonal architecture. If you had to name the single idea that the Python community, not individual engineers, the community as a collective, has consistently been wrong about in its architectural guidance, and that wrongness has cost production systems real reliability or real maintainability, what is it?
The Python community has collectively underestimated the cost of dynamism at architectural boundaries, and I say this as someone who loves dynamic Python and has used it expertly for 19 years. The culture around Python has historically celebrated the flexibility of duck typing, dynamic dispatch, and runtime introspection as features, and they have features, genuinely powerful ones. But that celebration has created a cultural norm where making things explicit types at API boundaries, explicit schema definitions between services, explicit contracts between modules, feels like fighting the language. It feels like Java-style over-engineering. And that cultural norm has led to an enormous number of production systems where the system's behavior is an emergent property of runtime decisions that no one fully modeled. The specific cost in Python code bases that lack explicit boundaries, the architecture lives in the runtime, not in the code. You cannot read the code and understand the system. You have to run the code and observe the system. That means new engineers take longer to become productive. It means refactoring is genuinely dangerous because the blast radius of a change is underdetermined. It means incidents are harder to diagnose because the state of the system at failure time is not something you could have predicted from static analysis. The Python community has gotten much better at this. Pydantic, data classes, protocol types, type did, these are all moves toward explicit contracts. But there is still a strong cultural undercurrent that treats explicitness as overhead rather than as documentation that the system writes for itself. My honest position, Python's dynamism is most valuable inside a well-defined boundary. At the boundary itself, between services, between modules, between teams, explicit is almost always better regardless of what the language makes possible.
Alright, rapid fire. I want short, opinionated answers. 1 to 3 sentences. We have 6 questions, and I want your actual opinion, not the hedged version. Ready?
Ready?
1. Asensio.gather versus Asensio.group. For new production code written today, which do you mandate and why in one sentence?
task group because it fails loudly and cleanly when any child task fails, whereas gather with return unscore exception sake false has non-obvious cancellation semantics that have caused production incidents in code I have reviewed. The structured concurrency model is worth the migration cost.
2. JavaScript and Python increasingly share full stack roles. TypeScript on the front end, Python on the back end. In your experience, what is the single most dangerous assumption that Python engineers make when they first write TypeScript that causes production bugs?
That TypeScript's type safety extends to runtime. Python engineers coming from Pydantic assume that if the TypeScript compiler accepts the code, the runtime value will match the type. It does not. TypeScript types are erased at compilation and a JavaScript API response can hand you anything. The same engineer would never trust unvalidated input in Python will happily destructure a fetch response in TypeScript without any runtime validation.
3. Property-based testing with hypothesis. Genuine engineering investment or expensive exploration for most teams.
Genuine investment for any code with the mathematical invariant parsers, serializers, numerical functions, state machines. Expensive exploration for CRUD application logic where the interesting failures are business rule failures, not edge cases in input space. The mistake is applying it uniformly. It should be applied surgically where invariant reasoning is possible.
4. Java engineers joining a Python team is increasingly common. What is the one Python concept that Java engineers most consistently misapply in ways that make the code base worse?
Getter and setter reflexes. Java engineers instinctively wrap every attribute in a private field with a get and set method because in Java, that is how you preserve the freedom to add validation later without breaking the AB. In Python, it is pure noise. You expose the attribute directly and reach for a property only on the day you actually need computed access or validation, and the call side never changes when you do. The Java habit produces classes that are 80% ceremony, and worse, it trains the next reader to expect that the ceremony means something, so they card it forward. The fix is a one-sentence code review rule, no property until it does something. A bare attribute cannot.
5. You have to choose one. You can only ever write test before the code, strict TDD, or you can only ever write test after the code is in production, no unit test, only integration tests. Which world produces better software and why?
Tests after the code is in production, integration tests only. Here is why. The integration test suite test what the system actually does in the environment it actually runs in. Unit tests with mocks test what the engineer imagined the system would do in an environment that does not exist. If forced to choose, I want test that can prove the system is correct, not test that prove the code matches its own mock assumptions. The unit testing world produces higher confidence in greenfield development. The integration testing world produces higher confidence in production correctness. Given the choice, I optimize for what matters in production.
Last one. A junior engineer on your team says, I have been writing Python for 3 years. What should I study for the next 6 months to operate at a senior level? You give them one learning investment, one area, one recommendation. What is it?
Study how operating systems and networks actually work, not at the application layer but at the system call and protocol level. Read the TCP spec, understand what a socket is at the file descriptor level, read about how the OS scheduler works, not because they will write kernel code, but because every Python abstraction, async IO, multiprocessing, HTTP clients is a thin layer over operating system primitives. Engineers who understand the layer below their abstraction can reason about failure modes that are invisible to engineers who only understand the abstraction. That understanding is what separates senior from mid-level more reliably than any Python-specific knowledge.
Saket, this has been one of the sharpest and most honest conversations we have had in this series. Before I let you go, 2 things. First, what is the single most important disposition? Not a skill, not a framework, not a tool, that you think separates engineers who are genuinely operating at a distinguished level from engineers who are technically very strong but working below that level?
The disposition is intellectual honesty under load, specifically the reflex to make your own uncertainty visible instead of hiding it. Technically strong engineers can be wrong confidently. The distinguished ones have trained a different reflex. When they hit the edge of what they actually know, they say so out loud, and then they listen forward from what they can defend. Everything we touch today has that shape underneath it. The coroutine localase, the whole point was noticing that single-threaded does not mean atomic, which requires admitting the intuition you started with was wrong. There might be questions. The honest answer was always, it depends on the contract, not a slogan. The dynamism cost, that is me being critical of the thing I love most about the language. Why does this separate the levels? Because at the distinguished level, you are the person whose judgment other people build on. If you round your uncertainty up to confidence, you are handing your whole organization a false floor and they will pour concrete on it. The engineer who says, here is what I know, here is what I'm assuming, and here is how we would find out, that person is safe to build on. Raw capability without that honesty is a liability that scales with seniority. So if I compress 19 years into one line, the goal is not to know everything, it is to be exactly as certain as the evidence warrants, and to say so plainly. That is the rarest thing, and it is almost never on the resume.
Be exactly as certain as the evidence warrants, and say so plainly. That is the note to end on. Saket, thank you. 19 years. And it showed in the specifics, the context manager protocol as a general resource lifecycle hook, the coroutine local toss CTO double spend that most people meet for the first time in an incident review, the cross-language contract governance, and a closing disposition that is worth more than any single technical answer in this episode. If you're hiring at the staff, principal, or CTO track level, and today sounded like your problems, reach out to us at Kritia AI Labs and we will make the introduction to Saket directly. And to everyone watching, this is the Kritia AI Labs Tech Interview Series. If it sharpened your thinking, like the video and subscribe. The full mock interview playlist is linked in the description, spanning senior through CTO track sessions. Drop a comment with the question that made you pause the hardest and defend your answer. We read everyone. See you in the next one. Welcome back to the Kritia AI Labs Tech Interview Series, the show where engineers grow, learn, and get hired. I am Balu, Senior Technical Architect at Kritia AI Labs, and today we are doing something that I have genuinely been looking forward to for weeks. We have a guest who has spent 20 years not dabbling, not side projecting, not using Python as a glue script between real tools, 20 years building production systems, leading engineering organizations, contributing to the language ecosystem, and watching Python transform from something people quietly apologized for using into the backbone of the world's most consequential AI infrastructure. He is in the market right now, looking for a CTO or chief architect role, and he agreed to sit down for a live, unfiltered mock interview at the highest technical register I can aim for. This is not a tutorial. This is not a top 10 Python tips episode. What you're about to hear is what a genuinely senior technical interview looks like. The kind where the questions are designed to find the edges of what someone knows, not the center of it. For those of you preparing for principal engineer, staff engineer, CTO, or chief architect interviews, take notes, pause, rewind. This is the level of thinking you need to demonstrate. His name is Saket, 20 years of Python, ready to find his next stage. Saket, welcome to the show.
Balu, thank you. I will be honest, I have listened to enough of these episodes that sitting on this side of the microphone feels strange. But strange is good. Let's do it.
Good. Let's start somewhere that sounds simple but isn't. You have 20 years with Python, which means you watched it go from a scripting language that serious engineers apologized for using to the dominant language in AI infrastructure. But I want to ask a different version of that origin question. What is the thing Python got architecturally right in its early design decisions that the language community has never properly credited, not celebrated, actually credited in the sense of understanding why it worked, causally, not aesthetically?
The honest answer is the namespace model, and I mean specifically the decision to make namespaces first-class dictionaries that are inspectable, readable, and composable at runtime. Now people celebrate this, but they celebrate it as a feature. Oh, you can do metaprogramming, you can do dynamic dispatch, isn't that cool? That is the aesthetic appreciation. The causal argument, the reason it worked, is different. The causal argument is that it made the language trivially embeddable and trivially extensible without requiring the host to understand the internals. When you embedded CPython into a C application in 2002, you did not need to understand the object model deeply. You pushed values into a namespace dictionary, called into the interpreter, pulled values back out. The interface surface was a dictionary. Everyone understands a dictionary. That lowered the cost of adoption for scientific computing, for system scripting, for game engine tooling, because the embedding API was essentially a key value store. And that is why NumPy happened. Not because Python was fast, because the cost of connecting Python to a fast C library was a namespace dictionary and a handful of C API calls. The community celebrates the expressiveness but does not credit the interface simplicity that made the ecosystem flywheel possible in the first place.
There is a keen causal argument. Now let me stress it. That same decision, namespaces as mutable runtime dictionaries, is also the source of one of the most persistent security criticisms of Python. The global namespace is trivially poisonable, module-level state is shared across threads with no access control, and attribute lookup is a dictionary probe that can be intercepted at any point in the MRO chain. How do you hold both of those as simultaneously true without retreating to everything is a trade-off?
I hold them as true by recognizing that they are not trade-offs at the same level of abstraction. The security criticism operates at the level of, given an adversary with code execution in the same process, the namespace model provides no defense. The adoption benefit operates at the level of, given a new domain wanting to integrate with Python, the cost of entry is low. Those are different threat models and different user models. The namespace as designed was not made in ignorance of the security implication. It was made with an explicit assumption that Python would be used in trusted collaborative environments, scientific computing, sysadmin tooling, internal automation. The mistake, and this is the mistake the community does not properly own, was not auditing that assumption when Python moved into web serving, into multi-tenant SaaS, into context where the adversarial model changed completely. The design decision was right for its context. The community was slow to recognize when the context shifted, so I hold both true by separating the design decision from the deployment context. The decision was architecturally sound for what it was designed for. The failure was the community not revisiting the assumption explicitly.
Good. One more follow-up before we move on. The free threaded Python work, PP703, is under active pressure right now. The steering council is making decisions. If you were advising them specifically on whether to preserve the mutable namespace as dict semantics under a no-GL model, where concurrent writes to the same namespace become a real data race, what is your actual advice?
My advice is preserve the semantics but make the race condition visible at the language level, not silent. The worst outcome is silent data corruption on concurrent namespace mutation. The second worst outcome is adding locks everywhere and calling it safe. Because that just moves you back to GIL equivalent serialization through a different mechanism. What I would push for is a mode where concurrent writes to the same namespace emit a diagnostic, a warning at minimum, an exception in strict mode, so that code that was written, assuming GIL protection fails, loudly rather than producing subtle state corruption. The broader point is, the free-threaded experiment broke a number of production libraries. I saw this firsthand with libraries that used module-level caches as singletons, not because the design was wrong, but because the DIL had been functioning as an implicit synchronization primitive that nobody documented. You cannot remove an implicit primitive without making the assumption explicit first. That is the governance failure in PIP 703 as initially drafted.
Okay, let's move to something concrete. This is still warm up, but it's going to feel like a cold shower. You are 3 weeks into a new role. CTO, Principal Architect, pick the title. The team walks you into a meeting room and shows you a service, 50,000 requests per second, P50 latency at 4 milliseconds. Healthy, P99.9 is 800 milliseconds. Nobody can explain it. They have been living with it for 4 months. Before you touch a profiler, before you read a single line of code, walk me through the questions you ask, and more importantly, tell me what you are trying to rule out with each question, not just what you are trying to find.
The first question I ask is, what is the shape of that 800 millisecond spike? Is it periodic, random, or correlated with a specific input class? Because those three cases have almost non-overlapping root causes. Periodic spikes rule in GC pressure, lease renewal, background compaction jobs, cron adjacent workloads. Random spikes rule in lock contention under high concurrency, cold cache paths, or non-deterministic network jitter from a dependency. Input correlated spikes are the most interesting. Those point at algorithmic complexity cliffs, data-dependent branching, or serialization pathology on specific payload shapes. I am ruling out the wrong diagnostic space before I spend time in it. If I go looking for DC pressure when the spikes are actually input correlated, I will waste 2 days. Second question, does this service call any downstream dependency synchronously in the hot path? And if so, what is the P99.9 of that dependency? Because 800 must have P99.9 with a fall M as P50 suggests the tail is coming from somewhere that the median path does not touch. Synchronous dependencies with their own tail latency are the classic source of this pattern. I am ruling out the hypothesis that this is a pure self-contained algorithmic problem. Most of the time in a service at 50k RPS, the tail is not the algorithm, it is the I/O. Third question. What changed 4 months ago? Not what did we deploy, what changed in the environment? Traffic volume, traffic shape, infrastructure version, database, instance class, anything. 4 months of living with a problem means either it predates current team memory or something crossed a threshold 4 months ago. I am ruling out the possibility that this is a new condition masquerading as a chronic one. Fourth question, and this is the one teams always skip, is that 800 me is actually affecting users in a measurable way? I want to see the business metric correlation before I decide how hard to push on this. Because the answer to what do you do with 800 MSP 99.9 is completely different if it is affecting checkout flows versus if it is affecting a background analytics query.
You said you asked about traffic shape and input correlation first. Most engineers would go straight to infrastructure, GC logs, thread dumps, CPU utilization. Why input correlation before infrastructure for you?
Because infrastructure problems affect the distribution uniformly under load. If you have a GC problem or a thread contention problem, you expect to see elevated latency across percentiles. Your P90 also moves. Your P95 also moves. When P50 is healthy and P99.9 is catastrophically bad, you are looking at a bimodal distribution, two populations of requests, not a uniformly degraded population. Bimodal distributions almost always mean either a subset of inputs is hitting a different code path or a subset of requests is encountering a specific resource that most requests do not. Infrastructure problems rarely produce bimodal latency without also producing visible signals elsewhere. CPU saturation, memory pressure, network errors. So when the P50 is clean, I trust the infrastructure first and interrogate the input space. It is a probabilistic prior, not a rule.
Let's go into the deep end, testing. Here is a specific claim I want you to evaluate, and I want a real evaluation, not a diplomatic one. The claim, mutation testing is the only honest measure of test suite quality. The reason most engineering organizations do not use it is not cost. It is that they do not want to know the answer. Do you think that is right? And more specifically, at what organizational size and code base maturity does Mutation testing stop being a diagnostic tool and start being a liability that actively degrades engineering culture.
The claim is 90% right. The 10% I would push back on is the framing of they don't want to know the answer, because that implies a kind of institutional cowardice, and I think the actual mechanism is more subtle. Most organizations do not use mutation testing because the result is not actionable at scale. That is not cowardice, that is a real engineering problem. But let me grant the code coverage is largely a lying metric. A test that calls a function and asserts nothing meaningful about the output will give you coverage and give you a 0 mutation score. It will detect almost no mutants. High coverage with low mutation score is the most dangerous state a test suite can be in, because it gives the team false confidence while providing no actual regression protection. The claim is right that most organizations do not want to confront that. Now, at what point does mutation testing become a liability? I would put the threshold at 2 dimensions, not 1. The first dimension is codebase age. In a codebase older than 3 years with multiple generations of engineers, mutation testing produces a flood of results in code that has not changed in 2 years. The team drowns in findings that are not actionable because the code is stable and the test, while not mutation complete, have not produced incidents. The cognitive load of triaging that backlog is real. The second dimension is team velocity. On a team shipping multiple features per week, mutation testing adds a CI feedback cycle that is measured in hours, not minutes. On any non-trivial code base, that cycle time directly affects how developers experience their work. I have seen mutation testing introduced in organizations where within 6 weeks the rule was being silently bypassed, people running with mutation checks excluded from their PRs. When a quality tool starts getting bypassed, it is not raising the floor anymore, it is training the team to route around quality checks. So my answer, mutation testing is a powerful diagnostic tool up to about 30 engineers and up to about 3 years of code base age. Past that threshold, you need to scope it, run it on specific modules during their active modification window, not as a blanket CI gate.
Let's make it concrete. A principal engineer on your team runs mut across the code payment processing service. The mutation score comes back at 34%. That number lands on your desk on a Thursday afternoon before sprint planning on Friday. What do you do with it? And I mean operationally in the next 24 hours, not strategically over the next quarter.
The first thing I do is not put it in the sprint. That is the trap. You get a scary number, it goes into the backlog as improve mutation score, and then it competes with feature work forever and never wins. What I do in the next 24 hours is ask the principal engineer to give me category data on these surviving mutants. Mutation testing tools will tell you the surviving mutants, the mutations that your test did not catch. I want to know what classes of mutations are surviving. Are they boundary condition mutations? Are they Boolean operator flips? Are they arithmetic operator substitutions? Because a 34% mutation score with surviving mutants concentrated in boundary conditions is a very different problem from a 34% score with surviving mutants concentrated in the core transaction flow. If the surviving mutants are in boundary conditions, input validation, edge case handling, that is a coverage expansion problem, which is tractable and can be addressed incrementally. If the surviving mutants are in the transaction commit path, the actual payment processing logic, that is a structural problem. It means your tests are not asserting the invariance of your most critical code that needs immediate attention before the next deploy. In the sprint planning Friday morning, I do not introduce a fixed mutation score story. I introduce a specific bounded story, audit and harden test assertions for the transaction commit path based on mutation analysis. Scoped, targeted, not open-ended. The 34% number itself goes into a dashboard that we track over time. You do not fix a number, you fix the specific weaknesses the number revealed.
Is there a class of Python code where achieving high mutation scores is structurally impossible even in a rigorously tested system? And if so, what does that tell you about the metrics limits?
Yes, blue code and orchestration code. When you have a function whose entire job is to call 3 other functions in sequence and pass their outputs through, mutation testing will generate mutations like swap the order of calls or skip the second call. But if those functions have side effects, if they write to a database, emit to a message queue, call an external API, your test cannot easily assert that they were called in the right order, mocking everything or running a full integration test. And if you mock everything, the mutation of skip the second call still passes if your mock is not asserting call order. So your mutation score on orchestration code will be artificially low, not because your tests are bad, but because the observable output of the orchestration function is not directly connected to its internal sequencing in a way that a unit test can probe. What this tells you about the metric, mutation testing is fundamentally a metric about decision logic coverage, not about coordination logic coverage. It is excellent at finding untested branches in algorithmic code. It is structurally blind to coordination failures. For coordination logic, the light verification mechanism is not mutation testing, it is integration testing with real dependencies or property-based testing with hypothesis exploring ordering invariants. The organizations that treat mutation score as a universal quality metric are missing this distinction entirely.
Moving to security. And I want to go somewhere specific that most security conversations avoid. Python has no linear types, no ownership model, no capability-based access control baked into the language. Java has final, private, sealed classes. The security manager existed even if it was deprecated. There are structural guarantees available in Java that Python does not provide. I want you to name a specific class of security vulnerability that Java's type system prevents structurally, not through discipline, not through convention, but because the language makes the vulnerable code impossible to express. And then I want the correct compensating design pattern in Python at the language and module boundary level, not at the framework level, not user-validated input library. At the module boundary,
the clearest example is capability confinement, what Java achieves through private constructors, sealed classes, and a module system strong encapsulation. In Java, if I declare a class with a private constructor and expose only a factory method, it is structurally impossible for client code to construct an instance through any other path. The type system enforces the construction invariant. The classic security application of this is capability objects. An object whose existence in a variable is proof that the holder has been granted a specific capability. In Java, that proof is structurally enforced. You cannot have one of these objects unless the system gave it to you through the authorized path. In Python, you cannot enforce this structurally. I can prefix a class with a single underscore convention and put a stern comment in the docstring, but nothing prevents a caller from importing the module and instantiating the private class directly. The convention is not enforcement. The compensating pattern at the module boundary level, and this is the one that most Python security guidance misses, is to use the module itself as the capability boundary combined with all and then add deliberate import surface control, and then add a runtime invariant check at the factory entry point that detects out-of-band construction. Concretely, you define a sentinel value, a unique object created at module import time, and store it as a class-level private attribute with a name collision-resistant mangled name. Your factory method sets this sentinel on the constructor object. Your capability checking code asserts that this sentinel is present and is the specific module-level instance, not just any truthy value. This means that even if an adversary constructs an instance directly, they will not have the correct sentinel and any capability check will fail. It is not as strong as Java structural guarantee, but it converts a silent vulnerability into a loud runtime failure, which in Python is the realistic security boundary you can actually hold.
You described a pattern that requires the entire team to understand the sentinel invariant and maintain it across all paths. How do you enforce that discipline in code review without it becoming a human bottleneck, where every PR now requires someone who understands the capability model to review it?
You codify the invariant as a test, not as a review discipline. You write a specific test and this lives in the security best suite separate from the unit test that attempts to construct the capability object through every non-factory path you can enumerate, direct class instantiation, copy.copy.deepcopy, deepbt, decopy, pickle deserialization, new nostripy bus object.set at disk injection. That test asserts that every non-factory construction path either raises an exception or fails the capability check at the first usage point. When a new engineer joins and modifies the capability class, the test breaks if they violate the invariant. The enforcement mechanism is the CI pipeline, not the code reviewer. The code reviewer's job becomes verifying that the test is still present and comprehensive, not verifying the invariant itself. This is a general principle I apply to security critical patterns in Python. Whenever you have a discipline that requires human vigilance to maintain, convert it into a machine checkable assertion. The assertion does not have to be a type system guarantee. It has to be a thing that breaks loudly and visibly in CI. That is a weaker guarantee than Java's structural enforcement, but it is a realistic guarantee for a Python codebase.
One targeted follow-up. Does introducing typed dict and protocol into a security critical internal API actually help this problem, or does it create a false sense of protection?
False sense of protection with a specific mechanism. Protocol and type dict are checked by myp and pwrite at static analysis time. They are not enforced at runtime. A type dict is a regular dict at runtime. A protocol is structuring any object with the right attribute satisfies it, whether or not it was intended to. The specific failure mode, you define a security credential as a typed dict with specific required keys. Your type checker tells you that every function receiving a security credential is receiving the right shape. But at runtime, if an adversary can inject a plain dict with the right keys into the call path through deserialization, through a shared data structure, through monkey patching, the type annotation provides zero runtime protection. The function receives the dict, mypy is satisfied, and the adversary's injected values flow through unchecked. Type dict for security critical APIs is useful for developer experience and for documentation of intent. It is not a security control. The moment you treat a MIPI passing annotation as a trust boundary, you have made your system less secure than one with no annotations but explicit runtime validation. Because the annotations suppress the intuition that validation is needed, the correct pattern use protocol and type dict for developer ergonomics and pair them with post askerentis mintis validation in data classes or with pedantic models with model asker config equals config dict strict stick true for anything that crosses a trust boundary. The static type annotation tells you the intention. The runtime validation enforces the invariant.
Let's talk about cross-language experience. You have led organizations where Java engineers join Python teams. I'm not asking about syntax fiction. I am not asking about PP8 versus Google Java style. I want the specific mental model that a senior Java engineer carries, something they built correctly and reliably for years in Java that becomes actively destructive when they apply it to a Python code base. Not a bad habit, a good habit that breaks things in Python.
The single most destructive good habit is defensive object construction through interface proliferation. In Java, you are taught correctly to depend on abstractions, not concretions. You define an interface for every significant dependency. You inject implementations through constructors. You never touch a concrete class directly in application code. This produces systems that are testable, extensible, and loosely coupled. In Java, this is excellent engineering practice. When a senior Java engineer joins a Python team, they bring this habit. They create abstract base classes for everything. They define explicit interface hierarchies. They build factory patterns for object construction. They add dependency injection frameworks. And in Python, this becomes actively destructive for a specific reason. Python's duck typing model means the interface is the usage point. The test is the specification. When you add an explicit abstract base class hierarchy in Python, you are not adding a structural guarantee. Python does not enforce that a class fully implements an abstract interface at class definition time in the way Java does with compile time checks. What you are actually adding is indirection. You are adding layers that make the code harder to trace and harder to modify without adding correctness guarantees. The specific failure mode, a Java-trained engineer builds a service where every component has an interface, an implementation, and a factory. The Python team then needs to modify the payment logic. Instead of opening one file and changing one function, they have to navigate 5 files: the interface, the abstract base, the concrete implementation, the factory, and the dependency injection configuration. They made the change in the wrong file, or they add a new method to the implementation and forget the abstract base class definition. The system still runs. Python does not enforce the interface at construction time, but now the interface and the implementation are silently divergent. The good Java habit of explicit interface boundaries became a confusion multiplier in Python because the enforcement mechanism that made the pattern safe in Java, the compiler, does not exist in Python.
A senior Python engineer listening to that might say, that is just a preference difference, both styles work. Where is the correctness failure, not just the ergonomic fiction?
The correctness failure is in the testing surface. When you have an interface implementation factory pattern in Python, your unit tests typically mock at the interface level. You stub the abstract base class and inject the stub. This means your test is verifying behavior against a contract, the interface that the Python runtime does not actually enforce on the concrete implementation. The concrete implementation can silently violate the interface contract in ways that might be misses the return type winding, raising undeclared exceptions, mutating inputs, and the tests that mock the interface never catch those violations because the mock implements the contract correctly and the real implementation is never exercised in isolation against the contract. In Java, if your concrete implementation does not satisfy the interface, the compiler tells you, you cannot ship a class that claims to implement payment processor but returns the wrong type from process payment. It does not compile. In Python with the Java style pattern, you can ship a concrete class that the abstract base class claims is an implementation of payment processor, but at runtime it raises a not implemented error on a method because someone forgot to override it, and you find out in CI. That is a correctness failure, not a preference difference.
And the reverse? Is there a Python mental model that becomes destructive in Java?
Yes, the REPL first exploratory construction model. Python engineers are conditioned to explore systems by constructing objects at a REPL, inspecting their state and iterating. This produces a mental model of software construction as incremental state inspectable, always running. You build a small thing, observe it, extend it. When a Python engineer moves to Java, they bring this model. They resist designing data structures and interfaces upfront because they are used to discovering them through exploration. They write large mutable state-heavy classes because in Python you could always inspect and patch the state. They avoid generics because in Python you just duck type your way to the right thing. In Java, this produces code that compiles, but that the type system cannot reason about safely, excessive use of object or raw types, mutable shared state without synchronization, classes that do too many things because the engineer was discovering responsibilities rather than specifying them. The Java compiler catches some of this but not all, and in a concurrent Java system, the Python engineer's instinct to treat shared state as inspectable and patchable leads to real data races. The mental model difference: Python engineers think of objects as values that can be interrogated at any time. Java, especially in concurrent contexts, requires you to think of shared objects as resources with explicit access protocols. That transition is the hardest thing for a Python native engineer to internalize.
Let's move to something that has caused real production pain across stacks. Your Python backend emits a pydantic model. There is a field typed as optional datetime. That value crosses a serialization boundary as JSON and lands in a TypeScript frontend. Walk me to every place in that pipeline where the semantic meaning of optional diverges, what pydantic believes, what the JSON specification says, what TypeScript's type system encodes, and what the JavaScript runtime actually does at execution time. And then tell me which of those divergences has actually caused a production incident in your experience.
This is a beautiful question because each layer uses the word optional to mean something subtly different, and those differences compose into real bugs. Start with Pydantic. In Pydantic v2 optional, datetime means the field can be either a datetime object or none. When Pydantic serializes this to JSON, if the field value is none, it emits the JSON literal null. If the field is absent from the source data during deserialization, Pydantic requires a default. If no default is specified, the field is required even though it is typed optional. So in Pydantic, optional means nullable, not omittable. This is the first divergence. Now the JSON specification.json has no concept of optionality as a schema property. That is a JSON schema concept, not a JSON specification concept. In raw JSON, null and a missing key are two different things. A field with value null is present and explicitly null, a missing field is absent. The JSON spec does not conflate these. Pydantic serialized output will emit the key with null value. So from the JSON specs perspective, the field is present and null, not optional. Now TypeScript. TypeScript's optional datetime equivalent is datetime, nullime, undefined, or in practice the TypeScript engineer might write null or date undefined or date undefined or date undefined depending on what they understand optional to mean. If they write date in null, they expect the key to always be present in the JSON, just sometimes null. If they write date in undefined, they might expect the key to sometimes be absent. If they write date in null in defined, they are covering both cases. The TypeScript type annotation and the JSON field semantics are not mechanically linked. The TypeScript engineer is making an assumption about what the Python backend does. Now the JavaScript runtime. JavaScript does not distinguish between null and undefined in most operations. Both are falsy. Both return undefined on property access of their properties. Both cause type error if you try to access subproperties. If your TypeScript code does response.attd.releasestring without a null check, you will get a runtime type error regardless of whether updated is null or undefined. The type system warned you, but the runtime does not care about the distinction. The production incident from my experience, we had a Python service that emitted optional datetime for a last login field. The Pydantic model had no default, so the field was always present in serialized output, either a datetime string or null. The TypeScript front-end engineer typed it as last login date with the separator meaning date undefined. Their null check code was if user.lastLogin, which catches undefined and truly checks the date object. When last login was null in the JSON, TypeScript received null. The type annotation said date as a date undefined, but null is not undefined. So TypeScript's strict null checks would have caught this, but we were running with strict null checks false at the time. So null was assignable to date undefined. The if user.lastLogin check evaluated null as falsy. So the display logic skipped the date correct. But a second code path that accessed user.lastLogin.toISOstring without a guard was never triggered in testing because our test fixtures always had a non-null last login. In production, the first user with a null last login hit that code path and the frontend crashed with a type error. 3 layers contributed: Pydantic's null not undefined semantics, TypeScript's strict null checks being disabled, and a test fixture gap. The fix was not at the TypeScript layer alone. It required enabling strict null checks, correcting the type annotation to date life null, and adding a fixture with an explicit null value.
If you're designing a contract-first API spec process for a team of 5 Python engineers and 3 TypeScript engineers, what is the single governance rule you would make non-negotiable?
The single non-negotiable rule, the OpenAP schema, is the source of truth. It is generated from the Python backend, and the TypeScript client types are generated from that schema by automated tooling, OpenAP TypeScript or equivalent, and the generated types are never manually overridden. The reason this is non-negotiable: as soon as a TypeScript engineer is allowed to manually override a generated type, you have 2 sources of truth. The next time the Python backend changes the field from optional datetime to datetime, The OpenAPI schema updates, the generated TypeScript type updates, and the TypeScript compiler immediately surfaces every call site that did not handle the non-optional case. If the TypeScript engineer had manually overridden the type to date life null ifs undefined, the generator's correct output gets overridden, the change is silent, and you discover the divergence in production. The second half of the rule, which people often omit, the OpenAPI schema must be validated in CI on the Python side. Any PR that changes a pydantic model must produce a schema diff that is reviewed and approved before merge. The contract is versioned. Breaking changes to the contract require explicit approval, not just passing test.
Does OpenAPI 3.1's adoption of JSON Schema Draft 2020-12 actually resolve the nullable versus optional problem? Or does it just make the problem more formally specified while still leaving it divergent in practice?
More formally specified and still divergent in practice with a specific reason. OpenAPI 3.2 had a custom nullable true extension that was not part of JSON schema, which meant tooling handled it inconsistently. OpenAPI 3.0 replaced that with proper JSON schema type string null, which is unambiguous about nullability. But the divergence between nullable and optional, whether the key is allowed to be absent versus whether the key is allowed to be null when present, is now formally expressible but requires explicit use of required arrays at the object level. A field that is not in the required array can be absent. A field typed as string null can be present and null. A field that is both not required and typed nullable can be either absent or present and null. The practice problem, pydantic v2's OpenAPI schema generation as of current versions does not always correctly distinguish between this field has optional street with no default, it is required, just nullable versus this field has optional street with a default of none, it is optional and nullable. The generated schema treats Big Bus case similarly, which produces an OpenAPI spec that overstates the option up-in, spec that overstates the option out. TypeScript tools then generate a type that treats a required but nullable field as potentially absent, and you are back to the same divergence with better documentation. The formal spec improvement is real. The tooling catching up to the formal spec is a work in progress.
One more technical deep dive before we get into your war stories. This one is about CPython internals and security. CPython's bytecode is not an officially stable ABI, but it is stable enough in practice that production systems depend on it. .pyc caching, Marshall, code object introspection, compiled code passed to eval and exec. Walk me through a specific technically realistic attack vector where an adversary who can write to a Python packages th mica to Kurigash but cannot modify the .py source file can achieve arbitrary code execution. And then tell me what the correct mitigation is at the deployment infrastructure level.
The attack is straightforward at the bytecode level and subtle at the detection level. When CPython imports a module, it checks whether a bytefilesys file exists in bycache that corresponds to the bytepy source. If the .pc exists and the magic number matches the interpreter version, CPython by default validates the .pc by comparing the source file's timestamp and size as embedded in the .pc header against the actual source file. If they match, it skips recompilation and loads the cached bytecode directly. Here is the attack: an adversary who can write to pycache mudscrafts a malicious .pyc file. They set the embedded timestamp and size in the .pc header to match the current values of the legitimate .p source file. They can beat the source file's metadata even if they cannot write to it. They then inject arbitrary bytecode into the pyse body. Bytecode that, when executed, does whatever the adversary wants, spawning a sub-process, exfiltrating environment variables, establishing a reverse shell. The next time any code imports that module, CPython sees the .pyc header matches the source metadata, skips recompilation, and executes the adversary's bytecode. The .py source file is pristine. A developer who catches the source file is nothing wrong. The malicious code executes at import time, which typically means at application startup before any application level security controls are active. The detection difficulty, standard file integrity monitoring tools check the .py files. The .py files are often excluded from integrity monitoring because they are just compiled cache and their content is expected to be derived from the source. Now, the mitigation at the deployment infrastructure level, the correct mitigation is to treat krish.ppk directories as uncrusted inputs and to deploy applications with bytecode validation configured for hash-based validation rather than timestamp-based validation. Python 3.8 introduced hash-based .pyc files. You compiled with Python num compiler invalidation mode checked hash, which embeds a hash of the source content in .pyc rather than a timestamp. An adversary who cannot modify the source file cannot produce a .pyc with the correct source hash, but the infrastructure level mitigation that is actually robust is simpler. Do not deploy to others' cache directly from untrusted sources. In a containerized deployment, build your container image with a step that deletes all SPP cast derecomposes from source inside the container, then marks the container file system read-only. An adversary who cannot write to the container file system cannot poison the bytecode cache. The read-only file system constraint converts a soft defense hash checking into a hard infrastructure constraint.
Python 3.8's hash-based .pyc validation, does that actually close this vector? Or does it require a specific deployment configuration that most teams do not have?
It requires specific deployment configuration that most teams do not have, and the default configuration does not close the vector. By default, even in Python 3.12, the default invalidation mode is timestamp. Hash-based validation requires you to explicitly compile with invalidation mode checked hash. If you compile with invalidation mode unchecked hash, the hash is stored in the .pyc but is never checked at import time. It is only used for reference. That mode exists for performance, but it provides zero security benefit. The practical deployment picture, most teams that use compiler do not pass invalidation mode at all, which means they get timestamp mode. Most container build processes that include a Python Vim compile-all step are using timestamp mode. The hash-based protection is opt-in, not opt-out, and the documentation does not prominently frame it as a security control. So, my honest assessment, hash-based bodyhash.epc validation can close the vector when correctly configured with checked hash mode. In practice, the percentage of production Python deployments that are correctly configured for this is very low. The read-only file system constraint is a more reliably deployed control because it is enforced by the container runtime rather than by a compile time flag that an engineer has to know to pass.
Let's shift gears into your actual experience. I want to hear about a real system you built or inherited where the distributed systems failure mode was specific to Python's async model, not a general distributed systems problem, but one that would not have existed in a thread per request architecture. Give me the story, what you were building, what broke, and what the diagnosis taught you about how Python's cooperative multitasking model creates failure modes that people trained on threaded systems simply do not anticipate.
The system was a financial reconciliation service, a sensor-based, consuming from a Kafka topic, performing a saga pattern across 3 downstream services, a ledger write, a notification dispatch, and an audit log append. The saga had a rollback path. If any step failed, we needed to undo the previous steps in reverse order. The failure mode that emerged in production was not a rollback failure. It was a rollback timing failure that was specific to cooperative multitasking. In a thread per request system, each request has its own stack. If a step fails, the rollback logic runs immediately in that request thread. Other requests are not affected. The rollback is temporarily isolated to the request that failed. In our SNCU system, the event loop is shared. When a SATA step raised an exception and we entered the rollback path, the rollback was itself a sequence of awaitable calls. Await undo ledger seeker write, await undo ledger and hr await undo notification. What we did not account for between those await points, the event loop was processing new saga events. Those new sagas were successfully completing their ledger writes using the same downstream service. So we had a window between the first rollback await and the second rollback await, where the ledger service had seen our original write, then started processing new writes from concurrent sagas, and then received our undo operation. The undo operation's preconditions that the state was exactly as we had left it were no longer valid. The audit log started showing inconsistencies. The ledger had undone a write that by that point had been referenced by 2 subsequent transactions. In a thread per request system, this would have been impossible because the rollback would have acquired the appropriate locks and held them across the entire rollback sequence. In Asyncio, we had assumed that the non-blocking rollback was fast enough that no interleaving would occur. That assumption was catastrophically wrong under load. The diagnosis taught me a fundamental principle about Python async and sagas. Cooperative multitasking means you have no automatic isolation between concurrent operations during await points. If your saga rollback is not itself idempotent and reorderable, or if you are not using distributed locks that span your await chain, you will have rollback interleaving problems under any load that produces concurrent failures. The fix was two-part. We added a distributed lease, a release lock that was acquired before the first saga step and held until the rollback completed or the saga committed successfully. That lock acquisition was itself a single await call, so we moved it before the saga began, ensuring that the entire saga, including its rollback path, was mutually exclusive with concurrent sagas touching the same entity. The second part was adding idempotency keys to every saga operation so that if a rollback ran twice due to a crash during rollback, the second run was a no-op.
That Redis lock, it is an await call to acquire and an await call to release, which means the event loop can still do work between those. What protected the lock acquisition itself from becoming a race condition?
The lock acquisition is a single atomic operation at the Redis level. Set key value nxpxtl. The atomicity is at Redis, not at the Asyncio level. The await redis.setKeyValue nxxtltl call sends that atomic command and waits for Redis's response. From the Asyncio perspective, yes, the event loop does other work while we wait for Redis's network round trip, but other coroutines attempting to acquire the same lock are also sending the same setNX command to Redis, and Redis serializes those. Only one client wins the NX set. Redis's single-threaded command execution model is the atomicity guarantee, not Asyncio. This is an important conceptual point. In Asyncio systems, you cannot create mutual exclusion between concurrent operations using Python-level locking primitives like Asyncio. Unless all competing operations are in the same process. The moment you have multiple workers, multiple Kubernetes pods consuming from the same Kafka topic, Asyncio doc is completely useless for cross-process mutual exclusion. You need a distributed locking primitive whose atomicity guarantee is at the external service level. Redis setNX is the standard tool for this. The Asyncio layer is just the mechanism for the network call. The guarantee comes from Redis.
I want to ask about a different kind of hard moment. You have been in CTO adjacent and principal architect roles for a significant part of those 20 years. Tell me about a time you had to make a technical architectural decision that you were genuinely uncertain about, where the data was ambiguous and the team was split, and how you made the call and what happened.
The decision was whether to migrate a real-time data pipeline from a Python native streaming architecture using Asyncio with custom backpressure logic to Apache Kafka streams running on the JVM with a thin Python consumer layer. The team was genuinely split. The Python engineers believed the Asyncio architecture was fixable. We had throughput problems under high load, but they argued it was an implementation problem, not a platform problem. The infrastructure engineers were advocating for Kafka streams because they had operated it before and trusted it. The data scientists depended on the output and needed reliability guarantees. The data was ambiguous. Our Asyncio implementation was hitting 40,000 events per second before showing latency degradation. Kafka streams in comparable workloads at comparable companies was handling 500,000, but we were not a comparable company at that moment. We were at 40,000 events per second, and our growth projections were not obviously going to push us into Kafka Streams territory within the next 18 months. The uncertainty was real. Was this a platform capacity problem we were not yet experiencing, or an implementation quality problem we were actively experiencing? The way I made the call was to reframe the question. Instead of asking which platform is better, I asked, what is the cost of being wrong in each direction? If we stayed with Asyncio and it was a platform problem and we hit the wall in 12 months, the migration would be urgent, chaotic, and expensive. The data scientists would have an unreliable pipeline during a critical growth phase. If we migrated to Kafka Streams and it was an implementation problem, if the Asyncio architecture was fixable, we would have paid 3 months of migration cost unnecessarily, but the system would be more reliable and the team would have gained operational experience on a widely adopted platform. The asymmetry was clear to me. The cost of being wrong in the stay direction was higher than the cost of being wrong in the migrate direction. That asymmetry broke the tie. We migrated. What happened? The Kafka Streams platform performed exactly as expected. But what I did not anticipate was the team morale impact on the Python engineers who had fought for the Asyncio architecture. 3 of them felt they had not been heard, not because I made the wrong decision, but because I had framed the decision as cost of being wrong rather than let's try to fix the current implementation first. In retrospect, I should have time-boxed a 2-week sprint to attempt the fix before making the migration call. Even if the fix failed, the team would have felt that their position was genuinely tested. The technical outcome was correct, the process was not.
Alright, Saket, rapid fire round. I'm going to give you questions that I want answered in 30 seconds or less. Opinionated, no hedging. Ready?
Ready? Let's go.
Celery in 2026. Still a viable choice for new Python async workloads, or should teams building fresh systems reach for something else?
Avoid celery for new systems. The at least once delivery semantics and the idempotency burden it places on task authors are significant for complex workflows. If you are doing simple background tasks with no complex retry logic and no ordering requirements, celery is fine. For anything more complex, reach for temporal or a purpose-built workflow orchestrator. Celery's flexibility has produced more architectural debt than it has prevented.
Python's match statement, genuine addition to the language, or syntactic sugar or very fairly chains that engineers will misuse more than they use correctly.
Genuine addition for discriminated union handling. But the misuse rate in application code is high. Engineers reach for match when if a leaf would be clearer, and they underuse the structural pattern matching capabilities that are actually its strength. The sweet spot is type data class hierarchies. In anything else, I see more confusion than clarity.
An algorithm that is on log n in theory performs worse than an on squared alternative in your Python production benchmark at n equals 10,000. Your team lead insists on shipping the on log n version because it's the correct choice at scale. What do?
Ship the on squared version with a documented performance regression trigger, a benchmark test that fails if n exceeds the crossover point. Big O complexity is a theoretical model. Cache locality, Python object overhead, and memory allocation patterns mean the empirically faster implementation is the correct one at your current operating point. Document when to revisit. Do not ship theory over measurement.
TypeScript's type system at compile time versus Python's runtime type checking with Pydantic. Which word do you trust more for a payment critical API surface, and why in one sentence?
Pydantic at the API boundary, because it runs at the point where untrusted data enters the system and enforces constraints on real values, not inferred types. TypeScript's compile time guarantees evaporate the moment JSON crosses the network.
A principal engineer on your team proposes replacing your entire Python test infrastructure with a property-based testing strategy using hypotheses for all new code. You have 48 hours to respond, approve, reject, or modify, and why.
Modify. Hypothesis is Exceptional for boundary condition discovery in pure functions and for protocol implementations, it is genuinely underused. But using it as a replacement for example-based test in domain logic loses the documentation value of concrete examples that future engineers can read and understand. I would approve hypothesis as a mandatory addition to example-based tests for all pure functions with non-trivial input spaces, not as a replacement.
One Python library or two released in the last 3 years that you think is genuinely underappreciated by the engineering community, something that deserves more adoption than it has.
Stamina, the structured retrieval library by Heinrich Schlaueck. It wraps tenacity with a principled API, adds structured logging of return attempts, and integrates cleanly with both sync and async code. Literally logic is in almost every production Python service, and it is almost always written incorrectly. Wrong jitter, no back of cap, no logging of literary context. Stamina solves all three with a two-line decorator. Genuinely underused.
Stamina is going in my own services this week. Alright, suck it. Let us land this. Before I let you go, I want to give you the floor. 20 years, a CTO or Chief Architect search underway. If you had to distill everything we covered today, the namespace model argument, the capability confinement security work, the cross-language failure modes, the reconciliation war story, into the single thing you believe separates a genuine chief architect from an extremely strong staff engineer, what is it?
The difference is that a chief architect designs the forces, not the system. A very strong staff engineer designs systems, good ones, correct ones, systems that handle their failure modes, but they are designing artifacts. A chief architect is one level of indirection up. You are designing the constraints, incentives, and defaults that cause hundreds of other engineers to independently produce good systems when you are not in the room. Every answer I gave today, if you look underneath it, was really about that. The capability confinement invariant I would not write as a doc, I would encode it as a test, because a doc persuades one person once and a test constrains everyone forever. The contract first API rule, where the open API spec is the source of truth, that is not a technical preference, it is a decision about where authority lives so that two teams cannot silently diverge. Even the namespace model argument from the very start was about interface simplicity, lowering adoption cost, a systems of people observation dressed as a language one. Here is the sharp version. A staff engineer asks, is this system correct? A chief architect asks, what is the cheapest constraint I can install today such that the systems built here are correct by default for the next 5 years, including by people I will never meet? The unit of design stops being the system and becomes the decision-making environment that produces systems. And the reason it is hard is that you have to give up the satisfaction of building the thing yourself. Your best work becomes invisible, a class of incident that simply never happens. In a system you never touched, built by someone who never knew a decision you made 5 years ago is the reason their week went smoothly. If you still need the credit, you will not do this job well. That is actual transition, and it is more psychological than technical.
Design the forces, not the system, and let your best work be invisible. That is one of the sharpest clauses we have had on this series. Saket, thank you. 20 years, and it never once dropped to trivia. The namespace model causal argument, the Boyd-C bytecode attack and hash-based validation, the async Redis lock war story, and a final reframe of the architect's job that I am going to be thinking about for a long time. If you are hiring for a CTO, chief architect, or principal role, and this is the altitude your problems live at, reach out to us at Kritia AI Labs and we will connect you with Saket directly. To everyone watching, this is the Kritia AI Labs Tech Interview series. If this is the level of thinking you are aiming for, like the video and subscribe. The full mock interview playlist is in the description, spanning senior all the way to chief architect sessions. Leave a comment with the answer you would have given differently and defend it. We read everyone, and the best pushback shapes what we do next. See you in the next one.